So what is the syllabus? Here you can see that syllabus that is covering architecture, virtualization, infrastructure, network assurance, security, and automation. Actually, the syllabus is quite robust, and in this training course, what I try to do that I have covered each and every single topic in greater detail. So for example, if we are talking about the architecture, so I have covered architecture related to the campus area network, then architecture related to WLC design, then SD-WAN, a small piece of SDA, software defined access as well. QS you'll find in detail, and whatever topics that you're seeing here in the list, each and every topic point by point I have covered in this curriculum. Then virtualization also has been covered in detail. Even I have gone beyond this syllabus, and then I have added virtualization that is core for VMware networking or for VMware. So that things also I have added in these sections. Then infrastructure. So if you go and check this entire syllabus, you'll find that the core of this CCNP core itself is the infrastructure module. So in this module, you'll find that you have to know about layer 2 technology, layer 3 technology, wireless, and then IP services. And this is actually one of the lengthiest uh, module we have in this particular curriculum. This is very important where you are learning the layer 2, layer 3 wireless and IP services. So that will again add the tools inside your core fundamental of the networking technology. Then we have the network assurance. Inside that, you have to configure the basic troubleshooting and monitoring stuffs. Then finally, we have the security topic. Again, this security topic is as it is that we have in the old CCNP as well, I can say. So you have to know about the ACLs, the COP, some of the wireless security stuffs, some of the upcoming security stuffs as well. And then finally, we have 15% weightage for automation. We should know and understand say Python, JSON, APIs, how the APIs are working, Cisco EEM scripts, then finally the Chef, Puppet, Ansible, and Salt Stack. So in general, you will find this syllabus is quite robust and even challenging as well, because not only we have to know the existing or you can say the old stuff as well, but you have to understand the new stuffs as well. And Cisco has taken care of this thing in the mind that maybe tomorrow you have to migrate your WAN to the SD-WAN or your LAN to SD access or SDA. So all these things has been taken care in this CCNP enterprise syllabus. Either it's a CCNP curriculum or it's a CCI curriculum. Each and everything has been taken care. Whenever Cisco has formed this or drafted this syllabus, they have taken care of this thing in the mind that there are cases that you are supporting the existing network, or there are cases that you are doing the migration, or there may be case that you are supporting the brand new upgraded SD-WAN or SDA network. I'm going to walk you through the CCNP Enterprise certification, and we'll see that what are the changes that Cisco is putting from this coming Feb inside the certification. There is complete strategy change you can see inside the CCNP Enterprise. We know that Cisco certifications are always valuable. You will get much salary hike, means compared to other certifications in the market. You will get much more reputation, and they are highly valuable certifications. We have complete sort of certification, means different type of certification like associate, professional, and expert. And as per your certification, even you can negotiate with the companies in terms of salary and other aspects. So they, as per your certification, they will think that you have the right knowledge, skill. You are very skilled in the IT. You are a skilled IT professional, and then you can go and ask for the salary because you are able to take the responsibility. So that's the reason the company will pay you. Here you can see that 99% of organization use certification to make hiring decision, because these certifications are structured in a way that they are going to test your different level of skills. So for example, if you see the old certification stack that we have, means now it's 28th of Feb. So now this become old, and now in the next slide I'll show you the new that will be available from 24th of Feb. So this old certification, you can see most of the people at the moment, at this point of time, they have, we have associate level certification, professional level, then the expert level, and different type of technologies are there. So for example, routing, switching, security, service provider, wireless, others. Now this has been changed in this. So now you can see that certification has been simplified, but on other hand, that will become much more focused. So now this CCNA, that is the associate level certification, this is the basic for all the professionals, and then again you can go for the expert. But CCNA become basic for the professional level. Now this CCNA will serve the purpose for enterprise, service provider, data center, collaboration, and security. And parallelly, you may have the expert level certifications in that particular domain. Now again, Cisco has other certification as well, and that is the DevOps, and their track is different. But you can see that 95% or maybe 90% of things relates with associate CCNA, and then the professional, and then the expert. Now here you can see that if you've done your CCI, so you know that inside CCI, you initially, means before this program, you have the theory and the lab, and that is 8 hour, very difficult type of exam. And there you must need a very high percentage, for example 75 to 80% of marks in all the sections to pass your CCI. Now, comparative to CCI, CCNP exam is also very highly skilled type of things that they are going to ask you. It means they are going to check your depth knowledge inside that particular domain. Here you can see that you have the enterprise core, security core, service provider core, collaboration, data center core. So things has been grouped strategically inside different type of core. So you have one foundation, you have one core, and then you can choose the uh, expert level, or more precisely the specialist level. So you have the core. First of all, you can see that you have the CCNA, and then you have core in these, say for example 5 domain. So you need core knowledge, and then you can go and get your CCNP, and then you can go and get your CCI. So from your core, now you can see that you don't have written and a lab exam, although your core, after your core you can go and write your lab exam. Okay, so choose between 2 lab exam inside this enterprise core. And what are 2 lab exam? If I go back, you can see that you have enterprise infrastructure, you have enterprise wireless, correct? So like that you have to choose. Now if you are in the security, choose your concentration, means you do your core, choose your concentration, and then take the lab. Like that you have all the tracks. You can see that from the slide, it's very much uh, clear and what to do at what point of time. Again, here you can see that you have enterprise, security, service provider. For everything, you have core exam, and you can go and have your CCNP. Means CCNP has 2 paper. One is core and one is the concentration, or one is the focused exam, and then you can go and write the lab exam. So for example, for enterprise, you have enterprise lab related to wireless and the CCI infrastructure, where you have different things like SD-WAN and SDA. Those new things are also added. All right, so now you can see that today means again, today is 27th or 28th. So now we are in this certification track. So 24th of February, we have Enterprise Core, that is mandatory, and then you can choose one. So either it's advanced routing or SD-WAN or enterprise, wireless or wireless implement. Like that, you can choose the certifications. Summary, that Cisco has tried to reduce the number of amount of certificates, and it has been focused and grouped well logically inside single technology, or inside single group, and is still um, and even they have removed the CCI written as well. So you can do your CCNP core and you can write your CCI. You can do your CCNP core and then you can go and focus on any of the specialized exam, like say for example SD-WAN or enterprise design, etc. All right, so this is the track. Everyone has a home, everyone gains, everyone maintains their certification, everyone awarded badges. So obviously by the end of day, once you complete the track, you can see that you have different type of badges. You have a specialist, then you have CCNA, then you have CCNP, and then you have CCIE. So you can start your journey and then you can slowly move your career from a specialist to the expert, and that's the goal. And once you complete your CCNA up to CCI in one particular domain, then you can move to the other domain. Okay, so there is a wealth of knowledge available, and if you want to gain it, if you want to become expert, go to one technology, complete it, and then move to other technology. That will be the strategy. This particular course is focused on CCNP Enterprise, and once we have one of the core topic, then we'll go and check the SD-WAN. Alternatively, we can go and check the other stuffs as well, like design, advanced routing, enterprise automation. But at this point of time, we can check CCNP Enterprise and the SD-WAN, because the combination of enterprise and SD-WAN will give you weightage. At the moment, SD-WAN is very hot in the market. It's very demanding, and if we combine like these two, core plus SD-WAN, so market value will be very good. What are the core skills you need? We'll see that we have complete syllabus. You can go and check. So now this was the past, where you have route switch, reshoot, arc, and other stuffs. Now in future, now present, I better tell this. This is the present. So you have enterprise core batch. You have a specialist. Uh, then you have the advanced routing batch. Wireless batch means for individual exam also you will get that exam certificate, but better that will go and club. So CCNP Enterprise with any of the four, correct? All right, so now here again you can see the summary that you have. Like if you want CCNP Enterprise, you do the core and you can do the advanced, or you can do the core, you can do wireless, any of these two. You can do the core and then you can do the design. And here you can see that CCNP Enterprise, Enterprise. Okay, and just try to tell that how it is equivalent to CCNP RNS, CCNP wireless, CCNP DP. So suppose if you want to do CCNP DP, you do the core and then design, and you are the DP. If you want to do CCNP in wireless, the do all these three, and then you are CCNP in wireless. If you want to do CCNP RNS, do these two, and you are CCNP RNS. If you want to be CCNP in SD-WAN, you do core and SD-WAN, and you are the CCNP in SD-WAN. All right, so this was the certification changes, and I hope that you understand that what type of changes, what certifications we have to obtain our new CCNP, and from there we can go and prepare for CCIE as well. Hi everyone, welcome to CCNP Enterprise Core course. This course is divided into 6 different parts. Here you can see, starting from architecture, virtualization, infra, network assurance, security, and automation. You'll find the detail of these topics and the subtopics in this particular link. I hope this course will be informative and you'll gain new knowledge from this course. Thank you. Let us start with 1.0. That is the architecture, and what are the things we have to learn in this. We need to understand the design principle, the resiliency, the scalability, the redundancy, the WAN deployment options, etc. So here you can see that you have a long list actually, starting from 1.1, then 1.2, 3, and then 4, 5, 6, 7, up to 1.1 to 1.7 you have. Now here you can see that inside 1.4, you have to understand the SD-WAN design principle. 1.5, you have to understand about DNA or SD access design principle. 1.5, you have this QoS, both in wired and wireless. And then 1.7 is taken from the old curriculum. Even in the this 1.6, that is the QoS, that is also taken from the old curriculum. So it's again the mix of the old CCNP plus whatever new technologies we have, and why we have such type of mix, that I will explain you in the upcoming maybe third or maybe fourth slide. You'll understand that. Now let's cover point number 1.1a up to B. And what is the agenda for that? So you have to understand the enterprise network design, such as tier 2, 3, what is fabric, fabric capacity planning, etc. And then the high availability and redundancy, like first of redundancy protocol and SSO. We'll see that, because although this is only point 1.1a and B, but we have multiple videos to cover these topics, because again, this is a big topic. So let's try to understand this 1.1, and let's try to figure out that what type of design principle we have and why we have. So once we understand that why we are using this, that will solve our purpose. So we should understand that why we need this. Now let's see this WAN transport technologies. In this slide, you can see that the evolution of the architecture and design principle. So early network, we have the fix and the bridge network, maybe 35 years back, when Cisco has invented routers and again the switches, and they try to connect different type of network. Here you can see that actually if we go from back behind that, say if we go and check the ARPANET and their principle and the TCP/IP discovery and their evolution, you can see that when the protocol first invented, and then again when Cisco come into the picture, and they have uh, revolutionized the complete network domain or the industry. So here you can see that from 1990, when we have the multi-protocol and the business support model for IT, and at that time we have various protocol like OSPF, BGP. Those are the commercial protocol. Say still in some of the places you can see that we are using RIP RIP. This again the old traditional methodology. Even we are using frame relay. Still some places we are using frame relay or X.25, etc. But now we are moving. So now if you see the journey from 1990 to 2000, where we have mission critical network, where we are supporting real-time traffic, we don't have even 1 minute of downtime, etc., etc. Means it's a highly mission critical network, and uh, if we are dealing for those topologies, how we are going to build those topologies. And again, if you move from 20, this is 2000 to 2020, now you can see that the evolution of SDN, and companies they are start deploying the SDN, either it's SD-WAN or LAN or campus automation or DNA, etc. So now is this the complete movement. Now again, this is the movement of network. So if you know the architecture principle, that what we are using in mid 90s or 2000 and now what we are going to use in 2020, actually each and everything has covered in this core. So we can start from our fundamental BGP, OSPF or other routing protocols, and then we can move and check that what type of protocol has been used inside SD-WAN or DNA. So for example, BGP, OSPF we are using here in the existing network, and OMP and TLOC we can use in SD-WAN, or Lisp we can use in DNA, etc. Okay, so we should have the clear picture, and if you're doing the migration from your existing network to the upcoming network, so if you know your existing network, if you know the upcoming technology and network, then only you can do the migration, and uh, a less number of issues will be there. All right, so this will be your summary slide, what we are moving, what we have at this point of time, and what we need in the upcoming network cycle. I mean, when we are refreshing the cycle or when we are migrating the cycle, and what type of challenges we have here. You can see that's again the uh, a small thing, means everywhere in all the places you will find the same type of challenges. Means the challenges are not as small, but in terms of gathering the facts, that's the common. So what are the common factors you want to improve, or what are the challenges you have that you don't want inside the SD-WAN or in the next gen network? So we know that scalability is one of the biggest issue. Means you can't scale. So you have this scalability, and we can discuss a lot and lot and lot about the scalability. Now when we are talking about scalability not only in terms of your network or how many devices you have, but scalability in terms of routing capability, your IPsec capability, or even you can go and do some sort of deployment over the cloud. So scalability plus cloud integration means you can mix these things and you can think all in a single bucket. Then how you are going to integrate with IoT, Internet of Things, because again this is a big huge topic, and we know that Cisco DNA, Digital Network Architecture, or ST Access, they have the capability to understand. Even Cisco is making the IoT related products as well. So we have the chance that we can integrate IoT devices inside the enterprise network. Then what is the fast IT changes? What is the next? Can you do the automation programming? Do you have single pane of glass from where you are managing all the devices? Okay, so if I go and summarize these topics, again I told you that all these problem and the complexity that we have, they are common at this point of time. And if you see the existing network, still we are using the access distribution and core routing layers or L3 layers. So we have some sort of C and then P and then P, and then the network, they are divided into multiple routing instances or forwarding virtual routing forwarding instances, etc., etc. So you can go and support the network level virtualization as well. So what I will do, let me quickly mark here that what is the common issue we have in the existing network. I will not add cost at the moment, leave this. We can discuss cost later on with this cost aspect, because you may find that cost is also one of the driver to make or to do the refresh in the network. So what we want scalability, and this scalability we want in routing, and we want in IPsec as well. And that's why we have DMVPN versus new SD-WAN IPsec or new SDN IPsec. Second thing what we want as a network, that we want integrated security. So at the moment I bring up my controllers, control plane, data plane, etc. I should have one solid, common, unified, secure fabric. Correct? So that's why this is also very, very important. Thirdly, what you want, we want that the overall cloud integration means nowadays to, again, this have some cost effect. So companies, they don't want to go to the central hub or data center and then they want to go and use either DIA, direct internet access, or direct cloud access. Rather, from branch they want to do local breakout, and then they don't want to use the resources hosted over internet or the cloud. So that's again important in cloud integration. Now, these things you have. Apart from that, one very important thing here, I will add it, that is possible in the existing network as well. In the SDN solution, it's by default. That is the segmentation. So once you do the segmentation, the scalability, security, cloud integration, and segmentation. Apart from that, you want other features like you should have full visibility. Then you want monitoring. You want a single pane of glass from where you want to do all these monitoring. You want solid reporting. You want easy way to do the troubleshooting, etc., etc. Correct? So these are the things and these are the terms we have, and we should consider these things inside the architecture principle. So let's just stop here, and in next section, uh, let's continue the same architecture principle, and I will add some more valuable point in the upcoming sessions. Let us continue our discussion and understand more that what we have discussed earlier. So we have discussed that yes, we have different technology, means in terms of evolution of network. So we can check the 1990 network, then 2000, then 2010, and then 2020 and coming forward. So what is the major change and how we are going to reduce the complexity in terms of design deployment? That actually it's very interesting. So here you can see that with the evolution of MPLS, and when the MPLS network it's start gaining the popularity, at that point of time you can see that how you can visualize the network. So here in the diagram you can clearly see that you have hub network and then you have a spoke. Somehow this design, this is giving some sort of idea that in upcoming iteration we are going to use some sort of spine and leaf structure. Sometimes it is referred as a cloth fabric. So you have your leaf, you have your spine, all the leaves, they are connected with the spines, and these leaves, they are not connecting to each other. And that's the thing we are achieving. Now again, when you are achieving this type of topology or this type of network where you have all the devices by default, they are one hop away. At that point of time, are you able to do the segmentation? For segmentation, we have already VRF, virtual routing and forwarding, and this is now from the years. So we are using the VRF technology, and later on you will come to know that in SD-WAN we are using VPN. That is nothing but the VRF only. Name or the term going to be used as a VPN, but logically or technically also they are also VRF, virtual routing forwarding. So now the complexity will increase when you have multiple devices, when you have different type of traffic and you mark those traffic as different type of VRF, how you're going to do the routing or maybe overlay routing, etc., etc. This is still we are using in the existing network. It is possible, but the thing is that we need to write actually the more line of codes, more number of configuration you need it. Okay, but still we are using, and you can see that we have multiple technologies like VRF Lite or MPLS VPN, because BGP is a nice protocol which is supporting all sort of address family related to VRF and even other address families as well. Now again, in this design principle, uh, how we are going to deploy the network. Do I have a single provider design? Do I have dual provider design? Again, if you go from single to dual, obviously the cost will increase. The high availability and the redundancy feature will increase. But anyways, the cost will increase. Or you are going to use the overlay network design. And this is actually the future. Cisco has started their overlay network design, means technically we are telling this independent of transport. So either you have a dual or three or four different type of ISPs, you don't care. You are creating tunnel on top of that, that's the overlay tunnel. And Cisco has introduced their intelligent WAN where they are using DM VPN as a overlay tunnel. Okay, but again, we are using IWAN and DMVPN, although so many companies they are using it, but again you have to write n number of codes or more number of lengthy configuration. So Cisco is telling all their existing network that from IWAN you can migrate to Cisco SD-WAN. Okay, why? Because again you can see the cones that increase design complexity, additional technology needed for SLA over commodity transport. So there are some extra overhead that is there, although the design and the solution is neat and clean and beautiful, but still you have some extra things that you can't do in the SD-WAN and the automation and the SDN solution that is there in the IWAN. So that's why this movement is there. Now let me quickly show you some of the slides related to single carrier and double carrier or dual carrier. So here you can see your network may look like that. So although you have different link, but you have single carrier. Suppose if one of the carrier, or because obviously you have single carrier, but suppose if that carrier will go down, at that time you have loss, and that's why it is listed here in the con that bound to single carrier for feature velocity does not protect against MPLS cloud failure with single provider. Obviously, if that cloud will go down, I don't have resiliency or availability that I can go via the other carrier. Obviously, this thing I have in the dual carrier, but again, the complexity is there, the cost is there. So you can compare here the pros and the cons. The con is that increase bandwidth paying for bandwidth twice, increase overall design complexity, may be reduced to common denominator between the carriers. Means overall you are increasing the resiliency, but cost wise there is issue. Now considering this diagram and this diagram, and again considering the overlay network design, if we have best out of all these three, so that will be the exact solution we are looking for, and that's why we are looking forward for SD-WAN solution. Again, we can see this all these things inside section 1.5. So let me quickly show you that 1.4. So we have 1.4 and 1.5 where we can address those design issues and how SD-WAN and the DNA or SD access combine together, and they're going to solve these issues. That also we can discuss in the upcoming sections. We are still in the basic section where we are learning what type of existing terminologies we have, and then what are the new things we are going to learn in the new CCNP curriculum. So let's discuss the WAN overlay technologies. Inside this, we have a layer 2 overlay and a layer 3 overlay. Means this overlay technology or terminology is not uh, new actually. This is coming from the old technologies. Now we'll see in the SD-WAN and the DNA and maybe in ACI. that is again the data center topic, that these overlay terms will come again and again and again. So now we have something called underlay, that is your physical infrastructure, and then on top of that you are creating virtual dynamic tunnels. This can be layer 2, this can be layer 3. Layer 2 tunnel examples, here you can see that you may have layer 2 tunneling protocol L2TP version 3. You may have OTP or VXLAN, that's the very popular term we have, VXLAN, and this we'll learn more and more in the upcoming session. When we are talking about layer 3 overlays, we have IPsec, we have GRE, we have Lisp as well. Now this Lisp I'm going to cover in the next slide, but at least you can understand that yeah, you are extending layer 2 fabric, or you are extending layer 3 fabric, or to extend the fabric either you need layer 2 or you need layer 3 uh, address families or addresses, etc. Now, what is there in the SD-WAN or what is there in DNA is that we are going to automate this process. So you need not worry. So for example, in SD-WAN to create the IPsec tunnels, like in I-WAN, we are creating the DMVP and phase 3 tunnels. Here you're not worried to create the IPsec tunnel. At the moment you bring up the fabric, automatically those tunnels will get formed. Now, when we are talking about the tunneling technology, a normal IP packet, a normal packet, we have the payload and the IP header. In GRE, again, you have the payload and the IP header, and then you have extra overhead for GRE. Correct? In IPsec mode, either you are using IPsec mode in transport or tunnel mode. In transport mode, you have less overhead in terms of packet, but in tunnel mode, that is much more secure, and by default, most of the technology they are using the IPsec tunnel mode, where you have the inner header and the outer header. So at that point of time, obviously your header size will increase, but the level of security will also get increased. Correct. I'm not going deep inside the IPsec and how IPsec is working and GRE and how GRE is working. It's just the overview. We have just started the course. And as per the agenda, whenever these things will come and it will tell in the exam or in the curriculum that we have to go deep dive in this particular topic, I'll go deep in this, that I'll do the packet capture, we'll analyze the packet, etc. etc. But at the moment, we are just getting familiarity with these technologies. Already these technologies are existing, and what new we are going to get in the uh, new enterprise setup or in the CCNP enterprise. And now, for example, Lisp, locator ID separation protocol or identifier separation protocol. Now, if you understand Lisp, so for example, I already told you that you have LAN based SDN. So SDN solution, you have three things. You have LAN or SDN for LAN, SDN for WAN, and then you have SDN for data center as well. So data center. Now for LAN, the common term is SD access. Obviously, I'm talking only in terms of Cisco. So in Cisco, we have DNA is a name, but the SD access is the technology. In WAN, we have SD-WAN, and in data center, we have application-centric infrastructure or ACI. Now, if you go and learn deep all these technology, you will find that everywhere you have some sort of leaf spine type of a structure. So suppose if I have two spine and then leaves like this. Say again, I'll take one more leaf so I can show you the redundancy. So all these leaves will go and connect with the spine, and leaf they will never connect. These spines, they are working as a route reflector, means these spines, they have the database. So now these leaves, whatever endpoints or whatever devices are connected with these leaves, in DNA they are termed as a edge node or edge devices. So these edge devices, whatever network, whatever entries, MAC address, IP address, etc., etc., whatever they have, they are sharing with their spine or their parent. Now this spine in DNA is mapping system or mapping resolver. Now this spine in ACI is spine and leaf. The spine and leaf is a term inside ACI. Now in SD-WAN, loosely if you analyze, you'll find that you have something called vSmart controller who has all the database for all the routing information. He is the controller or the control plane device. And he is working as a route reflector. In ACI also, these spines are working as a route reflector. And suppose if you are not knowing all this technology, so there are chance that you will get confused that, oh, what I am telling that, okay, in SD-WAN, the vSmart, in ACI, this fine, in DNA, uh, it's actually the control plane device. Sometimes we are telling this as a control plane routers or maybe border router, etc. So again, we'll see later on, but what at this point of time you can mark or understand is that you have some common authority. You have say common authority just like DNS server where they have all the topology information, all the database information. You think that you have the database information. Now these endpoints they have offloaded with the information, so they don't have entire topology information. They know their local system or local endpoints, local entries. Once they have their local entries, they are teaching or they are telling the common authority that this local system I have, this local IP MAC I have, you please store at you. Likewise, he will also tell, okay, you please store with you. And when this guy wants to communicate with this guy and he don't know how to reach it, he will send the query packet to him. I want to reach there, and he will reply in a way that now they can communicate directly. Okay, so these are working as a proxy on behalf of, and most of the technology, most of the SDN technology, we have the same analogy. All right, so now we can understand all the different technology. If you say, for example, if you know other non-Cisco technology as well, for example, NSX T or any other SDN solution, there also you'll find the same type of thing is happening. Okay, and then once you start comparing these technology, it will become easier to learn and understand, because again, every day some new thing will come and it's almost impossible to learn and memorize all those things. So better you start comparing different technology, and then we can learn it easily. In section 1.1a, we need to discuss about quality of service as well. Now we are going to see the design aspect of this, because we should understand the core quality of service things, and then we should understand the SD-WAN quality of service things. Now the basic principle will not change. So how we are going to do the classification, marking, policing, shaping, scheduling, etc., those things will not change. So what are the things are going to change? The way that we are going to implement to the devices, those things are going to be changed in the SD-WAN. So I have already uploaded complete course for SD-WAN. There you can go and check how we are going to use this QoS actually inside the SD-WAN. Now at this point of time, let's focus that what are the basic components of quality of service. So here you can see that we have three important things: classification and marking. You classify the traffic, you mark it. We have policing. Policing is something like you have some sort of a strict rule with the traffic. So if certain limit or threshold will breach, it will start dropping the packet. And then we have this scheduling, including queuing and dropping. Means you want to give some sort of buffer in case if you have congestion. Means you don't want to directly drop the traffic, but you have some sort of buffer for that. Now here on top you can see that you have different type of class of traffic. Say I have voice class of traffic, then I have video class of traffic, telepresence, and data. Now, for all these type of traffic, they have different requirement. So some of the traffic are UDP based, some of the traffic are TCP based, some of the traffic that we have need high latency, some can tolerate with delay, etc., etc. So now you can see in the bottom that say for voice traffic, you have UDP priority, but latency should be less than 150 millisecond. Otherwise, this voice will auto destroy. There is no meaning for that. Means whenever we are sending the voice packet, you think that your TTL is set with 150 millisecond. If it is not delivered between that time, it will get lost, something like that. You can see the jitter should be less than 30 millisecond, loss should be less than 1%. Now why we are discussing this? Because the first fundamental of QoS is classification and marking. So you can do the classification of the traffic, and you are understanding that what is the loss, latency, and jitter requirement for different type of traffic, including that what type of protocol they are supporting. So you can see this voice, video, and telepresence, they have UDP, means they are very much real-time traffic, but you want trustworthiness as well, you want security as well, and that's why you have the business traffic, or you have business data that is using TCP protocol. And that's why here you can see in the bottom that you have mission critical application, maybe SAP, maybe any type of database, etc., etc. Now the bottom line that you are seeing here, that is actually important when you are going to create the QoS policy. In other words, when you are going to create the policy, if you breach certain SLA as specified in the bottom, then that policy can take some decision. So dynamically changing the route, etc., etc. And that's it. And this particular feature has been optimized in the SD-WAN solution. So here it's very much coding based. You have to understand the protocol, means the device should understand the protocol. According to that, you have to write the code, and then it will take action. Correct? So first thing is that to do the classification of traffic, there are several methods in QoS that you can go and deploy it. Here you can see one of the example for that. So you are creating the policy map, then you have class voice, because this is high priority traffic. You're giving priority for voice, you're giving priority for video. Then you have the critical data, you're giving 15% for that. You're using some random detect DSCP based. Again, there are different type of drop methodology. Means you're going to use RAID, random early detection. You're going to use tail drop. So those methods you can use. Again, you can see the data bandwidth percentage is 19%. This is again just an example. Your scavenger traffic, you are giving a less bandwidth percentage. Network critical, you are giving this 3%, etc., etc. So bottom line is that you need to write the code for all the devices inside your enterprise infrastructure, and then you have to configure it manually one by one by one. See, suppose if you have same type of hardware at 1,000 places, you have to write this code, or at least you have to do the copy paste to all those 1,000 devices, rather than if you do this thing via the SD-WAN. It's like you have, once you created the template, you can push from the management plane to all the devices. Correct? And here you can see that how this queue look like. So the important thing here is that you need to do the classification, and then you have to map with the queue. So classification or forwarding classes to queue mapping, that will be the step number one. Again, on top you can see this is for low latency queue or class based weighted fair queue, where you're adding the voice, video, etc. Now we have a nice example here that is clearly telling us that traffic shaping. So without shaping, how it look like. Once you apply the shaping, then how it look like. Once you apply the shaping, then the shaper typically delay excess traffic, smoothing burst, and preventing the unnecessary drop. If it is polisher, it will chop up, it will directly drop the traffic. Again, we have other example. So suppose this is your configuration, and once you apply it, obviously you have one bandwidth pipe, and generally we are applying this policy to the WAN facing interface. So suppose if you have 300 Mbps speed, correct? So you have 1 gig interface, but as per your agreement, you have 300 Mbps speed. Now, how you are going to use that uh, classes, and how you're going to allocate that 300 Mbps speed with priority, with some scheduling, with some RAID to the device that you can see here in the example. And again, we are making this as a child. Child is called under inside the parent. Inside the parent, we have the shaping, we have some buffer limit. Okay, so this is the way that we can go and apply the QoS. Again, we have one nice example here that you have your enterprise devices, you have your MPLS devices, where means in inbound, what type of policy you want to apply. And these examples that you are seeing here is the standard one that Cisco is recommending. Still, if you want to learn more about QoS, you can go and check the QoS, Cisco QoS deployment guides, and there are tons of information we have um, over Cisco URL that we can go and get it. But this is something like a standard format. So all the companies, they have this type of existing network where they want to apply QoS. Now here you can say that you can't apply QoS to the ISP side. So whatever QoS you have to the ISP side, the same thing you want to match to your side as well. And that's why if you go and check the E and F configuration, so outbound policies, you can see the outbound policies as LLQ or class-based weighted fair queue, remark, real-time traffic, class-based weighted fair queue, etc., etc. Then you can go and check the service provider in the bottom. So what is there in the outbound? What is there in the inbound? So obviously my outbound will be the inbound for the service provider, correct? So we are going to manage this enterprise network, and then according to our QoS, we can consult the service provider and we can tell them, okay, you can map this DSCP, this policy from your side as well. As long as we have the common agreement, the common configuration, things will be better. Now again, this design strategy that you are seeing here, there is major change in the SD-WAN. Now to reduce the cost for the SD-WAN MPLS, because you know that MPLS cost is too much. What customers are doing, instead using 100 Mbps MPLS, they are using 1 gig internet. So you will see even here also, in upcoming sections, I will give you some slight design related things or stuffs that you can compare later on in your study as well, that what is existing design means what is existing hybrid design, internet plus MPLS, and then when we are moving to next generation SD-WAN type of network, what design possibilities we have. And again, you can argue that okay, MPLS has this advantage, internet has this drawback, etc., etc. But nowadays, the big enterprise, they are using dual internet connection. Primary, secondary, both they are using 1 gig or maybe 2 gig internet interfaces, and then they are load balancing the traffic. All right, so if you have GRE or IPsec QoS consideration, on top you can see that you have normal packet without QoS. Obviously, we know that in IP header we have TOS type of service. Now, if you are using QoS with GRE, so you have your inner header, you have your GRE header, you have your outer header, and then you can see this TOS is propagating from inside to outside. Likewise, if you have IPsec encapsulation, where you have inner header and outer header in case of IPsec tunnel mode. So you can see that we are retaining the QoS marking. All right, so these are the examples related to QoS, and just again, this is again very much high level, but you should understand, and as per our curriculum, exam or this is to expect that we should know these variations. We should know that what we have in the existing and what we are going to have in the upcoming SD-WAN QoS. All right, so let's stop here. This session is quite interesting because we are going to discuss about the WAN and the LAN architecture designs. And actually, we have started this course and we are studying about design principle, what is existing, what is going to become, or what is the SD-WAN or DNA, etc. As per this the scope of the CCNP exam. Now, thing is there. So I have one dedicated slide. I'll come after 2 to 3 minutes to this particular blank slide. Let me quickly walk you through 2, 3 slides. So we know that there is demand, there's drastic demand in the networking, means there are so many things that try to connect with the network. Means we have IoT, we have so many handheld devices, we are managing different type of mobility features or mobility devices. We are managing everything maybe from the cloud, so we can integrate with the cloud. We have different applications. We want to do the visibility for the applications. To manage all these devices, the complexity will be very high. If you directly going to the cloud, your threat surface will increase. So you should provide security even from the inside or outside your, etc., etc. So the bottom line is this, that you have demand because you have to integrate different type of devices inside your networking infrastructure, and then due to that complexity will increase. Manageability will be the challenge. In that case, your security, or you may have the holes in the security. So everything should be integrated, should be tight. And what will be the solution? So the solution is that instead using the monolithic, or instead using the existing way to manage the IT infrastructure, you can check the SDN, software defined type of architecture. Now what SDN will provide, at least at this point of time, is that you can focus on application. So SDN, the true capability of SDN is that now we can build the policy based infrastructure. Now what does it mean? So for that reason, I have this particular slide. So I'm going to draw one very nice difference in between all the technologies that we have, all the technology related to SD-WAN, and this will give you nice idea about different type of complexity that we have in existing and where we are moving actually. So for example, we have LAN, we have WAN, and we know that we have data center as well. Now for all these devices, if we are connecting LAN, obviously you have LAN. If you have multiple ISP, you can go and connect with the WAN, and then somewhere you may have your data center, correct? This is something like your existing network where you have spread branches and you're using existing methodologies to manage your IT infrastructure. Now what is the different when I'm going to use SDN approach in to manage the LAN, WAN, and data center? For LAN, we have something called DNA or SD access. For WAN, we know that we have Cisco WebTel SD-WAN. For data center, we have ACI. Now we know at this point of time that all these infrastructure, all these component of the IT infrastructure, they have control plane, they have management plane, they have data plane, they have policy plane. Somewhere you will find the orchestrator plane as well. So who is the control plane for DNA, the management plane for DNA, data plane, and policy plane, etc. So now this thing you have to study, and you can compare different technologies. So the control plane is, again, you will see that Lisp is a protocol who is managing the control, or who is providing the control plane information. But for that you have border routers. For SD-WAN we have OMP, Overlay Management Protocol, who is managing this, but the controller is vSmart. ACI, we know that we have a spine and leaf architecture, and we know that we have the COOP protocol. Maybe you have MP BGP protocol to manage the control information. Correct? What about management plane? For management plane, we have a DNAC center, that is nothing but Epic EM, Epic Enterprise Module. This ACI, they are also using Epic, but this Epic and this Epic is 100% different. This is for your DNA or DNAC at this point of time, we can understand. And this is there for your data center manageability. Then what about SD-WAN? In SD-WAN you have vManage. Then the data plane, you are going to use VXLAN. You have edge routers. For SD-WAN, your data plane is nothing but IPsec tunnels, but you are using vEdge or cEdge, the Cisco edge devices, Cisco routers or Viptela routers. ACI, you have leaf and a spine structure. So your leaf will be your Nexus devices. Here in the spine also, those are the Nexus devices that you can check the reference sheet or data sheet. But Cisco is using IVXLAN, something you can tell that intelligent VXLAN, because they have this one field for having the contract information as well. Okay, or maybe policy information as well. Some extra bits are there in that VXLAN format. Then the policy plane, who is the policy plane? The ICE, we are integrating with DNA. So ICE is the policy plane. For SD-WAN, your vSmart is the policy plane. And for ACI, again, your Epic is the policy plane, because there you can go and build the policy and then you're pushing to different type of devices. This is the reference, and we can see, and now you can think that, oh my god, my existing network is better than what these stuff. So now you have to learn, understand DNA, SD-WAN, and if you are doing your data center study, you have to learn ACI and lots of programming as well. Okay, so this is the overview we have for all the upcoming technology. At least you will learn the SD-WAN and the DNA plus the WLCs. I haven't shown you where the WLC is fitting in the picture. I will check later on in the DNA section. Again, this is the DNA framework that you're constantly learning the network, and then you can take the decision. We'll discuss more and more about this framework in the upcoming session. But at least you can see that you can manage the entire network from the cloud management. Then you have this full automation capability. You have analytic engine inside DNA. It's a big UCS box that DNA boxes are. You have full visibility, because these devices, these Catalyst devices that we are using, or the hardware that we are using for DNA, they are very smart, intelligent, and they have programming chip inside that. And due to that, the telemetry feature by default will be there. So we have the full visualization for all those events and things are happening with help of DNA. We can visualize the network. Then we have the full programming facilities, either for the physical or the virtual infrastructure. Everything is integrated inside the security. We know that we have the policy plane that is nothing but ICE, from where we can push the policy to the DNA devices. So the principles are open, programmable, API driven. And obviously we can do everything, that whatever we can do with the CLI or GUI, we can do with the API as well. Now here you can see in the diagram that you have the DNA center, that's your management plane. You have SD access and SD DNA is a term and ST-access is the technology actually that is used. Then you have the hardware as a Catalyst 9K, and then you have the security features that you have in encrypted traffic analytics. It's a big thing. Actually, DNA is a big thing. SD-WAN is also big because now whatever we have studied, we have to rethink our study, or we have to redo the study. And if you compare, or if you try to compare that what we have done in the existing network and what we are doing here in the DNA or SD-WAN, so actually there is no much a scope of comparison. We should think that this is the new thing we are learning, and then we can start from the scratch. All right, so let's just stop here, and next section is interesting. That is our core existing technology that I'm going to discuss in campus design, and other topics are also there. This section we are going to discuss about the technology that we know, the multi-layer campus design, and obviously in the upcoming section we'll discuss more about the upcoming technologies. So we know that we have our core layer, distribution layer, and access layer. And again, I have slides for all these layers, so we can go and discuss there, but everything is going and connected to the core, and then core is taking decision that how to send and where to send the summarized routes, etc. So here you can see this core is connected with the devices again at the distribution layer, and then you have the access layer where we have the WAN, where you have the internet, means you may have hybrid topology where you're connecting with the WAN, internet, and you're connecting with your data center as well. Again, this is one of the campus design, and maybe at this point of time, 80 to 90% of campus design is like this only, because now we are slowly moving to the DNA. The adoption rate at this point of time for DNA or SD access is not that huge, but we are expecting that in coming 1 to 2 years, or maybe 2 to 3 years, we'll see much more adoption for SD access. Okay, so this is the core that you have, the core, distribution, and access layer. And again, if you split this diagram, you'll find that you should have, say, structure, modularity, and hierarchy, that you have the core, access, and core, distribution, and access layer, and where you are going to connect your MPLS circuits, where you are going to connect with your internet, where you're going to connect your IP telephony services, etc. Okay, so let's quickly check that all these layers, what they are offering, what exactly they are looking for. So here you can see the diagram left and right. You have the boxes and how it look like. So you have the core, distribution, and then you have access. Like that you can think. We have dedicated slide for all these layers, so better we'll check all these slides one by one. So what's the use of the access layer? What access layer is doing? You have L2, L3 features. You can go and use the high availability security QoS, IP multicast, etc. You can go and use QoS. You have IGMP trust boundary. You have broadcast or multicast boundaries as well. If you want, you can suppress those requests. You can go and use various type of optimization method for loop prevention if you are using L2 methodology. If you are using L3 methodology, you can use routing protocol like EIGRP, OSPF, etc. If we are doing high availability and redundancy, we can use PAGP, that very less guys are using Cisco proprietary port aggregation group protocol. Generally, we are using LSAP, link aggregation control protocol. If you have, if you are using UDLD or FlexLink, etc. Okay, so this is something where you have your trust boundary, where you want to protect your network. Obviously, you want to protect your network to all the places, but this is the place where the endpoint will come and connect. So at this point of at this particular level, you want higher security, you want segmentation, you want MACsec, BPDU filters, filter guard, etc. Correct? Now, next you have the distribution layer. Distribution layer is there. This is the second type of backbone or second level of backbone we have, where you want to apply some more mature policy and high availability features. So that's why we have the high availability load balancing QoS. We can do the aggregation of all the access at the level of distribution, means you have less number of devices that is there in the distribution label at compared to the access layer. Even in access layer, you can use 2K series or 3K series switches. In distribution layer, you can use 4K or maybe a 6K. Now Cisco is requesting everyone to use 9K model of switch, so you can choose those recommended or the supported models in terms of hardware capability. They can do the route summarization, fast convergence, and HSRP GLVP. That we have separate section for first hop redundancy protocol, HSRP GLVP, BRRP in upcoming session. So we'll discuss more in the upcoming session about that. Core layer, obviously, is the core. This is the backbone. You want high availability and the scalability for the core layer. They are the aggregator point for all the routes. And again, if you go and refer this diagram, this particular diagram, you can understand that things are converging towards core layer, and then from core layer, you can distribute those routes to the other locations as well. Again, here you can see in this diagram how it look like. So you have layer 2 access, you may have routed access, you may have virtual switching, etc. Then you have the distribution level switches, everything is coming to the core, and then it is going to one of the branch or the data center or other branches. So this is the network that we are very much familiar. And again, with respect to design, you'll find that there are variations that we need to consider. Obviously, there is the evolution for the hardware. For all the devices, there is evolution or there is upgradation for the software also for all these devices. So how much virtualization these devices are supporting, uh, how much hardware, again that depends, means how much throughput as a customer or as a user I want from these infrastructure. So according to that, the hardware can be implemented, and it's recommended that even if you have this network and you want to upgrade the switches in this network, use Cisco 9K switches. So in future, if you want to migrate to DNA, you have some sort of switches where those are supporting DNA. That's a strategy nowadays all the company are using. So they are not ordering for the legacy or the old hardware, rather than they are going for the new hardware. So in future, if they want to migrate, they can use that as strategy. Again, as per design perspective, here you can see that you may have layer 3 distribution interconnection, or you may have layer 2 distribution interconnection, means you want to stretch the boundary up to distribution layer. So this red color wire that you're seeing here, those are L3, and this bluish color connection that you are seeing, those are L2 domain. And that's why it is telling that what you want layer 2 access. So obviously in the bottom, in the access switch, you have the VLANs. You want to do inter VLAN routing. You have the obviously by default the STP will be running there. You have the HSRP or GLBP. You want some ether channel, you have some BPD guard, etc., etc. So all type of prevention you have. Some of the companies they are using layer 2 boundary up to the distribution layer. So here you can see the difference. Let me quickly show you the difference. So you have layer 3, this red color link in between the distribution switches. They are using a routing protocol to forward the traffic, and that's true actually. If you see any of the upcoming network or any of the SDN solution, you'll find that even for layer 2 carrier or even for layer 2 also, we are using routing. So what does it mean? So for example, if you go and check Cisco ACI, application centric infrastructure, where you have leaf and a spine, they are connected behind the scene, but they are using layer 2 type of routing strategy. Means MAC addresses also can route, that you can check. Well, that's true, uh, that the routing is better than that we are doing in terms of switching for high available network or for a scalability reason, and that is again one of the design aspect we have. So suppose if you have two different fabric, a stretch fabric, you don't want to extend the L2, although you can extend the L2, but routing is always preferred uh, on top of the L2 tunnel. So for example, the L2 tunnel is not preferred over L3 routing tunnel. All right. In short, routing is preferred design rather than stretching the L2. This is also supported model. This is not for the reason that we are talking that L2 is supported model or L3 is supported model. This is something that which is giving the capability of, say, for example, VSS, virtual switching system. So uh, there are parallel enhancement in the network. Suppose if we have switches, if we connect, obviously you know that as per their priority and MAC address, they will choose who is the root switch, who is the secondary switch, etc., etc., all priority and everything. Now, what you can do in this case, that you don't want these triangles in a network. What you want straight line. So you collapse these two switches inside one unit, and then the bottom switches also, they can think. So this diagram will be like this, or maybe this diagram will be like this. Means two switches, they are connected back to back. Physically they can be like this, but logically they will be like this. That's the overall idea if you are using this type of technology. And then that's the evolution you have. If you see the data center evolution, you'll find that it started with 6500, then it moves to Nexus 7K, then Nexus 9K, and then now Nexus 9K CI. So started with normal, this type of network, then moved to, for example, VSS, then moved to VPC, then moved to leaf and spine, and then leaf to spine ACI. Okay, so evolution is there. Up to you which network or which type of a standard network or design you're supporting. You will find this type of network as well. You'll find this type of network as well. Both are supported in an existing model we have at this point of time. So you can have these devices in same unit, these distribution devices. So you have, for example, one control and two data channel, and these devices, they are working as a MEC, like multi-chassis Ethernet, etc. Means you are eliminating the L2 loop rather than you have a straight line in the network. All right, so this session is actually becoming lengthier. Let me stop here, and next section will continue from here. Let us continue the previous section, and we have seen that we have option that we can use L3 distribution link, or we can use L2 as a distribution link in between that. If we are using L2 capability, we have option that we can go and use virtual switching system, where we want to reduce the number of triangles in a network. Now here you can see the convergence time with respect to RSPBST or RPBST plus, then the routing protocol like OSPF and EIGRP. And that's the thing that we are considering, that when we are using the routing protocols, their convergence is faster. They are not using the blocking interfaces, like if you are using L2 interface, then STP will run automatically and 50% of link will be unutilized. So those things are not there. That's why always this routing design will be preferred with the switching design or L2 design. How it will be looking like inside the DNA? that we are going to discuss in the upcoming session. But if you see this diagram, from this diagram, let me try to explain a few of the things. So here you can see that you have border router. So for example, BRBR, then you have edge devices. Maybe they can do switching and routing both. So you have the edge devices as well. Now, with the use of these edge devices and plus this APs that you are seeing here, that they are near to the end point. So now these routers or now these edge devices, they are not learning the entire routing table, entire topology table, not everything, but they are knowing that what is connected to them, and then they are sending those information to MSMR. So we have this resolver, or we have the servers where they are pointed to, or they are sending all the information to the global routing table. Like that, you can think. You have one DNS, and that DNS having the information from where to where I have to reach. So those all information that DNA has or having. Then you have the access point that you can see, and then you have the WLC, that all the access point control information, or all the access point, those are managed via the WLC. We are going to discuss this also. So we have the underlay architecture or infra, we have the overlay architecture and infra, and this underlay and overlay in conjunction, they are working for SD access. Here you can see that the ID challenge new services, you have the mobility services, scalability, flexible and programming infrastructure. Those are the things that you'll find inside DNA or SD access. We have the controller, we have the control plane, and this thing we have discussed. We have the policy plane, that is the ICE identity services. With help of control plane and policy plane, or with help of the DNAC plus policy plane, we are going to manage the DNA fabric or DNA center. So you have the endpoints, and the way that these endpoints are thinking now, they have offloaded the load that we have in the existing campus area network, or in existing enterprise campus area network. Correct? So these are the things that is going to be new thing, or these are the new innovations we have from the existing campus area network. So now if you see this existing network, and again you can go and refer this MPLS WAN technology design guide, you will get a nice document from Cisco. Now if I go here and highlight you certain things, so here you can see that you have your core, then you have your campus area network where you have the distribution switch. You may have one building with one switch, other building with one switch where you have connected the access point. Here you can see you may have one floor where you have much more number of users. So then you have the endpoint, IP phones, you have wireless access points, and you have roaming users, etc. So you have the access layer endpoints, maybe you have IoT devices as well in the existing network as well. Then you have the distribution, and then you have the core switch. Now here you can see that your core switch, one portion is going towards the WAN, and maybe this is my data center or main location. One portion it is showing that it is going to data center. So you have the Nexus switches where the core switches are connected, and then you have Nexus 5K, then you have MDS and your storage network and your application servers, etc. So you have your data center. Here you can see that you may have CE to PE. So suppose this is your CE, customer is, here you have PE, somewhere you have the MPLS backbone, that you have the P devices, so PE and P devices. So here also you can see that your core switch is connected with the core router, and then it is going to be terminated to the WAN. Here you can see that you have the VPN endpoints for the remote users, or suppose if you are using DIA or maybe DCA, direct internet access or direct cloud access, then your traffic is going via the firewall to the internet where you have IPsec tunnel for the remote users, or maybe those users who are connecting with IPsec. So either teleworker, mobile worker, or the remote user. So maybe in few of the branches they are using internet and the WAN, both means they are using the hybrid type of branch, or they are the hybrid type of branch, or maybe we have the dedicated MPLS type of branch. So that's the reason everything is shown in this particular diagram, and this is one of the validated campus area network. In this particular curriculum, you will not study this data center portion, but you should know each and everything that is showing here in this diagram with new format, with SDN format. And that's the overall goal with the CCNP Enterprise Network, that you should know the DNA and SD-WAN, but you should know the core as well. Again, the same thing here. You can see that how the core distribution, and then again you're going towards dual MPLS or dual carrier. Maybe you're going towards layer 2 WAN. Maybe you have some internet and you're creating IPsec tunnel, and then you're going to the internet. Okay, so all the summary routes, they are coming and collected to the WAN distribution layer, and then it is going to the core. Now this slide is also very important, and this is equally important for SD-WAN as well. So whenever you are doing the migration or the new SD-WAN deployment, at that time you have to mark the site. So you may have sites, say for example, gold, silver, you can mark it. It's just the name, and maybe bronze. Now gold means that you are using uh, uh, say for example, you have dual devices and dual ISP, that is your core, this type, or maybe this type, that is your high available network. Silver may be that you have only one device but you have two ISP link, either two MPLS or maybe one MPLS, one internet, or dual internet, correct? And bronze means that you have one device, one connection, one device, one connection. So as per the type of branch, you can categorize the branches or branch type, and then you can create the templates, and then you have to push the templates, or you can create the configuration and then you have to manage them. So for that, you should understand that what type of remote branches will be there. Now, once you identify your remote branch, that one part of this course, the other thing that you should know, that what is behind that, correct? So once you know that the WAN part, you should know the LAN part, and then that will become the enterprise network, correct? So for that reason, you may have multiple options, but I'm going to show you that a few of the examples. So maybe you have shared LAN, maybe you have L3 connection with the switches that is behind this edge devices, or maybe you are using some sort of highly available and redundant design, or maybe ether channel, multi-chassis, or stack of switch. Actually, this is the recommended way. And suppose if your WAN is your internet, so obviously you have to put the firewall as well in between that, correct? So these are the design options we have. The last recording and this recording, actually it's very important. You can, I'm going to upload this document so you can have the reference, whatever have discussed in the previous section and this section, and these, actually these sessions, these slides, these recordings are the fundamental of how we are going to design what is in the existing, what is going to come in the DNA and SD-WAN. Inside 1.1b, we have to understand or discuss about the high availability techniques such as FHRP and SSL. So let's discuss one by one. FHRP is nothing but first hop redundancy protocol and how it is working and what are the flavors you have. You can see that we have HSRP, that is the hot standby redundancy protocol. Then we have VRRP, that is Virtual Routing Redundancy Protocol, and then we have the Gateway Load Balancing Protocol. Now, VRRP is the industry standard. This HSRP and GLBP are Cisco proprietary. Mostly, we are using VRRP. This VRRP and HSRP both are very much similar, but this GLBP is different, and we can discuss that how different this gateway load balancing protocol is. Basically, what is happening in all these gateway first hop redundancy protocol or gateway load balancing protocols are that, say, these, suppose if we have two routers or maybe switch, and these switch, they have the common interface going towards the LAN, and suppose you have one PC here. Now this PC can have gateway here or can have gateway here, but the common term here is, or the technology here is, that we are not giving gateway, say for example dot 1 or dot 2 for this particular IP who is dot 10. Rather, we are giving the gateway to some virtual IP, and that is glued with this device and this physical device. So what is the benefit? The benefit is that, for example, this particular device or router, so for example, this is router A, this is router B, he is working as an active member and B is working as a standby. So that means that packet is forwarding in this direction, and suppose if the link going towards the WAN or going towards outward is down, or the device is down, automatically the packet get gateway from this direction. Okay, so that's the term, and that's the mechanism, some sort of high availability mechanism, we can say, that if one of the device is down, or maybe if the link that you are tracking is down, you can go from other direction. Again, if this device will come back online and you have set some prompt, then again the traffic will go in this direction. Okay, so that's the thing that we are using with VRRP and HSRP. GLBP is bit different, because now if you see these terms or technology, you'll find, oh, so is it like a spanning tree or something, that all the time one of the member is active and other is working as a standby, means 50% of the resource utilization we are doing? The answer is not exactly what we can do. So for example, for certain VLAN 10, 20, for example 30 and 40, if I have these four VLAN, for VLAN 10 and 20, as per high priority, here higher is better, you can set priority 200 towards router number A. So suppose this is router A and this is router number B. This A is for active, is for standby. A and B is the name of the routers. So for 10 and 20, he is the active member, and so for example 30 and 40, this B is the active member. So that means that they are using some sort of active mechanism to send the traffic, and obviously you have different virtual IP for all these different subnets. This way, in case of HSRP and VRRP, you can achieve active type of load balancing. GLBP is a bit different, that is doing the load balancing by default. So let me show you this in the diagram. You can see that when you have the distribution layer, here you can see that you have the first hop redundancy protocol. You can go and use first hop redundancy protocol. So used to provide a resilient default gateway. These are the technologies. They are providing millisecond of convergence time, means if one of the active memories fail, it can go to the standby or the backup. BRRP, if you need multi-vendor interoperability. VRRP is nothing but the industry standard that we have already discussed. GLBP facilitates uplink load balancing, and the name itself is Gateway Load Balancing Protocol. Preempt is there to avoid the backhauling of the traffic. Means preempt is something that if your device will go down and if it will come back up, again it will become the primary member of the active member. Okay. Now here you can see that how they are working. So they have these devices, they have their IP, they have their MAC, then they have their virtual IP, they have their virtual MAC. Now this virtual IP is shared, so you can think as you have some ghost router in between, and that is glued with these two devices. So when the traffic is coming, here you can see, and if he is the active, the traffic will forward it in this direction. Okay, so traffic will come, it is going in this direction because he is the active guy as per the priority. And here you can see the example for all the IP, the MAC, the gateway. Gateway is the virtual IP, and the ARP entry. Now this is the standby or active and backup. If this will go down, obviously it will reroute it to the other direction that we have discussed. That's the mechanism, 100% same with HSRP and VRRP. Uh, but if you go and check the VRRP methodology used in SD-WAN, that you can go and refer the SD-WAN course, you'll find that there is customized VRRP inside SD-WAN where we are tracking the OMP, we are tracking the prefixes. So track OMP, track prefix. Rather than here, if you want to track the interface, you have this option that you can go and track the interfaces as well. So what I'm telling that, suppose if you have WAN and you want to track this interface, you can track it. Suppose if this will go down and its priority is 200, its priority is 150, automatically you track the interface and decrement the priority. So this priority at the moment the link is down, this will become 200 minus 100 means 100. Now 150 is higher, so traffic will go in this direction. So that's the tracking thing we have. And again, the preemption option we have, you can preempt it. So if the device is down, the traffic will go in this direction. When it will come back up, then again it will go from the primary member, from the active member. Same thing we have in the VRRP, so that's why I'm not discussing here. Same methodology we have, because VRRP is open for all the vendors. It's a multi-vendor support. Rest of the things are almost the same. Now, next we have the GLBP. So let's quickly discuss about GLBP. GLBP is doing some sort of gateway load balancing. So here you can see this IP, MAC, virtual IP, and virtual MAC. Now you have virtual MAC here, and here you have two different virtual MAC. So what will happen that sometime traffic will go in this direction and sometime traffic will go in this direction. That's why you can see that both the direction we have the traffic flow. Although I haven't seen much of the customer using this methodology due to some internal load balancing issues related to MAC addresses. But yeah, we have this option that we can go and use the GLBP as well. So where we don't have to group the VLANs that we have discussed earlier. So you don't need to group the VLANs, but they will do the load balancing at their own level. So they can do their MAC address based load balancing. And here you can see that how some of the traffic is going via B, some of the traffic is going via A. One is the active virtual gateway, one is the active virtual forwarder, like that. Okay, so this methodology that they are doing the MAC based load balancing, this methodology you can create some sort of VLAN based load balancing. So some traffic will go via the gateway 1, some traffic will go via the gateway 2, and as a whole unit they are working as a active load balancer. All right, so let's just stop here. Let us continue the previous section and discuss about the other high availability features that we have. So we have SSO, that is the stateful switch over, and how it is helping to provide high availability in the campus architecture design that we are going to discuss. Now here you can see that we have two different type of network design. We have layer 2, layer 3 topology. We have multi-tier layer 3 topology. Here you can see that this blue interfaces or this blue lines are a layer 2 interface, and then this red one, red color connectivity lines are L3 interfaces. Here in this diagram you have L2 plus L3 link. Here in this diagram you have everywhere the L3 link. So either it's L2 L3 topology or complete L3 topology, we have option to do SSO. We can do stateful switchover. Now, what does it mean and why this is important? You can see here that you have two use cases for this. Either you have a big catalyst chassis box where you have active and a standby supervisor engine, or you have a stack of switch. Now suppose if you want to upgrade the image but you don't want to take the maintenance window. So you don't want to tear down, or you don't want to stop the production traffic, and then you want to upgrade the image. That's the one of the use case with we have with the SSO. In that case, we can go and achieve this target with help of SSO. Now, when we are using SSO, there is one problem that uh, suppose you are doing iOS upgrade and you have this SSO feature enable. You have active supervisor engine, you have a standby supervisor engine. The problem here is that if you do the switch over, that will not be a stateful. Now to do this a stateful switch over, you should have the common database between the active soup and the standby soup. Here in the diagram you can see clearly that their active and their standby supervisor engine, they haven't synced their routing database. So particularly with respect to routing database, they are not doing the stateful switchover until unless you go there and enable one of the feature that is nothing but NFS, non-forwarding, non-stop forwarding. So here you can see that if you go to these protocol like OSPF, BGP, etc., and you have to enable the feature called non-stop forwarding, NSF. And for that, you should go and check the dataset that which particular version or hardware or model that is supporting NSF, non-stop forwarding, which is not supporting. Okay. Apart from that, it's okay that we have this SSO. We can go and use SSO with NSF, and then they will do the stateful switchover. That's the one very important point we have. The other point is that suppose if you are using ISSU, that in-service software upgrade. Now in that case also, you should know that which particular supervisor engine, which particular image, what is the hardware platform that you want to upgrade. Suppose if you want to do the major upgrades, so for example 6.0 to 7.0, it is recommended from Cisco TAC or Cisco that you do not do in-service upgrade, or you do not do inline upgrade. Rather than you take complete uh, maintenance window, take complete downtime, and then you do the major upgrade. Now these SSO and these ISSU or uh, these fast upgrades, whatever we have, uh, for these upgrades we can go and use this SSO, and it is quite a bit handy. Okay, so that's the feature we have with the SSO. All right, so let's stop here. We have completed 1.1 and now we are inside 1.2. In 1.2, the topics are that what is the principle for wireless LAN deployment, the wireless LAN deployment, and the services involved inside that. So let's first try to understand the design and deployment option for the WLAN or wireless LAN. We have controller based architecture, we have mobility architecture, how it works. So here you can see that what components we have. Components we have the wireless LAN controller, we have the access points, and actually if you compare these technology with the SD-WAN, so we know that we have the evolution of SDN technology or SD-WAN or any type of SDN, SD-LAN or ACI. Now in that, what are the things we have? We have something called control plane and we have the data plane. Now, if you think WLC, wireless LAN controller, as a control plane, you can think access point as endpoint devices. They are working as a data plane. Means these access points they are dependent upon their control plane or the controllers. Then you have the management plane. You can use Prime Cisco Prime infrastructure, or you can use Epic EM or DNAC DNS Center. We have the mobility service engines as well, MSE. So here you can see that you have the access point and they have to join. First of all, they are forming some sort of CAP WAP tunnel, and that is the industry standard nowadays with the control plane. So you can think that the data plane, they will join with the control plane. The data plane is nothing but the AP. The control plane is nothing but the WLC, and then they are working accordingly. So once they join, then they are getting the configuration pushed, kicked from the controllers, and then they are up and running, or they are ready to run. Now, when we are talking about the centralized wireless LAN architecture, here you can see that you have your access point and they may be spread across the geographical location. You have the controller. Now you have to think, or you have to check actually the data sheet, that how many access point that a particular controller can hold, and according to that you have to go and check the capability of the controllers, and actually when you are designing the network, how many access point and how many users you have. So those capacity planning we have to do. All right, so here you can see that in this design that you have the cap wap tunnel, and this cap wap tunnel, that is the industry standard. It can be for control plane. So here you can see that when they are forming the control plane, they have the DTLS tunnel. Even in the SD-WAN also, when we have the vSmart as a control plane, and we have the vEdge or edge devices as a data plane, they are forming some sort of DTLS or TLS tunnel in between to send and receive their OMP traffic or the control plane traffic. For data plane, they have the DTLS, that's the optional. But for data plane, we know that in SD-WAN we have IPsec tunnel in between that. So there it is different, but most of the things means logically, if you try to analyze, you'll find that yeah, WLC is a old technology, means wireless LAN control is quite a bit old in the market now. SD-WAN is also become older, but they have introduced this control plane and data plane feature long time ago. Even if you go and check the catalyst switch where you have the supervisor engines, so supervisor engines and the line card, so you have the soup engine and then you have the line card, they are also very much have the concept of control plane and data plane. So this control plane and data plane feature is not something that is 100% new in SD-WAN, but somewhere they got inspiration and then we are working inside the SDN. So now we have the CAP WAP tunnel, and one note is that CAP WAP is not supported on the layer 2 mode. Okay, so this is the thing, and let us continue. Here you have one graph where you can understand that your AP access point will boot. They will discover the wireless LAN controller. They will form the control connection that TTLS will set up. They will join the WLC. If you want, you can reset as well. They can check, WLC can check the image as well. From WLC, they can push the configuration and they are up and running. They are ready to run, correct? Again, very much similar to the SD-WAN steps. They are using the plug and play feature as well. The SD-WAN is also using either plug and play in case of C-Edge, that is the ISR devices, and they can use ZTP, zero touch provisioning, in case of V-Edge. All these things are explained with the lab in the SD-WAN course, so you can refer that. Now let's see and compare the plug and play option or feature here. Why we want plug and play? You want plug and play that, so for example, in remote sites, you don't have uh, the IT management staff. So what you can do, simply someone at the remote location, they can connect the interface and that's it. Once they connect the interface, rest each and everything can be done remotely. So they can reduce the cost, they can reduce the complexity. You have the high level of security. Why? Because you are forming the DTLS tunnel with the controllers and the time and productivity. So that's the reason actually we need or this plug and play or this ZTP are very popular nowadays. So you have IT staff sitting somewhere in some location and he can manage n number of sites with the feature of PNP. How this PNP process is working, here you can see that obviously they have to resolve the DNS, they have to get the IP via DHCP, then they try to initiate the traffic, they try to build a web tunnel with the WLC, that's a discover phase. Then they can go and check cloud related features. Actually, what is happening in this at this point of time, that while they are discovering the AP, they should they have to form the DTLS tunnel, and for that DTLS tunnel, there are chances that you have your in-premises certificate or you are using some other cloud-hosted certification features. So cloud redirection will happen for these APs, and then finally they can go and join. These steps are very much similar in the ZTP process or PNP process in Cisco SD-WAN as well. So you can go and compare these two features. What you can do, that you can check the PNP process for the AP, and then you can go and search over Google the PNP process for SD-WAN or the ZTP process of SD-WAN. You'll find the steps will be similar. Obviously, the way that we are doing is different, but overall the steps are very much similar. So what will happen here, here you can see the summary slide we have, that AP will boot, it will discover the WLC, they will form the DTLS channel, they will join the WLC, and then WLC will push the configuration, and then the AP will be up and running. Now here you can see that now you have the three different tier. You have the management plane, either you are using prime infrastructure or DNAC, and that is solved or resolved inside DNS Center. Then you have the control plane, that is nothing but WLC, and then you have the data plane, that is nothing but the access point. These access point can sit anywhere remotely, and you are using the feature called plug and play. So from the prime infrastructure, you are using WLC to the methodology is plug and play to install all the remotely hosted access points to reduce the complexity, to reduce or to enhance the productivity as well. Okay, so let's stop here. Let us continue our discussion. We have the controller-based architecture and the mobility-based architecture. Now this term mobility and the roaming both are different. Mobility means you are providing the mobile features. Roaming means the user can roam from one place to other place. He can associate and de-associate with a different type of access point. I can show you the diagram here. You can see this user, this laptop that you're seeing here. It can associate and de-associate with different access points, and that's the feature roaming. Mobility is providing you that capability that you can roam. Now the next important thing we have is to understand that what are the WLC or which type of WLC is there and what is the capability. Again, you can go and refer this Cisco dataset. There you will get much more information about the capabilities, features of the WLC. So for example, we have the Mobility Express who can support 52,000, 50 APs, 1000 clients, 100 AP, 2000 clients in these series. As you can see, they are supporting up to 100 AP. Then we have mid-size enterprise level WLC, say 3500, Cisco 5520 series. There you can see that how many APs, clients, and what is the overall throughput. How many is APs client and what is the overall throughput for this 5520. And for the large enterprise, we have 8540 WLC that can support 6000 AP. Even the rake unit, you can see it's bigger. So this WLC, that is 5520, is one RU, one rake unit. This 8540 has the highest stability, scalability, for redundancy and scalability. Stability is again the different thing. Scalability is different thing. Higher availability and redundancy is again the different thing. So we can achieve all those targets, but this 8540 has the highest scalability, means it can support up to 6K, 6000 access points, 64000 clients, 64K clients. The deployment models, we have centralized, Flex Connect, and Mesh. More and much information related to this WLC and their operations and all, you will get inside CCNP WLC course. There is separate CCNP course for wireless LAN controller, or we can say that for wireless. Not only for LAN controller, but for complete wireless, we have separate course as well. But here also you will get the core knowledge, means what is AP, what is WLC, their association, de-associations, and their design related stuffs as well. So now when you are grouping the mobility engines, when you are grouping the mobility devices, here you can see that you can go and group this mobility devices. The mobility group name is a mobility group everywhere. They have their own MAC address, say 1 for this mobility device or the controller, then 2 for this controller, and then 3 for this controller. So that means his neighbor is 2 and 3. So 1 has neighbor 2, 3, 2 has neighbor 1, 3, 3 has neighbor 1, 2. And now this client, if you check this client, he is roaming from one place to other place, and because all these controllers, they are part of one mobility group and they have their own DTLS channel in between them. So for any user perspective, they don't have much issue to roam from one place to other place. Obviously, behind the scene, they are doing this control plane and data plane message exchange. So we have the cap wrap tunnel and we have the join. We have all those things that we have discussed initially, and then they can associate and dissociate the SSID or the access point. Now again, you can see that you can go and group the mobility group. So if you want 24 WLC and 72 WLC inside the mobility group, you can go and group them. You should go and check the mobility group, say for example 8.0, 8.2 and 8.3. Even if you go and check the latest data sheet, you will find some new addition, some new revisions. So according to that, we can go and design our mobility groups. Okay, so let's stop here. Let us continue and discuss the best practices. We should do the RF planning. We should do the RF optimization, means we should categorize the data, voice, video, traffic, and location and client density. We should have the optimized gig Wi-Fi as a primary and gig Ethernet as a fallback. We should have high redundancy, and we'll see in the upcoming slide that what does it mean by SSO in terms of client, AP, and WLC. And then we have AVC, application visibility control. That means for mission critical traffic or application, how you are categorizing the application, correct? So you are giving priority to one traffic over other. And that's why we have actually AVC. They can recognize the application with the metadata, and then obviously we can put the rule for that. Now here you can see that we have three SSO. We have client SSO. That means that if in case of any type of failover, the client state remain active. There is no problem with the active client state, in other words. Then we have the APSSO, means suppose if you are failovering from one active WLC to other, still your AP, they don't have disruption. They have stateful switchover. And finally, you have the cluster of WLC. So one is primary, one is backup, standby, etc. Like that, you have the redundancy in terms of WLC as well. So here you can see that box 1 to 1 means 1 to 1 availability. One is in active state and other is hot standby. I will show you that you can connect this via dedicated link in the upcoming slide. Let me quickly show you this. Here you can see that you have the redundant port in between two WLCs. Here you can see the redundant port in between two WLC. Correct? So like that, if client sessions are active, those are client SSO. If AP sessions are active in case of failover, those are AP SSO. There is timing in between that. So suppose AAP, which has joined the WLC, and then he is actively tracking the active WLC. Suppose this active is gone, then he will send some probe and he'll wait. He will not get any response from the active. That means he will go and work with the standby. Okay, and it's a very normal situation you have. Say for example, here you can see that downtime during failover reduced to 5 to 1000 millisecond depending upon failover. In case of power failure on active WLC, it may take 350 to 500 millisecond. In case of network failure, it can take up to few seconds. And we have the SSO support for these models: 3504, 5500, 7500, 8500, and Wisdom 2. You can group these WLC, how you can make primary, secondary, and tertiary part of one group. For that, you can go to the high availability section. There you can see that you have the backup primary controller IP, backup primary controller name, because everything we are going to do via the GUI. So it's actually very easy to create the or have the redundancy from the main or the active configuration GUI dashboard. And here you can see that you have the redundant port that you can go and connect these redundant port for SSO. And again, we have 13504 pairing device. So pair of devices, here you can see you have two devices, and you can see the RP ports where you can go and pair or make this as a part of redundancy. All right, so these are the things related to redundancy of WLC. I hope you understand up to this point, because next section again we have some summary slides, 2-3 summary slides, and then we'll move to other section. So let's stop here. In 1.3, we have to understand the on-prem versus the over-the-cloud deployment. And actually nowadays it's a very popular term that you have something on-prem, you have something over the cloud, or you have mix of both. So you are using on-prem and then you are using multiple cloud. Now we have three main players at this point of time when we are talking about the cloud service provider. We have Amazon, one of the major stakeholder for cloud services. We have Azure from Microsoft, and then we have Google as well. Google is also gaining popularity, and then they have done a huge investment in the cloud domain. Now let's just start this section and try to understand that how these terms fit together when we are talking about on-prem and over the cloud deployment. So when we are talking about hybrid cloud networking, here you can see that means that you have on-prem and you have a single public cloud provider. When we are talking about multi-cloud networking, then you have on-prem and you have multiple cloud providers, correct? Now, what type of terms we are going to use? Um, Overall, if you see that how the technology fits in, actually it is simple, and that's the reason that AWS and other cloud service provider, they have gained their popularity. So it's simple to implement, and it's very easy to use, and it's highly available. So these are the key pillars upon which these services depends upon. Now, for example, I'll skip this slide. I'll come back to this slide. So for example, I'll show you an example here. So now I have my private network, and inside that private network, I have one virtual router or maybe physical router. This router, I am creating gateway with Google VPN. It may be AWS gateway, it may be Azure gateway. Everywhere you have same type of feature and capability. Maybe the name and the terminologies will get changed. So then you can see that I can reach to the Google Cloud router, and this can work as a gateway for the application that is hosting behind this router. Correct? So you have multiple application hosted here, and those application have gateway as a cloud router. Then I have the VPN connectivity in between public and the private cloud, and then maybe I have a user hosted behind this private network. Okay, so this way actually the flow will work for all the cloud providers. So let's try to understand these terms. So obviously you want to create the IPsec or IKE version 2 or IKE version 2, 1 and 2. So I think 2 and 2 twice, but yeah, you have option. Some of the cloud provider, they are supporting version 1, some of them are supporting version 2. You have SSL, you have PKI infrastructure. Then routing, it is supporting a static BGP, OSPF, EIGRP as a IGP. So you have to redistribute IGP to BGP. BGP is one of the standard protocol, and BGP is used everywhere. We have the tunneling methodology as well, like IPsec tunnel mode, GRE, MGRE, MPLS, etc. So bottom line is that whatever things that we have learned in Cisco, whatever technology that we have learned in Cisco, the same way these cloud provider, they also uh, programmed, or in the same way they have written their code, so they can connect either with Cisco or Juniper or any third party or any networking domain companies, correct? Because any of the companies, they can use the cloud hosted applications, not only Cisco, correct? All right, so these are the terms that are going to be used, and when you create the tunnel in between your private and the public cloud, obviously you have the VPN gateway one place, you have the VPN gateway at the cloud side, and then you can form the tunnel. For routing purpose, you have BGP who can take all the routes from one place to other place. If you want to learn more about this Google, GCP, AWS, and Azure, so these are the links that you can go and verify. Now, why we are using multi-cloud or multiple cloud? Because obviously different, if you are use different vendors, so they have their own availability. If one of the vendor go down, is still the other vendor is up and running. So the reason is high availability. We have all these actually cloud providers, they have some unique features in them, so we can use one feature from one cloud provider, other main core feature from other cloud provider, and we can mix and match our requirement as a customer, correct? And then per project service requirement, again this depends upon the service. Now when we are extending the private network to the public domain or private cloud, say for example at this point of time to the public cloud, then Cisco has their cloud service router, and obviously they have the compute requirement, so they have the route process, and along with other services it can be installed over ESXi. Here you can see the list of the minimum requirement. So for example, performance elasticity, available licenses, we have 10 Mbps to 10 Gbps. We have the CPU footprint, one virtual CPU to 8 virtual CPU, and the licenses. So you can install the CSR over any of these compute. Once you install this, then you can form the tunnel from your private to the public network. And here you have the list of all the dashboard of different type of cloud provider. Most of the cloud provider trainings are having very less cost, or it's free. You can create your, at least you can create the account over any of these cloud provider, and you can go and check the features. So for example, I can go and open Amazon aws.amazon.com. I'll get the dashboard, and from that dashboard I can go and check n number of features they are providing. So you want to do compute, you want to do networking, security, storage, there are n number of things. All different cloud vendors are providing. Now, how this topology look like? Again, private network extending to public network. I'm using BGP as an overlay protocol. I have tunnel in between my private network to public network, obviously for security sake. And then even you can see that I can redistribute IGP over eBGP. BGP will carry those prefixes till the Google Cloud, and then it will reach to the gateway router, and then it will reach to the applications. Correct. Now, in case of physical routers, that capability is also there. So I can create the IPsec tunnel between the physical router to the Google VPN, and then it will reach to the Google router. And then same way, they can exchange the routes as well. All right, so let's just stop here, and in next section we'll continue from here. In 1.3, we have to understand the on-prem versus the over-the-cloud deployment. And actually nowadays it's a very popular term that you have something on-prem, you have something over the cloud, or you have mix of both. So you are using on-prem and then you are using multiple cloud. Now we have three main players at this point of time when we are talking about the cloud service provider. We have Amazon, one of the major stakeholder for cloud services. We have Azure from Microsoft, and then we have Google as well. Google is also gaining popularity, and then they have done a huge investment in the cloud domain. Now, let's just start this section and try to understand that how these terms fit together when we are talking about on-prem and over the cloud deployment. So when we are talking about hybrid cloud networking, here you can see, that means that you have on-prem and you have a single public cloud provider. When we are talking about multi-cloud networking, then you have on-prem and you have multiple cloud providers. Correct? Now, what type of terms we are going to use? Overall, if you see that how the technology fits in, actually it is simple, and that's the reason that AWS and other cloud service provider, they have gained their popularity. So it's simple to implement, and it's very easy to use, and it's highly available. So these are the key pillars upon which these services depends upon. Now, for example, I'll skip this slide. I'll come back to this slide. So for example, I'll show you an example here. So now I have my private network, and inside that private network, I have one virtual router or maybe physical router. This router, I am creating gateway with Google VPN. It may be AWS gateway, it may be Azure gateway. Everywhere you have same type of feature and capability. Maybe the name and the terminologies will get changed. So then you can see that I can reach to the Google Cloud router, and this can work as a gateway for the application that is hosting behind this router. Correct? So you have multiple application hosted here, and those application have gateway as a cloud router. Then I have the VPN connectivity in between public and the private cloud, and then maybe I have a user hosted behind this private network. Okay, so this way actually the flow will work for all the cloud providers. So let's try to understand these terms. So obviously you want to create the IPsec or IKE version 2 or IKE version 2, 1 and 2. So I think 2 and 2 twice, but yeah, you have option. Some of the cloud provider, they are supporting version 1, some of them are supporting version 2. You have SSL, you have PKI infrastructure. Then routing, it is supporting a static BGP, OSPF, EIGRP as a IGP. So you have to redistribute IGP to BGP. BGP is one of the standard protocol, and BGP is used everywhere. We have the tunneling methodology as well, like IPsec tunnel mode, GRE, MGRE, MPLS, etc. So bottom line is that whatever things that we have learned in Cisco, whatever technology that we have learned in Cisco, the same way these cloud provider, they also uh, programmed, or in the same way they have written their code, so they can connect either with Cisco or Juniper or any third party or any networking domain companies, correct? Because any of the companies, they can use the cloud hosted applications, not only Cisco, correct? All right, so these are the terms that are going to be used, and when you create the tunnel in between your private and the public cloud, obviously you have the VPN gateway one place, you have the VPN gateway at the cloud side, and then you can form the tunnel. For routing purpose, you have BGP who can take all the routes from one place to other place. If you want to learn more about this, Google, GCP, AWS, and Azure. So these are the links that you can go and verify. Now, why we are using multi-cloud or multiple cloud? Because obviously different, if you are use different vendors, so they have their own availability. If one of the vendor go down, is still the other vendor is up and running. So the reason is high availability. We have all these actually cloud providers, they have some unique features in them, so we can use one feature from one cloud provider, other main core feature from other cloud provider, and we can mix and match our requirement as a customer, correct? And then per project service requirement, again this depends upon the service. Now when we are extending the private network to the public domain or private cloud, say for example at this point of time to the public cloud, then Cisco has their cloud service router, and obviously they have the compute requirement, so they have the route process, and along with other services it can be installed over ESXi. Here you can see the list of the minimum requirement. So for example, performance elasticity, available licenses, we have 10 Mbps to 10 Gbps. We have the CPU footprint, 1 virtual CPU to 8 virtual CPU, and the licenses. So you can install the CSR over any of these compute. Once you install this, then you can form the tunnel from your private to the public network. And here you have the list of all the dashboard of different type of cloud provider. Most of the cloud provider trainings are having very less cost, or it's free. You can create your, at least you can create the account over any of these cloud provider, and you can go and check the features. So for example, I can go and open Amazon, aws.amazon.com. I'll get the dashboard, and from that dashboard I can go and check n number of features they are providing. So you want to do compute, you want to do networking, security, storage, there are n number of things, all different cloud vendors are providing. Now how this topology look like? Again, private network extending to public network. I'm using BGP as an overlay protocol. I have tunnel in between my private network to public network, obviously for security sake. And then even you can see that I can redistribute IGP over eBGP. BGP will carry those prefixes till the Google Cloud, and then it will reach to the gateway router, and then it will reach to the applications. Correct. Now, in case of physical routers, that capability is also there. So I can create the IPsec tunnel between the physical router to the Google VPN, and then it will reach to the Google router, and then same way they can exchange the routes as well. All right, so let's just stop here, and next section will continue from here. Let us continue our discussion and add more complexity into the design. So now we know that we can have the interconnectivity between the private network and the public network. So here you can see that your private network, you are creating IPsec tunnel. You have the IPsec IKE version 2 tunnel mode. You create a tunnel up to these VPN gateways, and these you're reaching up to these routers. These routers are actually the gateway for these virtual private cloud. These are some of the compute thing where you have hosted your applications. So these application having these gateways, and from here it is reaching to this point, and here you may have your user. Okay, so this is one of the deployment model, but we have others as well. So let's see that how DMVPN is taking role in this. Before coming to DMVPN, here you can see in the diagram that you may have interconnectivity in between clouds. So here you can see that from AWS cloud to Google Cloud, I have this VPN tunnel, and then these maybe you have the users here and you have servers here, etc., etc. There may be chances, but these compute network can communicate across the cloud as well. Now, if you want to make this arrangement a little more automated and much more meaningful, then Cisco has given the solution. We can integrate with DMVPN, dynamic multi-point VPN. Now this dynamic multi-point VPN or DMVPN, what you can do, that you can define the hub, and then you have the spokes. So here you can see you have the spokes. So this will work as a hub and a spoke methodology, and depending upon which particular phase of DMVPN you are using, it may be hub and a spoke, it may be a spoke and a spoke as well. If we are using, I think, DMVPN phase 3. Again, if you want to add much more redundancy as per your design requirement, still we have the option that we can add primary and secondary hub, and then we have the spoke. So now you can see that we have the redundancy in terms of spokes, or even for few of the spoke he is primary, for few of the spoke he is the primary. Like that we can do some sort of load balancing as well, and this will give us the perfect design related option. Same thing here, you can see that for one of the cloud he is, or the first router is the gateway. For other cloud, the other router is the gateway, but they are working as a primary and secondary. Now at this point of time you may be thinking that then what is the role of SD-WAN when we are integrating our existing WAN with the cloud? Now role here is that you should go at this point of time and can search SD-WAN infra as a service. In that case, even this is much more automated. You can go to vManage. You can have your images. Obviously, you need the images to spin up. Even from vManage, we can manage the ISR as well. We have the virtual edge as well. We have ISR virtual as well. So you can manage n number of devices. You can create the template for those devices, and then you can push the configuration from vManage to the edge devices. Not only you can track the on-prem devices, but you can track the devices that will be installed inside the cloud. Okay, and that's the true power we have when we are using the vManage to manage such type of requirement. So it will give you great visibility, and the use of access or ease of access, or the ease you can access the network and monitor the network, it's really amazing. So you can go and check that how we can achieve the same target With help of vManage, obviously the way of doing things will be different, but we are going to achieve the same target in much more simpler way if we are using the SD-WAN, and then we are integrating with the cloud. Let us start with section 1, where we have to understand the architecture and various components. What are the topics we have inside the section 1? First of all, we are going to discuss about the architecture and component. Then we have to understand the components of the controllers. We have the orchestration plane, management plane, controller plane or control plane. Then we have the data plane devices. Inside data plane device, we have various things like what is TLOC, how they are forming the IPsec tunnel, what is Viptela route, what is the BFD, bidirectional forward detection. Now there are some common terms that we are going to use. So in terms of data plane device, we have vEdge or Viptela Edge routers. We have cEdge, that is nothing but Cisco ISR/ASR routers or router. Those are nothing but SD-WAN router. Then we have the controller. We have vSmart controller, that is nothing but your control plane. We have the orchestrator plane, that is the vBond. And then we have the management plane, that is nothing but vManage. Now this small v is not virtual. This stands for Viptela, because Viptela was the parent company who has introduced SD-WAN. Now the overall solution will look like this, although this diagram will find little bit busy, but once you understand all the components and the hierarchy, then it makes sense. Now starting from the orchestrator plane or the orchestration plane, you can see that you have a couple of vBond, and those vBond are identified as a DNS or a URL. They may be inside the DMZ zone. So one of the interface is towards the private data center, or one of the interface is towards the data center. Other interface is facing towards the public interface. So you have the orchestration plane, then you can see that you have the management plane, that is nothing but vManage. It is recommended that you should have cluster of vManage, means three manage or three servers inside same cluster. Now it's actually very big, and here you can see in the slide that it can be in multi-tenant mode or dedicated, means dedicated to one customer or group of customers having multi-tenancy, or maybe one company or organization having multiple sub-organizations. So any possibility will be there, but this is the management plane from where you can manage entire fabric. This is the one common place from where you can manage everything. So here you can see that from this management plane, I am managing control plane devices, plus parallelly you can push the configuration template to all the devices. Correct? All the devices in the data plane. Not only in the data plane, but in the control plane as well. So the usability of this is huge, and we'll see some of the use cases of the vManage, but vManage is there. From there, you can do the monitoring, troubleshooting, configuration, in short, everything we can do from the vManage. Then we have the control plane. That may be inside containers, or we have the VMs that you can spin up over the hypervisor. Now, recommendation for control plane that they should also be in group. So maybe you have two vSmart in one group, two other vSmart in other group, but they should have the same configuration. That means these are my control plane devices. They should have the same configuration, or they should have the common configuration. Otherwise, there may be inconsistency in the network. Now, in terms of control connection, whenever the data plane devices, they are forming the control connection, they can form the control connection with one group of vSmart as a primary, other group of vSmart as a secondary, but in any case, all the vSmart, they should have the same information. Then finally, you can see that you have the data plane devices in the bottom. So irrespective of transport, either it's internet, MPLS or 4G, they have the IPsec tunnel among with other devices. By default, they have full mesh type of setup, means all the devices have the IPsec tunnel with all the other data plane device, correct? They can be physical, they can be virtual. Okay, so now here in the diagram, you can see if I draw it. Let me try to draw the diagram so you can understand. Here you can see that this link, either this can be DTLS or TLS, and here also it can be DTLS or TLS. In vBond also you have the control connections, so vBond to vSmart, like that. I'm not drawing all the connections, but this is always, actually vBond connections are always DTLS. Now what is DTLS and TLS? TLS is nothing but your SSL, secure socket layer, plus TCP, TCP based SSL, and DTLS is nothing but your SSL plus UDP, UDP based SSL. That is nothing but your DTLS. Okay, some space, less space is there, but you can understand. Now you have a control connection like that, and then you may have the data connection or the IPsec connection. So how it will look like, let me quickly draw here the data connection as well with some other color. So now from device to device, you have the IPsec connection. By default, it will be full mesh. So here it's not in a bundle, but single. They have the IPsec connection, that is the data plane connection. So obviously the traffic will move only from one data plane device to the other data plane device, and from the control plane, that is your vSmart, you are sending the updates. The controller, that's the vSmart, they can send the update with help of OMP protocol, that is the overlay management protocol. They can use or they can send actually different type of control messages related to routing updates, security key exchange update, related to policy exchange. Okay, so that's actually the role of the controller. Now here you can see that this is the overall overview, or this is the summary of the architecture that we have inside the SD-WAN. Now why it is very interesting and important, because Cisco SD-WAN, they can scale. So here you can see, if I start from the bottom, any location, branch, co-location, cloud, any transport, satellite, internet, MPLS, 5G, LTE, any service. They can use branch security. We have cloud integrated services or security. We have the application quality experience for SaaS application, voice collaboration, cloud on ramp. Means you can integrate with any type of service in the SD-WAN. And then we have any deployment. Any deployment means on-prem, cloud, multi-tenancy, even MSPs like managed service providers, they are also offering these services. So you can see that how open and secure our network is. Open, that we can go and we are very much near to the cloud integration, or we are near to the cloud. Even we can install everything over cloud as well, either it's a controller or data plane device. You can integrate with any services. It's so flexible. You can run the application over broadband or internet as well, because anyways they are forming very high level secure tunnel in between data plane devices. So adding all these points, you'll find that the SD-WAN is highly secure and desirable solution at the moment. And I think almost all the customers, they are going for SD-WAN deployment. Now again, you can see the SD-WAN deployment architecture. You may have your branches spread across geography. You may have your physical branches. You may have your virtual branches as well. And then you can see that you can use software as a service. You can use DIA, directly use those services. The good thing about this, that whatever place you have your services or application, you can track each and everything from your vManage dashboard. So you have single GUI, single dashboard. From there, you can manage or you can track all the applications. Okay, so not only you can track and manage the application, but you can do the configuration and changes, etc., etc. There's so much tunable options are there. So here you can see that software as a service, or it's a VPC, virtual private cloud, or it's enterprise controllers, or it's a private cloud. Everything, each and everything we can go and integrate with our SD-WAN fabric inside that architecture. Let us talk about the controllers. We have three different type of controller. One is the orchestration plane, that is nothing but the vBond. Management plane, that is nothing but vManage. Control plane, that is nothing but vSmart. So vBond, vManage, vSmart, or vManage, vBond, vSmart, etc., etc. Now here you can see in the bracket vBond and comma NAT and vSmart comma OMP, because actually these features are very important to understand, and we should understand these features. So for example, vSmart. vSmart is your control plane, and among vSmart, suppose if you have 2-3 vSmart, so among vSmart they are running OMP, and from vSmart to edge devices or vSmart to branch edge devices, again you have OMP. So we have overlay management protocol, that is nothing but your control plane. So for example, if your OMP is down, your control plane is down. So that's the importance we have. Let's learn one by one what are the baseline features with these controllers. Say, for example, we have the orchestration plane. What are the characteristic and what is the use of the orchestration plane is that they are used to do the secure bring up. So to bring up your Viptela fabric, first of all those devices, they are going to, or they have to go and they have to contact with the orchestration plane or the vBond. So what is happening? So suppose that's your day zero deployment and you want to deploy one of your edge device. What will happen that first of all, this edge device, they will go and contact the vBond. So let me draw here and let me try to explain. All right, so let me redraw here. So what will happen that these devices, they will go and contact first of all the vBond. Now what vBond will do, he will check what is the serial number, what is the chassis ID of the edge devices, and this edge device, they will go and check the organization name, org name of the vBond. Now once this vBond will satisfy, because they are doing some sort of whitelist modeling, they have the list of all the devices that is going to be part of the fabric. So once the vBond will be satisfied that, oh, the request I am getting is legitimate, they will form some sort of temporary, they will never form the permanent tunnel, temporary DTLS tunnel, because remember, vBond understand only DTLS. So they will form the temporary DTLS tunnel, and then he will offer this edge device what is the vManage and the vSmart IP addresses. Now next time these guys, they will go and contact the vManage and the vSmart, and the same process will happen. vManage will go and check the serial number, chassis ID of vEdge. vEdge will check the org name. That's a part of certificate. That's a part of licensing certificate. Then again, the vSmart will go and check the serial number and the chassis ID, and then the vEdge will check the org name of the vSmart, and then what will happen? What will be the end result? The end result is that the edge devices, so here let me try draw with other color. So they will form the permanent either TLS or DTLS connection. They will form the permanent connection with vManage, with vSmart, and your temporary tunnel will tear down. Okay, so here you can see the nodes. Let me try to read out the nodes here. We have the nodes that is telling that the orchestration plane is there to do the secure bring up of the all the component, so securely bringing up the devices in the fabric. Orchestrate control and the management plane, first point of authentication, distribute list of vSmart and manage to the edge devices or routers, facilitate NAT traversal, require public IP, could sit behind one-to-one NAT, highly resilient, multi-tenant or single tenant. So that's the use of the orchestration plane. Its use is defined, their role is defined, and these are the main points. Now you can go and install this over the compute over ESXi or hypervisor, and here you can see some of the important point that they should internet reachable, they are doing the orchestration, they are securely bringing up the fabric. Now the next very important piece we have is the management plane. This management plane will go and integrate with third-party APIs, and it is there to do, you can see, to do day 0, day 1, day 2 operation, means all the day. You have to bring up first of all your vManage, and then you have to add vBond, vSmart. You have to do at least minimum configuration. You have to do the licensing process. Once your controllers are up and running, then only can add the data plane devices. And for that, you have to start with vManage. This is centralized provisioning. It can be multi-tenant or single tenant, where you can build the policies and template. You can do troubleshooting, monitoring, software upgrade, GUI with RBAC. It can be integrated with third-party tools for APIs and programming. This is also highly resilient. Now this is also a software, so you can go and install the cluster over the compute, either ESXi or KVM. Used for centralized management, API, configure, monitor, and management. These things then can be done via the vManage. Finally, in the controller section, you have the vSmart, that is the actual brain behind the scene. Now, with help of this particular vSmart, what you can do, that it will provide you the intelligence. So you can do app route policy, central policy, you can do any type of service insertion, chaining, whatever, all policies, IPsec key exchange, overall routing management, everything is done with help of a vSmart. That's your policy engine. That's your brain. Okay, and this is also a software, and you want to operate this vSmart uh, in a redundant manner in a group. So you can have group of 3-4 devices. You can have other group in other data center or other zone with 3-4 devices. Only thing is important that all those vSmart in a single fabric, they should have consistency. They should have same database. That's the important thing. So here you can see routing information, encryption key propagation, policy management, service chaining, traffic engineering, and so many things that we can do and achieve with respect to vSmart. All right, so that's the main thing we have with all the controllers. Next, we have the data plane device, and you'll find so many interesting things inside the SD-WAN data plane devices. Not only that they are doing the actual movement of data within the IPsec tunnel, but whatever existing WAN features we have, say for example, we can do VRRP, we can do OSPF, we can do BGP, we can do EIGRP, etc. So all the traditional routing protocols they are supporting. We have advanced features as well, like zero touch deployment or provisioning. They have the physical plus the virtual form factor. So these things are there, that is there in the existing WAN as well, except this zero touch provisioning or plug and play options. Even plug and play option is there in the intelligent WAN or iWAN as well. But what new things we have? It can do application recognition. It's a huge feature. Now, so for example, in Viptela devices can go and they can do The application recognition, they have something inbuilt DPI, Deep Packet Inspection Engine. In Viptela, that is Cosmos. Again, I'll repeat, Cosmos. In Cisco devices, we know that's very popular term as a N-bar, that is network-based application recognition. Now Cisco has introduced new VM as well, and they have enhanced the N-bar. We have something called AVC as well, application visibility control, enhanced version of N-bar, you can say in other words. But yeah, you have the application recognition engine. So your devices now, the SD-WAN devices now, they can understand the application metadata like Palo Alto firewall or firepower firewalls can do, or you can say that next generation firewall, they have this capability to understand the application or recognize the application, and then as per the policy, they can take the action. That's the same thing we have in the application aware routing feature. Okay, and that's one of the major advantage we have. Not only we can do the app aware routing, we can do app aware firewalling as well. Now apart from that, the edge devices and the control plane devices, that's the vSmart, they are forming the OMP session. Means we have the routing peer with my control plane devices, and then I'm exchanging all my routes. Either it's a Viptela route or TLOC route. Later on, we are going to discuss about these things like OMP, TLOC, and etc. etc. So either it's a security route or service route, it's a Viptela route or OMP route, or it's a TLOC route or next hop route. All these things you are sending to your controller, because we are dealing with the SDN solution, your controller is working as a route reflector, RR, and once they receive the route from one of the branch, they will reflect to the remaining branches. And that's the whole thing. Now, if we compare this particular solution with, say, for example, ACI leaf and spine, what leaf are doing? They are sending their endpoint uh, registration or their endpoint information to spine. Spine is working as a route reflector. He can reflect to everyone. Likewise, here also you can see these are your leaves. You think that these are your endpoint. These guys, whatever they are learning, they are sending to vSmart, and vSmart is reflecting to everyone. In between, the underlying protocol is OMP. And again, it's a huge, OMP can carry so many things. But the overview or the top view is like that. Then obviously these are the data plane devices. So let's go and see that what are the variants we have in this data plane devices. You can see that there's a number of devices that is supporting for SD-WAN. We have enterprise network compute system, say ENCS 5100, where you can go and integrate, or we can go and deploy the SD-WAN images, the third-party firewall, load balancer, etc., etc. It's a very capable devices, and so many customers they are using ENCS devices. You can see overall throughput as well, 250 to 2 GB. As per your scale will increase, your compute, your memory, your RAM, etc. increase. That means they will support more throughput. Now we have both the form factor. We have hardware, we have software. Here you can see the Viptela devices. In Viptela, you have a small end devices like VH 100, then 1000, then 2000. Very much it is looking like Cisco device. Cisco maybe 1800 or 2800 type of hardware. Then here you can see that you have iOS XE image. Now this is the thing I want to explain here, because I found some of the confusion around the community. See, we have SD-WAN, Cisco SD-WAN, and you have two type of operating system. One, iOS XE with something 16.10 or more, maybe 16.11. You can convert or you can upgrade the image of iOS XE. Inside iOS XE image, we have SD-WAN code written. So it will support features, SD-WAN features. But there is one native operating system that is nothing but Viptela OS. This Viptela OS, actually the evolution of this Viptela OS was due to SD-WAN. So SD-WAN was the core in the brain, and then evolution happened. Now this Viptela operating system, it is coming with vEdge, Viptela Edge, but Cisco has introduced the same image you can run. Here you can see vEdge next generation ISR platform. You can use Cisco ISR platform to run Viptela OS as well. And that's a huge advantage we have with Cisco. Means you have the best operating system for SD-WAN, and then you have the best hardware for branches. You can integrate both, and they will do all the features, that whatever features we have in the SD-WAN and whatever features that is going to come in the SD-WAN, everything will be going to be supported. So that's the good thing we have. Okay. So apart from that, as per the scale, you can see we have the ISR. We have the ISR 4000 up to 2 Gbps speed. Then we have the aggregator routers, ASRs, that having up to 200 Gbps of speed. So if you are looking for the speed and throughput, you can go and choose your branch devices. I have few slides for edge devices. You can see 100 and 1000. How behind the scene this vEdge is looking like, very much like Cisco device. You have the management interface, you have the serial console, USB, LEDs, you have the fixed 8 gig Ethernet SFP port. Why I have added this slide? Because I want to tell you one nice thing about these hardware. These hardware, they are coming with TPM chip. Now this trusted platform module or chips, they have anti-counterfeit and secure authentication. Means what is happening, that OEM, Cisco is the OEM in this case, they are adding or they are putting the RSA keys inside this TPM chip, those preloaded certificates or CSR, certificate signing request, they are shipped to the customer. So what customer has to do, at the moment they connect their WAN interfaces to the WAN, or they should be VPN 0, we'll talk about this later on, but at the moment you connect your interface to the WAN, they will do the auto authentication, or automatically they will get authenticated from the controller devices, because you have the preloaded certificate inside the TPM chip. Now considering the fact that the edge devices, they are coming with the secure image or secure boot image, Cisco devices also coming with secure image. Cisco devices, they are using TAM module, Trusted Anchor module. I will show you this in the next slide. And the edge devices, they are using TPM. This TAM module, you can check, this is there in the UCS boxes as well. You can go and check. So how it is secure, you can see you have the anchor module that is very near to the hardware anchor, microloader, and then bootloader check the operating system, and the OS get launch. So it's like internal integrity checked by the anchor module, and then it will load up. Likewise, you can see that you have the common features between TAM and the TPM. So they are anti-tamper protection, non-volatile storage, policy and configuration. They have crypto services like key store, random number generation, and crypto image. Now all these features that you are seeing here, this is belonging to certificate plus to secure your hardware. And that's the power we have. And even the provider of SD-WAN, they have thought of all these things before putting or before giving the SD-WAN solution. So all these features we have inside the data plane devices. This is the last video in section 1.4. This is 1.4b, traditional WAN and the SD-WAN solution. Now, what exactly inside SD-WAN solution is that, so this is your existing WAN. Whatever things that you can't do in the existing WAN, or it's very difficult to do in the existing WAN, that I can go and do inside the SD-WAN. So the term is simplified solution, the scalability, inbuilt secure fabric. Those things are by default there inside the SD-WAN. That is although not there in the in the existing WAN, but you can achieve with certain number of codes. One of the major drawback we have in the existing WAN is that its visibility is not that much. And suppose if we have to create IPsec tunnel, now if you use DMVPN, that is very much the case we have inside the SD-WAN, is still that DMVPN or any type of IPsec VPN that we have, in SD-WAN you will find that it is 100% optimized. So at the moment you bring up the control plane, now the control plane, now I'm seeing that most of the customer, they are taking the control plane from Cisco. So you may have over the cloud control plane. So I have this cloud hosted, say for example, cloud hosted control plane. So my control plane burden is gone now. Now I am only worried for the data plane devices. Now these data plane devices, what are the major things they will do? They will do routing, they will form IPsec tunnel, they should do data plane policies, or they should do data policies, not data plane policy. But inside data plane policy, you have so many things actually. You can refer my SD-WAN course where I have explained this, and we have so many things to consider when we are talking about policies. But in short, what I'm telling that what are the capabilities you have is the routing, you have the IPsec, you have the app, say for example, app aware routing that is falling under data plane policy or data plane or data policy, etc. So routing, IPsec, data policy, and plus cloud integration. These things are the nature of SD-WAN. They are evolved with these capabilities. Although, in other hand, if you go and check the existing WAN, so you will find that for each and everything you have to write the code. So for example, if you want to form IPsec tunnel, you have to plan, and that DMVPN planning for hub and spoke and redundant DMVPN design itself is time consuming, and it should be constant throughout the devices. Correct? Means you should use some sort of a standardization for the configuration. On other hand, when you have the IGP and when you have the BGP, so those configurations should also be um, good, although the routing capability of Cisco devices is the best, and Cisco is very good in the routing at least. They are very good in other features as well, but routing is the fundamental and core of the Cisco networking. Even Cisco is very good in switching and in data center and other domains as well. All right. So the thing is that you can do all those things, but it's restrictive. You have to write n number of line of codes. It's not that much scalable. You can integrate with API, which is very difficult. You have to uh, check what are the alternates there in the market. So you can use Ansible, Playbook, etc., to do full automation for the existing WAN, and it's a time consuming. So you don't have full visibility, and its evolution is not that by default it can scale in terms of routing, security, cloud integration, etc., etc. Correct? So that's a major uh, differences we have in the existing WAN and the SD-WAN. Is still, if you go and complete that SD-WAN course, you will get the complete picture of SD-WAN, because already at this point of time we know whatever network we are working is the WAN. One portion of that network is the WAN infrastructure. So we know about the WAN, and once you go and complete the SD-WAN course, then you will understand about the SD-WAN course, and then you will be at the better position to compare with the SD-WAN features with the existing WAN feature. All right, so let's stop here. Now we reach to 1.5, and in 1.5 we have to learn and understand about software defined access, SD access. The common term is DNA. Here we have to understand that what is SD access and what does it mean by control and data plane. And some of the examples also I'll add. We can uh, correlate this, or we can differentiate in a manner that what is the existing campus and then how it will look like inside the DNA or SD access. All right, so we know DNA, and what DNA is going to add value in the market is that we have the full automation engine, we have the analytic engine. Actually, we have NDP, network data analytic engines. What is happening here is, and I have explained this earlier also, that now you have management plane, you have control plane, you have data plane, and you have policy plane. Now this management plane is nothing but your DNAC engine, DNA controller. From DNA controller, you can write the policies, you can do the orchestration. It is open for the API. We have full automation support. We have full analytic engines. We can do the programming. We have the virtualization support. We'll see that. What does it mean by network virtualization? And then obviously we have this cloud integration and support as well. In short, whatever required for SDN, everything is supported in this particular module, in this particular feature. So this is nothing but the SDN type of LAN or campus area network solution. Now, why we are getting such type of enhancement in the existing campus network to the DNA is because now we have the full support from the hardware, and then we have full support from the programming as well. Full support from the hardware means now we have the programmable ASICs. ASICs where we can write the program, they can understand the program. They have the analytics, means they can understand the analytics as well. They can understand the programming as well. We can do full automation in that. So here you can see that due to the evolution of ASIC, either it's a wired or wireless stacking, TrustSIC, SDN, they can do programming. They are flexible. Recirculation will be less. We have integrated stacking, visibility, security. Means we have mature and very extensive hardware, and that can be easily integrated with the programming. So whatever programming that we want to do, or in future we want to add it, that will be fully supported with the hardware. Generally we are using Catalyst 9000 switches for DNA. I will see that later on in this session, and I will point you to the URL where you will get the list of all the supported devices. So not only the switch, but routers, WLCs are also there for DNA. Now let's try to understand that what is fabric, because this fabric is a common term. Either it's a ACI fabric, application centric infra in a data center, or SD-WAN fabric, or DNA fabric. So everywhere you used to get the term fabric. What is fabric? Fabric is nothing but the overlay. So that means we have underlay as well, and the answer is yes. We have underlay and then we have overlay. So whatever connectivity, whatever physical connectivity you have, that is nothing but your underlay, correct? And then if you abstract this physical connectivity as per your networking, as per your topology, that will be the overlay. And different abstraction can be different virtual network or tenant. So tenant 1, tenant 2, tenant 3, these tenants are nothing behind the scene. They are the overlay or instances of the physical infrastructure or the abstractions, correct? So the overlay that we are using at this point of time is not a new concept. We know that we used to use Lisp, OTV, DFA, ACI is new, but CAP, web tunnels, IPsec over DMVP, and MPLS, GRE, these are actually the old terms. So what Cisco has done nicely in DNA is that they have use the old mature technology only. So for example, Lisp and VXLAN, we are going to use inside DNA, and with that, we have the SD access, this DNA, a campus area network, that is software defined access network. Again, we have some slides that just to differentiate inside the underlay and overlay. So with one particular fixed underlay, you may have multiple overlay. So you can create overlay for tenant 1, tenant 2, tenant 3, or customer 1, 2, 3, etc., etc. Correct? And that's the true power you have. So now you have fixed your physical devices and connections and interfaces and wiring, and then you can abstract that. Now, if you do this uh, overlay, or if you are in the fabric, then what features you have? You can do the mobility, scalability, programming. Now you have all sort of flexibility with you. Correct? Again, one more example with the overlay, and this is actually specific to the DNA. In upcoming session, we'll go and learn about DNA terminology, and then you will find that you have terminology used, say for example, edge devices. So you have edge devices, then you will go and learn that you have the border devices as well. You have edge devices, border devices, and then edge devices and the border devices. Then again, we'll see in upcoming slides other terminologies as well that you can abstract inside the overlay. So you may have multiple overlay with the fixed underlay. So you have underlay and then you have overlay. For underlay also you have the control plane, overlay also you have the control plane. Just an example, underlay control plane may be VXLAN, overlay control plane may be Lisp. Okay, we're going to discuss about Lisp also in the upcoming session. Maybe after this, we have session for Lisp. Even if you go and check the syllabus, you'll find that section 2.3 is for VXLAN and Lisp. So after this section, when you go and start your section 2, that is for virtualization, there you will find the topics related to VXLAN and the Lisp as well. Now there is some uh, best of both in the world. So L3 and L2 overlay examples, and VXLAN you can think as a, even VXLAN is used for L2 and L3 as well. But at this point of time, you can think that VXLAN can be used as a L2, and then Lisp can be used as a L3. Although VXLAN can be used for both, generally it is used as a L3 overlay, is VXLAN. All right, so what type of planes we have? We have control plane, we have data plane, and we have policy plane. And one by one, we are going to learn actually in section 2.3. I think A and B, you can go and refer. We have VXLAN and Lisp. And then you have the policy plane. These are the key components of SD access or DNA. The differences: L2 plus L3 overlay versus L2 or L3 overlay, host mobility with Anycast gateway, VRF and NZT. We have topic related to VRF as well in section 2 in the virtualization, virtual tunnel endpoints, no topology limitation. Why, if you have any limitation, not in DNA? Because we are going to use the scalability method with respect to Lisp, locator separation protocol or locator ID separation protocol. We'll see that. We have complete things related to that. We are going to check that. So what are the terms we have in DNA? You have control plane, that is a Lisp map server. You will find this term MSMR, map server and map resolver. Then you have the edge node, they are Lisp tunnel router. So XTR, it may be inward and outward. We'll see that. So you have tunnel router as a edge node, and then you have proxy tunnel router PTR as a border node. I will go and refer this topology. And then we have the intermediate nodes as well. These terms we are going to use so many times in the DNA. The fabric domain is FT, that is the Lisp process. Virtual network, we have the VN or the VRF. We are going to check this, and these are the loose term. So VN is the loose term for Lisp instance, is the loose term for VRF. Endpoint ID group or EIG is a segment that can be used inside the TrustSec that we can check. Host pool is the dynamic endpoint ID or VLAN plus the IP subnet. So these are the terms actually are going to be used inside the DNA. All right, so I hope you understand that's overall DNA term. At least three planes are there. Three things are there: Lisp as a control plane, VXLAN as a data plane, and ICE actually is for policy plane. We have very important topic now is the Lisp. Lisp is the control mechanism or control protocol for DNA. This is nothing but the locator ID separation protocol. Means how you can differentiate or how you can separate the identity and location. We'll see that what is the mechanism and what are the uh, technical definitions or technology behind the Lisp. Correct? So let's try to understand this fabric and this DNA piece step by step. Now here in the diagram, you can see that you have edge devices. These are actually the edge devices. We have three components. You have edge, then you have border, then you have control. One by one we'll go and discuss all. But these edge devices that you are seeing here, actually the endpoint identities are connected with them. Here you can see EID, EID. So this edge device specification is that one portion is connected with EID, but one portion is inside the fabric, correct? Now inside the fabric where you are running the Lisp protocol as a control mechanism, now this Lisp protocol has a R locator, means router locator, and then inside that you have one database. So that means that whatever edge devices you have, they will map to the RLock, and that EID to RLock mapping will be stored inside the database. And that's the case we have. It is doing like this. Now we have the other components as well. So let's try to understand all the terminology, and then I'll come back and connect all those pieces. Now, if you use Lisp, what will happen? Say you are storing or you are preserving the identity. So suppose if you move the system from one place to other place, before Lisp, they have to change their identity. But if you are using Lisp, you can see they are preserving the identity. So that's why they are supporting the mobility feature. And this mobility feature is huge in the campus area network because all the time users are moving from one place to other place. Now, how is Lisp used in the campus fabric? Let's try to understand this. In campus fabric, you have the a controller router, you can say at this point of time. So you have one controller router, and then you have the edge devices that is connected with EID. You know that they will use R locator, and here you have the database who will store EID to R locator. Now what will happen? This EID has the database /34 for IPv4, /128 for IPv6 or MAC addresses. So at the moment you are part of Fabric or you want to become the member of Fabric, you will send all the prefixes to the controllers or to the control plane. Now this controller, what he will do, that he have his database. Next time, suppose this is A and this is B. Next time, suppose the B wants to communicate with A, and he don't know how to reach to A, he will go and contact the controller. Hey controller, I want to reach to A. Now since controller know that this request is for A, why? Because he has the EID to R locator information, so he can tell, okay, this is the way that you can reach, and later on they can go and communicate directly. Okay, so it is working, you can think at this point of time as a proxy, but that's true. why it is working in this way and what's the benefit we have, I will show in the next slide. But this is the mechanism behind the scene, correct? And you can read out these points as well. Now here you can see that you have the edge node or edge device. The Lisp term is Lisp tunnel router. So these are the Lisp tunnel router because they are going to do the mapping for EID to R locator. And again, this term is also huge. So provide Anycast L3 gateway for connected endpoints. So whatever EID to R locator, obviously R locator will be fixed for the EID, but they are going to check who is the group to near, who is the nearby endpoint, and then according to that, he has to store the information. Again, in the big fabric, you have or you should have multiple control nodes. Now, those control nodes, which particular group of endpoint is near to that control node, so there this Anycast will come into the picture, correct? All right, so you have the EID. They have to register to the control plane or the controller, and then the controller will have the database for EID to the allocator. Then again, you have the border node as well, and they are termed as a Lisp proxy tunnel router. So you have Lisp tunnel router and then you have Lisp proxy tunnel router. Why? Because if you want to go to Lisp to non-Lisp domain, or who will be your entry or exit point, so these border nodes will work like that. So here you can see the nodes. Connects traditional L3 network, that means non-Lisp domain if you want to go, where two domain exchange endpoint reachability and policy information. They can have VRF and security tagging group or group tagging. We'll see that these things are possible when we are talking about Lisp. The two very important feature of Lisp is one is the mobility, other one is the virtualization, or they are supporting VRF. Okay, provides a domain exit point for all the uh, edge nodes. So that's the usefulness of the border. So now we have three terms. We have edge, we have border, and we have control. Border is the entry point, the exit point for all the edge devices. Plus, if you want to communicate from Lisp to non-Lisp domain, this border will be getting used. This control plane or the controller device is to have the database for EID to R locator information, correct? And these are the terms actually. Apart from that, there is one other term as well, that uh, transient devices. So in between, if we have non-Lisp devices, so that is also supported. So it is not mandatory that inside the fabric you are running Lisp to each and every devices. All right, so we reached or we understand up to this point. Let's understand few more slides. What benefit we have, and that's the main thing. So I'm going to use Lisp, then what benefit that Lisp will provide to me. Now here you can see the benefit. First of all, mobility and then the virtualization. Both features are there, means devices can move from one place to other place, but they still have their actual identity. Why? Because they're responsible to manage their identity. That's it. That's it. They're not there to manage the entire topology table or entire database, because for that you have other devices in a network. Apart from that, these Lisp, they are fully supporting virtualization. So for virtualization, there are some code for VRF and all, but they are fully supporting virtualization. Now, before moving further, let's try to understand about this location and identity term. You have location and identity. You have the identity of yourself. So that is nothing but the endpoint route. So you have endpoint route, and then you have this color red is topology route. Now you can see in a big network, the topology route will be very big. And why you want to have the topology route and unnecessarily you are utilizing your tables, your CPU and processing, etc. Rather than you offload this. You offload this topology route to some database. Whenever you want to need it, just contact to the database and that database will provide you that information. So rather than adding or rather than putting extra burden to all the devices, you can put that in a centralized location like this. So now you can see that the efficient utilization of the CPU, they are not overloaded because you're storing the topology table to the central location, and whenever they need, they will go contact there, they will get the answer and then they can communicate directly. That's the overall idea. So now you can see the scalability feature, the better utilization of resource feature, and they are supporting mobility and they are supporting virtualization as well. So routing scalability is there, mobility is there, and virtualization is there. With help of Lisp, we can achieve all these target. Finally, we have the Lisp mobility in the campus fabric. We have the host pool. Now, this is nothing but you are preserving the VLAN and the IP subnet. So now you are creating the VRF, for example. So VRF A, VRF B, VRF C. Later, we'll go and study about VN, virtual network, associated with VRF. So different network or instances you can create, and once you have those instances or network, they are associated with VLAN ID. Everything will happen dynamically here, and they will manage the network. So you have the resource, but you are doing sort of virtualization in terms of VLAN and subnet. You are preserving the VLAN and subnet, and then you are doing the communication. That term is host pool. So host pool is based on IP, subnet, and VLAN ID. Okay. Again, these are the features we have inside the Lisp, but the core fundamental is the same. That means that you have to register somewhere. Where you are registering, he has the information of all the topology inside the fabric. You have you have local responsibility. Now you can think like this: you have local responsibility, and someone has the global responsibility for all the devices who has their own individual responsibility. Whenever one responsibility wants to communicate with other responsibility or who has the responsibility, so at that time they will consult the global member and he will provide the path. Obviously this will not having the lag, this will be very faster. Okay. Finally, the Lisp is supporting the virtual networking or VRF, and you can by default that will be VRF 0, but we have option. We can go and configure VRF 1, 2, 3, 4, etc., etc. So different fabrics we can create, or you can think like different overlay you can create inside the fabric. This overlay is nothing but the virtual network. This virtual network is nothing but a tenant itself. So tenant, overlay, virtual network, all together they are the same term or the same thing. Alright, so final thing is that how Lisp is working. Already we have discussed that you have one centralized database. So whenever your edge device who has the uh, identifier or edge endpoint identifier, they will go and register to the control plane or the controller, or basically we are telling this as a control router. Sometimes it is referred as a MSMR, map server, map resolver. So bottom line is that once you are inside the fabric with help of RLock, so EID to RLock mapping is happening, and then you have the entire database is stored at this guy. You can think this as DNS as well. So you may have local DNS, you may have global DNS, like that you can think. And whenever you require, you are resolving like DNS. So these guys will resolve like DNS. They will send their query, and finally they will get the response, and then they will do the communication. So very much like how the DNS is working, the same way the Lisp is working. If you want to learn more about this, you can go and check these links. Plus, you can go and check, there are so many good documents in Cisco Live as well that you can go and refer. Previous session we have discussed about a Lisp, that is the control plane for DNA. The data plane for DNA is a VXLAN, and let's learn about VXLAN. So now here you can see the header formatted. That before going that, let's try to understand that what type of headers information we have inside VXLAN and Lisp. So normal IP packet will be looking like this. You have the payload, you have IP, you have Ethernet. But if you go and check Lisp, Lisp is actually the L3 overlay, but VXLAN is L2 plus L3, means it supports both L2 and L3. Lisp is referred as, you can see here, this is something IP in IP, and VXLAN you can think as a UDP in IP. So you have IP packet, even you have Ethernet packet, and then you have the UDP encapsulation, and then you have the outer header format as well. We have the document, we have the slide actually, that is referring some of the points. I'll come back there as well. So MAC in IP, but you can think VXLAN as a UDP in IP as well. And here you can see Lisp as IP in IP. Okay, so VXLAN as per Cisco, you can refer as MAC in IP, and Lisp you can refer as IP in IP. All right, so here you can see that you have the header format for VXLAN. You have your IP and payload up to this point. Then you have VXLAN encapsulation. Then you have you have the UDP encapsulation, and then you have IP and Ethernet. These are the outer header, and then these are the inner header. Now, knowing up to this point, let me go back to the actual header format, and we have those in detail as well. Let's try to understand this first, and then I'll go and cover the next header format as well. So now here you can see that you have the actual payload, then you have the IP header, you have MAC header, you have VXLAN header, you have UDP, where you have the destination port as 4789. Then you have outer IP header and the outer MAC. Now in outer IP header, it's important that you have the source IP as a source RLOC related to Lisp, and then the destination is destination RLOC related to Lisp. That is the fabric outbound and inbound IP addresses. The rest of the things are very much similar, that how the VXLAN used to work. In UDP, you will see that your source port is the hash of L2, L3, L4 headers. Your destination port is UDP 4789. Okay. Now, if you go and check the VXLAN header, you'll find that you have the segment ID that is going to integrate with ICE security group tagging. So you have 64K possible segments. Then you have this VNID, VNID, and this is actually 16 million. And actually 16 million is not supported, but yeah, it's very much and more than the VLAN ID. VLAN is actually, we know that we have only 4K VLAN, and that's the restriction we want to overcome inside VXLAN, that we have 16 million of possible VLAN if we are using L2 VXLAN, VRF if we are using L3 VXLAN. Okay. Although this diagram is very busy, you have to take your time and at least draw the VXLAN, UDP, and outer IP header. These three are important. Now VXLAN, once you understand VXLAN, these are the fixed thing. Then UDP header, it's easy. Source will be the hash value, so you can do the ECMP. Destination will be fixed 4789, and then the outer IP addresses are the Lisp-based inner and outer IP. That is the RLOC, correct? Now we have one more diagram here. Let's try to understand parallelly Lisp header and the VXLAN header. Lisp, we know that IP in IP, so that's why you have the inner header as a IP. Then you have the Lisp header. You have one field here, that is the instance ID. This instance ID is the criteria for the virtualization. So if you want to do a Lisp virtualization, you have to put instance ID apart from 0. 0 will be the default. By default, all the configuration has 0 as a Lisp ID, but for different VRF, you can put different instance ID. Then you have the UDP destination port and source that will be randomly generated. Then you have the outer header. Outer header, we know that what will be the outer header for the Lisp packet. So you have the destination routing locator, you have the source routing locator. UDP protocol number is 17, like that. So we have referred the diagram, and here you can see the same thing. You have inner header, then you have Lisp header, and then you have the outer header, correct? Like that. Better you refer this rather than this. All right. Now, when coming to VXLAN, here you can see that you have inner header. So you have the payload here, and you have the Ethernet as well. Then obviously you should have IP as well. So once you have the IP, then you have the VXLAN. Here you have the VNID or VNI. You have L2 and L3 VNID. You have some reserve bit as well. Then you have the UDP encapsulation here, where the destination port is 4789. Source will be the hash of different values. Then you have the source routing locator and destination routing locator. And then you have this is actually your outer header. So you have outer header, your UDP, your VXLAN, your Ethernet, your payload, and optional things. Okay. So this is the way that you can understand VXLAN, and actually we have covered the detailed comparison of VXLAN and the packet format. Now we have one more slide here, that is that how this data plane is working. Obviously it will do the decapsulation and encapsulation at the edge point or the edge node. So if you have two edge node inside the fabric, they will do the encapsulation and decapsulation. So if I can draw and explain here, I have one device here as edge, and then I have EID. I have other device as a edge, so suppose edge 2 and edge 1, and then I have EID. When the packet will come, it will resolve the Lisp. It will go and contact with the control device or MSMR, where it should know that how to reach to the destination. Then the dynamic VXLAN tunnel will form. In that dynamics VXLAN tunnel, the source and destination outer header will be the RLOC source and destination IP. Correct? So that's the thing written here. The underlay address, advertisement, and mapping. This is your underlay, and this is your overlay or fabric. Correct? So this thing will happen. Then automatic tunnel, so your VXLAN tunnel will form automatically. Then frame decapsulation between routing locators. Obviously encapsulation and decapsulation will happen. So once you are sending the frame with VXLAN, it will do the encapsulation, and once it will reach to the destination over the tunnel, he will do the decap. So incap and decap will happen. Lisp is IP in IP, VXLAN is MAC in IP, and then we have some of the Lisp control events as well. So this was the detailed explanation of VXLAN, and I hope you understand the format, the encapsulation, the packet format, and how it is working. So in next section, we'll go and learn that what type of products supported inside DNA. Although there are links where you can go and check the list of product, and there's a huge number of products that has been supported inside ST Access or DNA. This is the last recording in section 1.5, and we are going to study about which type of devices supported inside DNA. Plus, I'm going to do the summary as well for section 1.5. We know that we have three variants. We have the edge node supported devices here you can see, and we can go and check the data sheet as well, which is the hardware and which is the software supported for DNA as edge node. Then we have the border node. Here you can see that 3K, 6K, ASR 1K, ISR 4K, Nexus 7K, they are supported as a border node. Again, these are the old iOS XE and iOS images. We can go and check the latest image, latest plus the stable image for ST Access. And finally, we have the control plane devices as well. So we have the Catalyst 3K, 3850, 6K, 6800, and ASR 1K and ISR 4K. You can see here that in the border node and the control plane node, devices are common as well. So there are devices, they can work as a border and they can work as a control plane node as well, that will be there in the fabric. Now if you want to check the new and the latest number of devices and how many devices are supported, you can go and check this particular link. There you will get the Excel sheet, and in that you will get so many supported devices with different product ID, different devices and their hardware capabilities as well. If you want, you have to go and check the data sheet. All right, so let's summarize that what we have a study. We know that we have the management plane, we have the control plane, we have the data plane, we have policy plane, and we have a WLC as well. So in the DNA or ST Access, what are the key components we have? We have the DNAC server who can do the automation, assurance, plus management, correct? Because he has a full visibility, because the telemetry is supported inside this, so that's why he has the full visibility. He can do management, automation, and the assurance. That policy plane is ICE, so we can create Pixie grid feature and the ICE. So from ICE they can send the input to the DNA center, all the contextual information, and DNA center can analyze those and then it can give the output. But the policy plane is ICE. Then we have the edge node here. You can see the edge devices where you have EID connected, endpoint identifiers, and then those will be registered inside the control plane nodes. Then we have the border node to do the communication with non-Lisp environment. We have the wireless controllers. The APs are not shown here in the diagram, but yeah, APs and wireless controller, they can use Fabric to build the tunnel to do the communication. So this is the overall picture of the DNA, where you have single unified fabric that will be controlled and managed from the DNA center or the DNAC. Okay, and finally, this is the overall thing that we want to achieve. So we want to do the we want to achieve actually virtual network, or we want to achieve the overlay. Beginning of this section we have discussed that yeah, you have fabric, you have underlay, fixed hardware, and then you can abstract that as a virtual network or the overlay or tenant. So here you can see that you have the fixed hardware connection, where you have the border node, edge node, intermediate nodes, etc. And then you have multiple instances as a virtual network A, virtual network B, virtual network C, up to N, etc. Okay, and that's the overall goal we have with the fabric, and this is the thing that we can achieve with ST Access or DNA. 1.6 is again important section where we have to learn about quality of service, both related to wired and wireless. Apart from that, We are going to discuss about QoS components and the policy in detail as well. Now, why we need quality of service? We know that if we have congestion, if we have bandwidth issue, at that point of time you need QoS. Even if you have bandwidth issue and still you need QoS, means if you have sufficient bandwidth and still you need QoS, because how you're classifying the traffic and which traffic you're giving the priority, that's important. In the next slide, I can show you here. So here you can see that there are chances that you have uh, high sender, slow receiver, and vice versa. So at that point of time, you need a quality of service. Suppose you have 10 gig, 10 gig. So let me highlight here. Two interfaces with 10 gig, and then here you have uh, only one link with 10 gig. So suppose 10 plus 10 become 20. So with 20 Mbps or 20 gig, you are sending the traffic, but the receiver having a speed only of 10 gig or maybe 10 Mbps. So in that case, you have 2:1 of oversubscription, and this is the classical case of high sender and slow receiver. Obviously, in that case, although whatever speed or bandwidth you have, still you have to categorize the traffic, classify the traffic, and then you have to map with the certain hardware queues inside different type of Cisco platform. So why we need QoS? Because the primary role of QoS is to manage the packet loss. There are traffic, they are very much delay sensitive. So if much more delay and congestion there to deliver the packet, uh, they will lose their meaning, and it's actually very difficult for those packets to do the reassembly. So first thing is that manage the packet loss. The second thing is that obviously the end-to-end delivery should happen, and for that you have trust, classify, and the policing. In this section, we are going to learn uh, all these things with respect to all the hardware. Now, when I am talking about all the hardware, we'll see in the next slide that which type of hardware it is expected to learn about QoS. Before going there, we should know our tool. So we should know the hardware we are going to work on, what is the CLI command or the GUI command, or what is the software or syntax, what is the global setting to that hardware, what will be the default setting to that hardware, where you want to set the trust boundary, where you want to apply the QoS, either it's a physical or logical interfaces. You should understand this NBAR, network-based application recognition protocol. This is not very new thing, but Cisco has done so much innovation inside NBAR, and now this NBAR along with DPI, Deep Packet Inspection Engine, they are working inside SD-WAN images or SD-WAN devices as well. So for example, Cisco ISR, they have NBAR 2, so they can do deep packet inspection. Somehow they come to know about the metadata of the protocol, and according to that metadata protocol inline, so packet when it is coming to the ingress going to the egress, at that point of time you can go and apply app route policies and different type of policies as well. So NVAR is important. Who is going to do the uh, application discovery? Once you discover the application, then you can apply the policy for that, and they apply policy either ingress and egress as per requirement. Now let's quickly see that what type of hardware we have in this. um, we have hardware 2960, 3560, 3750. They are very much similar type of hardware, and by default QoS is disabled. You have to go and write a code MLS QoS. Then the QoS will get kicked, it will get a start. MLS is nothing but multi-layer switch QoS, MLS QoS. Okay, so here you can see this is one type of hardware. Now the second type of hardware you have is 3650, 3850, where you can go and use modular QoS CLI command. Modular QoS is very much iOS XE images are using, even the Cisco routers are also using MQoS format of QoS or syntax. QoS is enabled by default. You can go and allow this, means apply this QoS. Okay, we'll see later on that what are the syntax and what are the queues, etc., etc. Then you have 5006800 modular chassis switch. Again, you can see, so here you have MLS, here you have MQC, and then in these chassis you have C3PL, Cisco Common Classification Policy Language QoS. Now here you can see that QoS is enabled by default in SUP2T, Supervisor Engine 2T, and 6T, disabled on by default on SUP720. So even the common hardware is still different. Supervisor engines has different type of setting, and that's the thing, that when you're using QoS, you have to learn the QoS for all different type of hardwares. Okay, all ports are trusted at layer 2 and layer 3 by default. C3PL presents queuing policy similar to MQC. The good thing is this, that C3PL and MQC format will be similar. Only difference is there that you have to use the type of policy. Likewise, we have Nexus 7K 7700 Nexus, where QoS is enabled by default. All ports are trusted at layer 2 and layer 3 by default. NXOX queuing policy similar to MQC, but as defined type and with default class names. So again, here also you have to learn the QoS policy syntax. Different hardware, different type, different way to write the policy. Good thing is that MQC is very much common for all the platform except the access layer type of switch like 2960, 3560, and 3750. Now let's quickly discuss about the trust boundary, where you want to put the trust boundary. And when we are talking about QoS, remember that you have layer 2 QoS, that is class of service. You have layer 3 QoS, that may be type of service, and we'll see that how we are going to map costs with DSCP, layer 3 DSCP marking bit. Okay. So here in the diagram, you can see that you can set the trust boundary for Cisco phone, for telepresence system, IP camera, media player. Your trust boundary may be at the level of switch also, or you're not using any type of trust. So that's one thing, that you can go and use the trust boundaries for QoS configuration. Suppose if you want to map your COS to QoS, so here you can see that you have 8 COS and then you are mapping with 64 DSCP bit. Now in very easy term, how it is that actually you have 8 bit, and let me try to write, say 1, 2, 3, 4, 5, 6, 7, 8. Now last two you can reserve as ECN, explicit congestion notification. Then first these three, and again you have to count from here. So these three you can think as that can be used for DSCP, or actually there are complete list of AF, assured forwarding, and hence. Then you have the first 3 bit, actually those are used for COS, class of service. So that means you have 000, 001 up to 111. So that's why the number will be from 0 to 8, because these you can read as 2 to the power 1, 2 to the power 2, and 2 to the power 3. So 1, 2, 3, like that. So binary to the decimal conversion, etc. So that's why here you can see that you have COS bit like this, and then you are mapping with the DSCP, and inside DSCP you have 64 values. You can map like this. Now again you have to understand, and that will come with experience, that which is your high priority traffic, which is your low priority traffic, mid priority traffic, default traffic, etc. So when we are using COS 0, generally the COS 0 marking will be for default. If you have high priority traffic, So here you can see that you have high priority traffic where you are using COS 6 and 7. These are for control plane traffic. These are for network control traffic. So for example, OSPF is there or STP is there or any type of control message exchange. These queues, even these are reserved for that. Then you have EF, explicit forwarding. This EF or expedite forwarding, these EF are for voice type of traffic. Then you can have this is, say for example, high priority traffic, mid traffic, and default. Like that, you should categorize all these things. But never mind, we have the slides in the upcoming session that we are going to discuss about that. Here again, you can have the trust boundary, and boundary doesn't mean that you are going to apply the policy at that point of time. So you have trust boundary here to mark the packet for the VoIP or for IP phone. Now for this particular IP phone, the policy may apply it at switch level, it may apply to the router level. This PEP is nothing but policy enforcement points. So it doesn't mean that if your trust boundary is there, you are going to apply the QoS policy at the same point. You can change the policy enforcement. Now, when you are applying the QoS, here you can see that you can apply per port QoS, you can apply per VLAN QoS. When you apply per VLAN QoS, whatever interfaces inside that VLAN, that will come into the picture. Correct? So policy map is applied to the logical VLAN interface. You can go to the VLAN, you can apply service policy input marking, and then you have, because suppose if this is 2960 switch, so you have to go and use this command mlsqs VLAN west for all the interfaces, and then over the VLAN you are going to, or you are applying the policy. Now if it is per port QoS, so you can go to all the ports and then you can apply the QoS service policy input marking. Correct? So these are the starting point of QoS. In upcoming session, we are going to learn more and more about QoS. Before winding the session, I have given one extra slide here for N-bar. N-bar, they are using UADP chip. This is nothing but the ASIC, and due to this ASIC, we have that much capability to understand the metadata, or to understand 1400 plus applications. So with help of this unified access data plane chip, if we are capable to understand the application, and once we are able to understand the application, then we can create and put the policies. Correct? Everyone knows that Cisco is one of the best company who's making high quality hardware, and N-bar 2 embedded inside the hardware, providing very nice application recognition features. All right, so this is it for the introductory session. Let's stop here, and in next section we are continuing from here. Let us discuss about QoS design and implementation for these hardwares or for these platforms. So we are going to start with 2960 and we'll see the QoS design. Later on, we are going to discuss about remaining hardwares and platforms and design. Before starting anything, we should understand this chart, because all the time you are going to get too many things. Actually, you are going to get different type of code words. Say for example, COS, DSCP, TOS, AF, IPP, IP precedence, CS, class selector, drop probability, and ECN, explicit congestion notification. Now I already told you that you have to focus on 8-bit. So 1, 2, 3, 4, 5, 6, 7, 8. Last two you can exclude because they are used for ECN, explicit congestion notification, but these 6 you can consider. So now if you see this particular table here in your right hand side, from here you can easily figure out that what is the cost value and how we are going to map with the cost to DSCP. Again, this particular diagram and slide actually is important. First of all, we have the category of application from high priority to low priority. So here you have high priority and then you have low priority traffic, correct? So you have routing and control. So for example, control information, or you have control packet. For that you are giving class selector 7 and class selector 6. Now the first column that you are seeing is COS, class of service or IP precedence. Starting from 0 going to 7, that means we have 8 option. So here the option number 8, that is 7, and option number 7, that is 6. The 7 and option 8 is for the control traffic. You can think for this point of time that is reserved. That is reserved for the system. Correct? Then you have high priority real-time traffic. Oops, let me clean this. So we have the high priority real-time traffic, and for that high priority real-time traffic, we should go and classify and do the marking. So let me go back. So again, you can see in this particular chart that you have class selector 5 EF, that is for voice. Likewise, class selector 4 and then AF, assured forwarding 41, 42, 43. So 41, 42, 43 means these are the high priority. So actually this chart is from high priority to low priority traffic. Likewise, you have the streaming video, mission critical, call signaling, class selector 3 starting from 31 to 33. Likewise, you can read this. Now, if you want to convert this in terms of bit, so here you have to go and check the bit. What you can do here, that here you can see that you have the DSCP. So obviously the first one is the default, so everything is 0. But the second one, that is the scavenger traffic, CS1 class selector 1. Again, you can see that one is for class selector 1, AF11, AF12, AF13. 8, 10, 12, 14, how you are getting this number? So you are getting this number starting from bit 3. So 1, 2, 3, 4. That means this is 2. It will start like this: 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. And since these bits are 0, 0, 0, so that's the reason you have 2 to the power 3 means 2 into 2 into 2, 4 into 2, that means 8. So that's why this is 8. Now how it is 10? 1 0 1 0, we know this binary will be 10, and then again 8 plus 4 will be 12. Likewise, suppose if you want to go and calculate this EF, how is this EF is 46. So that calculation here you can see that you have starting from here 1 0 1 1 1 0. So that means you have leave this. So you have 2 4 8 16 32. You are not taking this 16, so if you add this, 32 plus 8 is 40, 40 plus 4, 44 plus 2, 46. Like that you can check this, correct? This is the maths. You can pause the recording here and you complete this mathematics. Otherwise, whenever you want to write the code, you can go and take the snapshot of this particular slide and you can refer it all the time, correct? Or you can make your own slide like this as well. All right. What is the best practice? The best practice for QoS is that if you have QoS in hardware and software, you prefer QoS in hardware. First thing. Second thing, classify and mark application as close to their source. So do the classification and marking nearby the source, because it is easy to classify and mark nearby the source. You polish unwanted traffic, and if it is unwanted traffic, put into the default queue. Then enable queuing policy at every node with the potential for congestion. If you see that congestion is there you can go and enable the queuing. Correct? So very straightforward. Suppose if you are seeing congestion on all these three switches, you can go and enable that QoS there. Now this slide you can see that you have trusted port. So all these yellow color are trusted. Then you have conditional trusted endpoints. So you have IP camera or IP phone, etc. Those are the conditional trusted endpoint. And then you have printer you don't want to trust. Okay, so you can classify, you can mark in terms of trusted or untrusted. Here also, you can see that you can have yellow ones as trusted, then black one is not trusted, then green is conditional, and then this red one is the classification and marking. So what is the summary for these things is that you should know that where you have to trust, where you have to do classification and marking, where you have to apply the QoS policy, either ingress or the egress. Correct? Now suppose if you're dealing with the hardware type of QoS, and that QoS type with that particular switch model is 1P, 1P stands for priority, 3Q and 1 threshold. So in that case, you have one priority queue and you have three queue. So priority queue, obviously you are going to put the voice traffic or real-time traffic, and then you have three queue. In these three queue, you can go and classify your traffic. We'll see that in upcoming 3-4 slides. You'll see that how it can be utilized. So again, here you can see it's just next after this. We have, so for example, one priority queue, 3Q and 3T. Now this example is for one threshold, but here we have the three threshold values, and that's why you can see T1, T2, T3. So all the queues you have three threshold. Anyways, whatever number of thresholds you have with the queue, that is not a big thing. How you can apply this? Here you can see that you have the classification of traffic. So that's fixed thing you have, classification of traffic for scavenger, for bulk, for network management, for transactional data. Remember, this thing again mapped with QoS, how it is. So here you can see that scavenger, bulk data, you have CS1, AF11, 12, 13. Low priority to the high priority, and a related DSCP marking or DSCP table is 8, 10, 12, and 14. Okay, so while you are doing this, you should know the calculation. So for example, this is say low priority to high priority in this diagram, and in the last diagram that is up, actually this is low priority up to high priority down, and here it is a high priority up to low priority down. Okay, all right. So now here you can see that you have different classes. Obviously you have one priority queue. So let me show you that which particular category is falling inside priority queue. EF, CS5, CS4. Now here you can see that where is your EF is VoIP, CS5 is broadcast traffic, and then CS4, here you can see CS4 is real-time traffic. So these traffic are falling inside this. Then you have 3Q. So you have queue number 2. I can see queue number 2 here. You have queue number 4. And suppose you are using one queue as a default queue. Okay. So this is your queue number 3. So I have Q2, Q3, and Q4. Now Q2, I'm using CS2 up to CS7. Now again, it depends that inside Q2 you are putting threshold 3 as CS7, CS6, and then CS3 as a threshold 2, and rest of the AF assured forwarding 2, 3, 4 inside Q2 T1. Then Q3 you are using 35% as a default, and then finally you have Q4 you are using as AF4 and CS1. Now AF1 sorry, AF1 and CS1. You can go and check. This is used for scavenger. So I am giving 5% of traffic to Q4 for default traffic or for scavenger. AF1, here you can see the bulk data. So bulk data and scavenger, we are using 5% only. Means after that it will do the tail drop. But what is there in default queue? So here you can see that inside default queue, we have the default traffic. Default traffic I am using for default queue. So Q3 and Q4 actually is used for default and scavenger and bulk data. For that, I reserve 40% of traffic. Remaining 60% of traffic we are using for Q2 and priority queue. Okay. So this is the thing that you have to design the QoS before doing the actual implementation. Now, when you are doing the implementation, we know that this is MLS, multi-layer switch queuing methodology. So you have to go and enable the queue. You have to go and enable the trust model, conditional trust, service policy model, and then you have to apply it. Correct. So we have policy map, marking, mapping table, and weighted tail drop. How it look like? The first step for 2960 series switches are that enable QoS with command MLS QoS. Then the good thing that you can go and use COS DSCP, or directly you can use COS as well. We know COS, we know DSCP, both have mapping as well. So here you can see that COS mapping. If you have any doubt to understand this mapping, what you will do, you can go and check the reference slide. So where we have the reference slide, the first one here. So here you can see the COS to DSCP mapping, the column 1 and column 3, and actually technically column 2 and column 4. So 0, 8, 12, 0, 8, 10, 12, 14, 16, 18, 20, 22, etc. If I go here and see, I can clearly see that 0, 8, 16, 24, 32, 46, 48, and 56. That's the marking. If you are using the DSCP model, we can simply go and use MLS QoS trust DSCP. You can go and trust different type of Cisco devices like Cisco phone, CTS, IP camera, a media player. So this is the way that you can go and do the enable the QoS and do the DSCP marking. Again, here you can see that you can go and enable the DSCP marking. Now the next phase is that how you will go and enable the policy. You have to create the class map and policy map. Class map will be called inside policy map. So here you can see that I have class map called VoIP, media, signaling, transactional, bulk, and scavenger. Once I have all this class map, then I am calling this class map inside policy map one by one. So policy map VoIP set, again you can see we are setting the DSCP bit. So we are setting the DSCP EF for VoIP. We are setting for multimedia AF41, and again class signaling CS3, transactional data AF2. And when you are doing this thing, mapping, then this diagram will come into the picture. So according to your classification, your marking, you have to go and apply the policy. So obviously you have the classification of traffic, and then you are doing the DSCP marking while you are putting the policy. Now once I have complete policy, then I can go to the interface and then I can apply it like service policy input marking policy, and that's it. Okay. Now it seems little bit complex if you are new to QoS, but if you go a step by step that whatever we are following here, then you will find it that it's logical, and after few practice, or if you do little bit of practice, you'll find that QoS is a interesting topic to learn and do the mastery for. In this section, we are going to discuss about 3650, 3850, and 9300 platform. Here you can see that we have the trust model, means which particular interface is connected with what type of device you want to trust and you don't want to trust, or you have any conditional trust. Now in case of 3850 or 3650, we have these steps to follow. So when we are doing the ingress QoS model, we have trust DSCP/CoS model, conditional trust service policy model, and finally for the egress queuing, that is the hardware queue, we have 2P, 2 priority, 6 queue, and 3 threshold. So let's understand that ingress trust model. We can go and go to the interface, and then we have the CLI command, trust device, Cisco phone, CTS, IP camera, etc. Or we can use conditional trust. Example here, you can see that you can go and create the class map, say voice, whose cost value is 5, signaling, cost value is 3, and then you can go inside the policy map called Cisco IP phone, where you can call the class whose cost is 5, and then you mark the DSCP bit as EF. Likewise, you can call the class signaling, and then you can mark the DSCP as CS3. Obviously, then you have class default, set DSCP as a default. Then you can go to the interface and you can apply this policy. So we have option that which particular methodology we want to use for the classification, or at least for the trust model. Now, in the upcoming slides, I'm going to show you that how you're going to create the policy and apply over the hardware queue or over the queue model that we have is 2P, 6Q, 3 threshold or 3T. We know that we have the N bar supported in these hardwares, and N bars can have 1400 plus application recognition. When we are supporting N bar, at that time how we can create the class. So I can go and use, say for example, class map voice, and then I can match the protocol. That's the keyword, match the protocol, Cisco phone, Cisco Jabber, link audio, Citrix, etc, etc. If you go there, type match protocol and question mark, you will get a long list of application that is supported to that particular platform that you can match it. Apart from that, we can go and create other classes as well. This protocol is related to NBAR. So again, you can see that you have the broadcast video, match protocol, Cisco IP phone. You have the real-time interactive, the protocol is telepresence. Call signaling, the protocol is skinny. Telepresence control, the protocol is Citrix, SA, etc, etc. Okay, so we can do the classification of the traffic with respect to N bar, and then the next phase is to call those class map inside the policy map. So I can go to policy map, and then I can call the class voice. Now voice will call all these 4 protocols, and I'm setting the DSCP as EF. Likewise, we can create all this policy, and then we can apply over the interface. Correct. Now N bar, which is supporting 1400 plus application, and it is supporting 12 class model, and this is one of the reference we have. So here you can see that we have class voice, broadcast video, interactive, multimedia conferencing, multimedia streaming, signaling control, management, transactional data, bulk data scavenger. So 1 2 3 4 5 6 7 8 9 10 11, and let me show you the last one as well. So while you apply inside this policy, you can see that you have class voice, video, and all up to 11, and last is the class default. Okay, so you can have protocol matching with all of these classes, and then you can go and do the DSCP marking. Correct. So this is the way that we can efficiently use this N bar feature inside 3K platforms. Again, marking and policing, how we can do. So here you can see that the configuration related to marking and policing. So for example, I have class VLAN VoIP set EF, set DSCP as a EF, then police 1 to 8K, confirm action transmit, exceed action drop. So what is it? What does it mean? Again, the concept of policing you'll find at each and every point. So what you can do here, that you have, say for example, B sub C, confirm burst, and then you have B sub E, that is excessive burst. So what you want to do at this point of time, if you have confirm action, you are doing the transmit. So you transmit it, and then you have certain buffer. Exceed action, again exceed action, you have option that you want to transmit or drop, but in this case, say for example, I'm dropping. So B sub C, transmit, and excessive burst we can drop because we are using the policing. Likewise, you have all the policies, correct? So here you can see all these policy in the list for all the class of the traffic. Then for transactional data, you can see confirm action, exceed action, set DSCP transmit. DSCP table is table map. Then class bulk data and set DSCP transmit DSCP table as a table map. Then you have the table map, that is map of DSCP table, and here you can see that you are mapping 0 to 8, 10 to 8, 18 to 8, etc. Now if you see this diagram in this slide, you'll find that how it is called. So here we have the table map for 18 to 8, then you have table map for 10 to 8, and then finally you have the table map from 0 to 8. Okay, and obviously you have the class default, you have class scavenger, you have bulk data. For those you are using the table map as well. So this is the way that we can use the policing as well. Let me quickly go and show you the full policy configuration. In case of per port per VLAN policy, we have VLAN. So for example, match VLAN 110. Class map is DVLAN, that is 10. Again, you can go and call these class map inside the policy. Now what we can do, that rather using all the features that we have, we should standardize the configuration. Like we should create the class map like this, and then policy map like this, and then we should apply it. Okay, obviously if you want to do the policing, you can do the policing as well, and that's very much required as well. So let me quickly show you that how this queue look like and what will be the final configuration. Here you can see that because this is two priority, so you have priority queue 1 and priority queue 2. Then you have 1, 2, 3, 4, 5, 6. 6 queue with 3 threshold. And how we can map the traffic, this slide can be your reference slide, that how you are mapping your 2 priority and 6 queue. So for example, I have priority queue 1 and priority queue 2. Here you can see, let me try to highlight here. So here you can see that you have EF and the priority queue level 1 EF for VoIP, and then you have CS5 and CS4 for broadcast video, and then for real-time interactive. So you are using your priority queues 10% and 20% here. Then you should use your AF4. So AF4 is used for multimedia conferencing, where we are using the bandwidth remaining 10%, and then the weighted tail drop is in conjunction with both. Then we have AF3 for multimedia streaming, where bandwidth remaining percent, DSCP based weighted tail drop. You are using the tail drop, means whatever left over, it will start dropping. Then finally you have the transactional data. Then you have AF1, means you have bulk and scavenger. So like that, you can use all your queues in this manner. And if you draw the configuration, how it will be looking like. So here you can see that you have voice priority Q1 matching DSCP EF. So when you are creating the class map, you are matching the DSCP value. So you have class 1, 2, 3, 4, 5, 6, 7. 7 class plus 1 is default, so you have total 8 class. Now how you are utilizing those classes? So for example, policy map, the name of policy map is this, for example. Then class priority Q1, priority level 1, percentage of bandwidth 10. Then Q2, priority level 2, percentage of bandwidth is 20. This is very much like this, correct? So once you do that, then you have the other class, that is control management queue. If you go and check you have control management queue where you're mapping this high level class selectors. What you are doing for that, you're giving bandwidth percent remaining 10, and you are giving the buffer as well 10%. Now you are moving to the standardization. If you go at this point of time and if you check the SD-WAN quality of service configuration, you'll find they have structured in this manner, means even better than this, because same place you are getting all those things, and even you can do the configuration with GUI as well. Then you have the conferencing queue, 10% buffer, queue limit DSCP, remaining percent, 80%, 90%, etc. So the configuration, although here it is using the strict priority, the remaining bandwidth percent, the tail dropping, etc. So whatever you are seeing here, all the configurations you can drill down and you can check the same way we have the configuration here. So finally, for bulk data, we have bandwidth remaining percent 5, the queue buffer ratio is 10, queue limit DSCP is 80%, AF 11% is 90, means for the scavenger traffic. So when you have the scavenger traffic, you are using the DSCP based weighted tail drop, correct? So that's why you have the DSCP based weighted tail drop 80 and 90. So after that particular limit or point of time, they will start doing the tail dropping. And finally, you have this class default where you have the bandwidth percent remaining is 25%. So here you can see this bandwidth remaining percent is 25%. So this is the way you can design the uh, policy. So first of all, do the classification, then design the policy and you can apply it. Correct. So do the classification, create the policy, and before applying, suppose if you want to use the shaping as well, so you can do a nesting of policy as well. I can go and create one parent policy for 50 Mbps traffic, and I can map inside class default shape average. I can give this particular subline CIR for shaping, and then I can call my child policy inside the parent policy, and then the parent policy I can apply over the interface. Okay, so this is the standard way of doing the MQC, modular QoS CLI configuration, or even most of the iOS XE platform. We are creating the policies and applying the policy like this only. All right, so let's stop here. Now we are going to discuss rest of the platform. We have 4500, 6500 and 7K and 7700 platform. Whatever knowledge that we have gained so far, those knowledge we are going to use in these platform. So we need not worry to relearn all those things. Now directly here you can see that in case of 4500 platform, we have, so for example, one priority, 7 queue and one threshold. So overall we have 8 queue, out of that one is priority queue. And if you have 12 class model, here you have 12 classes. You can see that how these classes are mapped. So priority queue is mapped with EF, CS5 and CS4. And then here you can go and check what is CS5, what is CS4, what is EF. Likewise, then you have queue number 1, 2, 3, 4, 5, 6 and 7. So here you can see that Q1 is starting with default queue 25%, Q2 is uh, bandwidth remaining 1%, Q3 bandwidth remaining 4%, Q4 remaining 10%, 5 10%. Like that we have all the queue to class mapping, correct? So this is about the 4500 QoS design. Now inside 6500 and 6800 QoS design, you can see that again you have 12 class model and you have say 2 priority 6 queue, means you have 2 plus 6 queue plus you have 4 threshold. Here again you can see that Q1 up to Q6 and then 2 priority queue. So first of all you can figure out that how you are mapping priority queue level 1 and priority queue level 2. 1 and 2 we are using EF, CS4 and CS5. Then rest of the queues here have been used. Now, for example, AF4, which is using multimedia conferencing, it is used for multimedia conferencing queue where 20% is bandwidth remaining, and then we have a DSCP based weighted random early detection. So if you want to do congestion avoidance, you can use either tail drop or you can use a random early detection method that you start discarding the packet before you reach to certain threshold value. In AF3 also we have 20% bandwidth remaining plus weighted random early detection. In AF2 also like same, but in case of bulk data you can use 5% of bandwidth remaining percent because you don't want to give more bandwidth for bulk data, or maybe in case of a scavenger as well. Okay, so this is the model. This is actually the standard format, but if you want to change anything you can change as well. Okay, then finally we have the Nexus platform, and inside Nexus platform you can see that you have 4Q1T. Now this dual class model, again you have the costs. So for example you have 8E4 4Q 8Q in 1Q1 like that. Actually if you go and log into the Nexus platform, you'll find that you have so many inbuilt QoS, and it is recommended that do not change it until unless it is required. So how the mapping is, here you can see that you have Q1, you have Q2, you have Q3 and Q4. Q2 is used as a Q default, correct? So Q1 it is matching cost 567. Q0 obviously it is for default. Q3 is mapping cost 234. So if I start with cost 1, so cost 1 for Q4, and again you can check the subsequent mapping. So cost 1 is mapped with bulk data and scavenger. Best effort is mapped with cost 0, that is your default queue. Then here you can see that you have Q3 mapping with cost 2, 3 and 4. 2 is transactional data network management. 3 is, so here you can see the 3 is multimedia and signaling, and likewise all these queue have been mapped. So once we know this mapping and this queue methodology, obviously we can then go and write the syntax, write the software commands. That is again it's easy. Again here you can see that you have 4Q1T, 1T, how it is mapped here. Apart from this mapping, we are giving the bandwidth percent and the queue limit as well, bandwidth percent and queue limit as well, because we have one threshold as well. In 7700, where you have 8 queue and one threshold, it's very much that we have 6K design where you have 2 priority and 6 queue. But anyways, you have 8 queue, and how you're mapping the 8 queue. So first of all, you can go and check your priority traffic. Priority traffic is cost 5, 6 and 7 used for priority, and here you can see the cost values. Then you can see the Q2, 3, 4, 5, 6, 7, and then you have one default. All these 12 classes model, how they are mapped with Nexus 7700 F series line card. So this is the way that all these wired QoS can be used and mapped, and we have discussed a lot in detail each and every component and things inside the QoS. Now next section onward, we have to study QoS for wireless network or wireless infra as well. Last topic in section 1.6, we have WLAN QoS. Now WLAN QoS may become the weakest link in the chain because there are some, you can see that actually there are 3 primary reasons for that. Means there are some issues, or there means these WLANs are not that efficient that we have the wired LAN. So that's one of the reason. So here you can see the primary reason are typical downshift in speed and throughput. Here you don't have any dedicated pipe. You have some sort of shared media. Here you can see in the diagram, and all the mobile devices are devices who are using WLC, SSID, etc., they are using the shared network. One thing. The other thing here you can say that shift from full duplex to half duplex. So these are the issues, these are the constraints we have that may be causing the weakest link in the chain. The other important thing here to understand is that wireless LAN supporting 4 level of services. So if you have wired LAN, you have to map your, say for example, 8 class of wired LAN to 4 class of wireless LAN. So that is also one of the limitation you have. Now, because the wireless media, they are going to use a CSMA CA, that is collision avoidance mechanism. So there are chances, we'll see that in upcoming slides, that you have to wait for some period of time or a small duration of time, but that is a small fraction of time also can cause trouble. So for example, voice, if we have 15 millisecond jitter versus 5 millisecond of jitter, the improvement is 300%. Say for example, transactional data, 14 millisecond latency versus 2 millisecond of latency can have 700% performance issue or enhancement in performance. Both ways we can think. So these are the things that is considered for wireless media, and for that obviously we want to apply QS as well. What are the tools we have? We have the user priorities, and later we'll see that how we have to map DSCP to the user priority. We have access category, we have arbitration, inter frame spacing, we have contention windows. We'll see that AIFS and CW in next slide. What does it mean? But they are associated with some sort of collision avoidance mechanism. Then finally, you have enhanced distributed coordination function. We have to map the DSCP with user profile. You can define the trust boundaries. We have discussed about policy enforcement points earlier. So you have PEPs, and obviously the WLCs, they are supporting AVC as well, application visibility and control. Now here you will understand about AIFS and contention video. Since we are using CSMA/CA, that is the collision avoidance technique, uh, if you compare with the LAN technique, that is CSMA/CD, collision detection. So if collision will happen, then the algorithm will start recalculating the refresh interval, and then next time they will avoid. But here, this is by default, they will wait until they will find that the link is okay or the transmission is okay, means I can do the transmission if it's ready to send, right? So it's something like collision avoidance, and that's the reason that the sender have to wait for fixed amount of time, and that is nothing but AIFS. Correct. The other waiting time you have is the random amount of time, that is the contention window. So not only that you are waiting for fixed amount of time, but you have the contention window as well. And then finally, this AIFS and contention window timers vary by access category. So here you can see that you have access category as defined by voice, video, best effort, and background. Now this access category, you know that you have high priority to the low priority data, correct? And according to that, your access category in conjunction with AIFS, in conjunction with contention window minimum and max, everything will work together. So for example, here you can see in the diagram below, the background having the longest contention window plus the longest AIFS, rather than the voice has less contention window plus the AIFS, etc. So voice and video AIFS is same, but contention video for voice and videos are different. Let me quickly show that how these models are going to map. So you have 802.11 access category. You have access category for voice, video, best effort, and background. Likewise, wireless media mapping, you can see that you have voice video best effort background. If you are using Cisco AirOS WLC, you have this category like platinum, gold, silver, and bronze. Let me show you much more information related to that. So we know and we have a study about this model. This is our RFC 4594 based DSCP based model. Now, how you are going to map all these classes or traffic classes with the IEEE 802.11 model? You can have a reference for this particular slide. So in future, if you are designing the wireless QoS, you can map in the same way that you are seeing here. So for example, CS1 is mapped with UP1, AF1 is mapped with UP2, UP user priority 0 is mapped with best effort. So like that, you can go and check each and everything. Then we have the high priority data as well. So for example, multimedia conferencing or VoIP plus DSCP admin. So here you can see that VoIP plus DSCP admit is user priority 6, and this multimedia is user priority 4. So like that, the mapping should be happen. Now the next question here is that how the 3-bit user priority can map with the 6-bit DSCP. So in that case, when you have user priority to DSCP default mapping, here in the diagram you can see that you will map 3-bit and rest 3-bit will be zeroed. So they will mark as a 0. So in that way, the frame will processed, and obviously your actual header or actual DSCP marking will be kept inside the IP packet. So whenever you are marking your user priorities, that is going inside the cap map tunnel from your access point to the WLC. So here you can see the marking will be like this, and they will mark only last 3-bit. So user priority has 3-bit, that will be marked with the 3 last bit of the DSCP. Okay, and in this way the flow of frame will happen. Now, if you want to learn more about the QoS related to WLAN, you can go and check this RFC 4594, and also you have the Cisco validated design as well. So you can go and refer the design document from Cisco as well. Finally, we reached to section 1.7. This will be the last subsection actually of section 1. And what are the topics we have in 1.7? We have to understand about hardware and the software switching mechanism, how CEF, Cisco Express Forwarding working, what does it mean by TCAM, MAC addresses, and FIB versus RIB. So all these things we'll study step by step, and before coming to 1.7 A, B, and C, I just wanted to explain you about hardware architecture of 9300. Although we have a study in our QoS section that in Cisco, we have long list of switching platform. Obviously in routing platform is also there, but we have long list of products. Now, because this core exam and upcoming exams, Cisco keeping track, or they are thinking that in future people will go and in enterprise network they will use DNA, they will use SD-WAN. So when we are coming to DNA specifically, in DNA we should use DNA ready hardware, and that's the reason in the hardware section I just wanted to focus on 9300 hardware. Now this 9300 catalyst switch is security integrated, means you can enable MACsec and other security related things. Whatever there in the switch generation related to security, you'll find inside 9300. It's a mobility ready, it's a IoT ready, because we know that IoT is a big topic nowadays, and it's a even bigger topic in Cisco DNA, and it's ready for the cloud as well. So here you can see that you can connect with SDA, you have web UI, you have patchability, etc. So let's understand this 9300 and at least 3 to 4 very important features related to 9300. Now here you can see the family. So we have 1G data, uh, 9300 specifically. Even you can go and refer the data sheet as well. So you have 24 plus 48 port, then you have 1G unified PoE/PoE plus 24 port 48 ports, and then you have mgig UPoE switches. So first of all, at least one thing we can understand here, that they are PoE ready, and not only they are PoE ready. So here you can see that line rate on all port. They will give you line rate throughput on all the ports. All the ports are PoE ready. So you can connect in any port you can connect the uh, IP phones or Cisco phones, so it will get the power. Then you have 24 multi-gigabit Ethernet ports. Here you can see you have 10 gig, 5 gig, 2.5, 1 gig ports available. So you can see that port availability, PoE, line rate, everything is enhanced here. Now, which type of SFP models they are supporting? Here you can see that you have uh, online insertion and removal SFP supported, like 4 into 1 SFP or SFP slash SFP plus. You have QSFP as well, that is 2 into 40. Then finally you have the copper support as well. So 4 by 1, 2.5, 5 and 10 gig. Correct. So all sort of SFP, SFP plus and copper interfaces are supported. Now here you can see that we have the power capability, means what type of power modules you have. You have 350 watt AC up to 1100 watt AC. It's very much similar to Cisco 3850 switches. And then we can do the stacking as well. So a stacking capability is also there. When you are doing the stacking of the switches, then you can stack up to 8 members in a switch, and in that case obviously when we are doing the stacking, they have active and a standby feature. So someone is active and who is taking control for all the switches. So from there you can go and log into all the switches, and from active you have to configure the active, and rest of the members are supporting the active configuration. So that means we have the centralized control plane, we have distributed data plane, and that's the power of stacking. We have one-to-one stateful redundancy, and again, we have discussed this earlier, that we have a stateful switchover SSO, plus we have NSF, non-stop forwarding as well. So you have a stateful switchover, you have NSF. Let us continue our discussion about the innovation inside Catalyst 9300. Here you can see that it is built in RFID. Uh, apart from that, apart from uh, regular Catalyst switch like 3850 or any other platform, what extra you have? We are going to check and discuss about what extra capability we have inside 9300. At this point of time in the overview section, you can see that you have RFID, and I want to highlight this extra capability that we have in terms of ASIC. So here you can see, let me try to do a spotlight. We have flexible ASIC UADP 2.0, and that's the extra thing we have inside this 9300. Due to the ASIC is it's quite extensive, high performance, programmable, and it's actually amazing innovation from Cisco, that this unified access data plane ASIC, we have 3-4 slides for that we are going to discuss more about this. So here you can see that you have extensible ASIC, you have RFID capability, and then you have the line rate capability. So let's move on and see that what other features you have in terms of hardware. Obviously, we have discussed about the stack. So we can have a stack of 8, and we have NSF and SSO supported. That's okay. Now let's try to dig deeper inside the switch, and let's try to understand the core difference, that where 9300 is standing and moving onwards if we are comparing with the other catalyst switching platform. So you have this UADP, rest all the things you'll find same, like redundant power supply, power stack connection, fan FRU, back stack connection, USB. Rest everything is okay, but you have this UADP, that's the ASIC. Now let's discuss about this ASIC. Before moving to that ASIC, you can see that you have x86 CPU who can support different type of programming options. So they can host Puppet, Ceph, Wireshark, Ansible, iPerf, Kibana, Perf, Sonar, etc. So they have this debugging options, and they can integrate with any third-party vendor for API integration or programming. Yeah, so we are waiting for this ASIC study, and now you can see that we don't have the traditional ASIC where things are monolithic, although this new ASIC, this UADP, they can understand different type of encapsulation as well. Say in traditional ASIC, if you put load on the frame, means if you are doing some encapsulation, you have VXLAN encapsulation overhead, GRE encapsulation overhead, etc. Those are not supported because they are doing a normal lookup related to MAC, IPv4, ACL, QS, etc. But in the new UADP, you'll find that it is supporting most of the things. So here you can see that you have the architect, you have the RTL design, synthesis, floor planning, fabrication, etc. Everything is there inside this new chip, and this chip is looking like this. So you have UADP, Unified Access Data Plane, which will provide you high performance, flexibility, and programming. So we have PFP, performance, flexibility, programmability, and that's the reason that it is used inside Cisco DNA. It has investment protection, universal deployment, enhances scaling, and it can have 7.46 billion transistors. It is using 28 nm technology. This is actually very much related to the hardware features, correct? But yeah, the summary is this, that because we have very high capable data plane related ASICs, that's why the capability is very much good, and you can think this 9300 as a next generation catalyst switch. Apart from that, we have some key features that they have flex parser, programming pipelines, recirculation capability, micro engines, adaptable tables. Okay, and no compromise on performance. Although they are giving you lot of features and capability, but there is no compromise on performance. Finally, let's quickly see this architecture. So for example, we are seeing 930024 port layout. How it look like if we are new to this uh, hardware type of a structure. So how we can understand and read this, obviously you have IO module, input output module, means you have to give something in the input, correct? So maybe the end machine or PC, anything is connected. So let me try to mark here. So you have your PC and it is connected, or maybe you have some other switch and it is connected. So where it will be connected, obviously to the port. This is 24 ports, so 12 plus 12 port, it is divided like this. Then you have octal physical connections. So that means the ports are mapped to the octal physical. Obviously you have the network interface, then you have the forwarding controller, packet buffer. Now all these things, suppose if you have a stack of switches, then you have 480G stack interface, but all these things are mapped with the ASIC, and then you have your quad core CPU, you have your flash memory, USB management console, etc., etc. So you can study, or if you want to understand this design, go from bottom to top, and then you can understand more about this. Now quickly let me show you this multi-gig uh, Ethernet or multi-gigabit 9300, and here you can see this capability is even much more enhanced. So now you have 12 port unified PoE, and you have multi-gig quad physical. Multi-gig quad physical. You have core 0 and core 1 inside ASIC. You have core 0 and core 1 inside ASIC 0 and inside ASIC 1. Obviously, these are mapping with the unified access data plane. Here you can see this overall clock cycle. Then you can see this quad core CPU 1.8 gigahertz, and then you have a rest of flash memory and USB management, etc. Okay, so these are the hardware level details of the switch platform. I have covered 9300 because that's the catalyst switch that we are looking for in upcoming networking technology, and that's the innovation we have. Next topic, we have traditional MLS, multi-layer switching, and Ceph Cisco Express forwarding. So what's the fundamental here? The fundamental here is route once and switch many. And again, if you correlate this with the SD-WAN, means you have the control plane and data plane. Control plane who will take all the decision, and then the data plane, it will forward the packet. Correct? So here also you'll find that you have the control plane called route processor or RP, and then you have the data plane that is the switching engine, that is the SE. Route processor will take the decision, and then it will program the switching engine that now I have taken the decision, this is the source, this is the destination, and you need to forward the packets. This is the way that the forwarding will be very fast, and this is the way that the multi-layer switch or switches, they are providing the line rate speed. Correct? Now, Cisco Express forwarding, how it is working and what are the key components we have. Again, the core of Cisco Express forwarding is take the decision once, and then everyone will follow that decision. So route once means that you have the brain, and in the chassis type of architecture, the brain is the supervisor engine. So either we are using the Catalyst 6K or 4K or 4500 series switches. We have the supervisor engines who will take the decision, and then they will program the line card to forward the packet. If you have the fixed type of switch, so for example 3850, 3750, etc., so there also Ceph can be enabled in the hardware. Okay, so Ceph is the feature. Here you can see in the diagram and understand more, that will provide you the fast forwarding of the packets, because all the time the request is not going to the CPU. CPU will take the decision once. So you are punting the packet to the CPU, who is building the routing table and the ARP table, but they will program the switching engine, or they will program the line card where you have the dynamic engine called fib, and then you have the next hop adjacency, or you have IP to next hop mapping, from where the packet will move to the destination. Correct? So here in the diagram, clearly you can see that the different rows of all these components. Routing table, it will build the routing table, that's the route processor, and then you have the ARP table, that's the L3 to L2 mapping, that will resolve the MAC address. Now you have the dynamic entry, that's the fib table, forward information base, and that fib table will be arranged in a way that you have the longest prefix match to the lowest prefix match. That's the beauty of this fib table. And then finally, this fib, whatever information they have taken from the ARP table, so now you have IP to next hop mapping, or you know that who is your next hop agency, and then you can forward the packet as per layer 3 forwarding engine. Actually, this is the mechanism that MLS is using. So now you have different type of terms. You have routing information base, who will form forwarding information base in terms of longest prefix match. So that is the LPM. And then you have the ARP table that will do the L3 to L2 mapping, and then you have the adjacency table that will be used by the fib. Okay, so I have put all these points here. If you want to read these slides, you can read it. But whatever we are discussing, the same thing here also. Now, once you have your rib, once you have your ARP table, once you have your fib, once you have your adjacency table, if you want to verify, you can go and verify like show IP CEF. And if you want to check the CEF entries in detail, you have that detail option. So you can come to know that who is the network you are looking for if you want to check that particular network. So we have option that we can go and check the particular destination network. So for example, show IPsec prefix IP, and then if you want to check the longer prefix matches, because this fib entry or the CEF entry, they will be in a manner that they will have the longest match and then the least match. It's like that. Obviously, if you have the longest match, then only the fib entry, that will be the natural choice for the fib entry, that you have to check the next hop for the longest match, correct? All right, so in this way, this fib entry will come into the picture, and when you check the fib entry, you can see that you have multiple next hop like attached or in the same network in the other network. Again, it depends that who exactly is your next hop. According to that, they will build the table entry. Now, again, if you want to see this in detail, so you can go and check show IPsec, the network and detail, where you will go and get the detailed information about the agency, about the next hop, dependencies, etc. Okay. Now the next important thing we have is the agency table. So we know at this point of time that you have the fixed components. So for example, rib table, and then you have the ARP table. Now you have the dynamic entry as per the longest match, that is the fib table, and then you have the adjacency table. Now this adjacency table obviously will be taken from the ARP table. So ARP is doing L3 to L2 mapping, and then when fib, they are looking for their next hop entry, they are contacting the adjacency table, and then as per the longest match, they can get the next hop. Okay, so that's the thing we have, that's the important we have in the adjacency table, but there are so many other stuffs as well inside the adjacency table. If you want to check that, you have this option show adjacency table. You can go and check that. You have the summary and detail option as well. The adjacency table will be look like this. So first, you can see that first few numbers belonging to MAC address, and then rest of the keywords are there. But what is important there in the adjacency table is to understand a different type of keywords. So while you are checking your adjacency table, you will find that you have null adjacency. Now what does it mean by null adjacency is that used to switch packet destined for null interfaces. The null interfaces always is defined on a router or switch. It represents a logical interface that silently observes packet without actually forwarding it. So you may have null interfaces. They are not actively forwarding the packet from one place to other places, but they are silently uh, absorbing the packet. Then you have the drop adjacency. Obviously, drop adjacency, as name suggests, that they are going to drop the packet, and the reason may be you have encapsulation failure, unresolved address, unsupported protocols, no valid route presents, no valid adjacency, you have checksum error, etc. Now, if you want to go and check this drop adjacency, you have this option. You can go and type show CEF drop, and then you can check encapsulation failure, no route, etc., etc. Okay. Then the third one is discard adjacency. Discard adjacency means your next hop is discarded by some blocking rule, ACL rule, etc. Then finally you have the punt adjacency. Punt adjacency means that you don't have your adjacent table You don't have your next hop, and directly you are forwarding the packet towards the CPU or towards the route process. If you want, you can go and check show CIF no safe switched, means they are not safe switched, rather than they are CPU or the RP switched or RP processed. So according to that, you can go and check these important keywords. So here you can see that you have null urgency, you have drop urgency, you have discard and point urgency. Finally, when everything is happen and the packet is ready to go, so at that time the rewriting of packet will happen in the egress or when it is leaving to the switch or the router. So what are the things they will change? They will change the layer 2 destination. Obviously the layer 2 destination will be the next hop MAC address. They will go and change the layer 2 source address. That will be the egress MAC address of that particular interface. They will go and check the TTL, means they will go and decrement the TTL by 1. They will go and check the layer 3 IP checksum. They will go and check layer 2 checksum as well. So these are the things that the switch will check before actually sending the packet to the egress. Finally, SIF will be enabled. Nowadays it is enabled to all the routers, all the switches. But suppose if you want to disable SIF on certain platform, you have option. You can go and type no IP SIF. In some platform, we have to write no IP route cache or maybe both. Okay, so in this way, we can disable the SIF. So obviously everything will be handled from the CPU or from the routing process in this case. And this is not the recommended way, but sometimes for the sake of troubleshooting or some other reasons, we used to do this. All right, so let's stop here. This is the last session in section 1. We are going to verify the SIF and we'll see the TCAM as well. Let's discuss or start with the SIF verification. So first of all, what you can do, you can go to the CLI and you can run the command show IP interface VLAN and show IP interface and the interface name. Suppose if it is a VLAN interface, you can go and give the VLAN and the number. Here you will see that SIF is enabled. So that means this particular interface SIF is enabled. Although you have other important informations as well with this command. So this is very simple and easy to run command, and you'll get a lot of information related to that particular interface. To understand the SIF or to verify the SIF is enabled or not, to run the SIF command, we have show IP SIF command. If we run that command in the next hop column, you can see that you have receive, attach, and other information. So what does it mean? The first entry here, you can see that you have 000/32. This is nothing but suppose if you don't have the agency table, if you don't have next hop, then the packet will be pointed to the CPU or the route process. That's the first entry you have. Then suppose you have 192.168.199.0/24 and attached as a next hop. That means that this is your interface. That's why it is showing attached. Then again you can see that you have 199.0/32. That's the network. This network and this network is receive. So that means that uh, obviously your network, but the thing here is that this is a reserve entry. Here you can see the more explanation. So if it is .0/24 and if it is attached, means it is connected interface. If it's .0/32, that means it is a reserve for exact network or network address, and this is used to contain urgency for packets sent to network address. If the network is not directly connected, in this case there is no urgency and the entry is marked as a receive. So I think you understand that .0/32, this is for network. Then you have .1/32, and this is also a reserve entry. This is very much like host route /32 host route. So you have network route or you have network, you have host route, reserve entries. Then again you have .2. Dot 2 means that you may have dot 2 as your neighbor switch. So you are connected with your neighbor switch whose IP is dot 2. And then finally you have 255 slash 32. That is nothing but the broadcast address, and that is also marked as a receive, and this is also a reserve entry. If you want to know detail about CIF, you can go and check show IP CIF, and then the detail will get the detailed explanation. Now finally we have to understand about the TCAM resources. So here you can see that you have forwarding resources. Inside that you have MAC, host route, IGMP routes, LPM route, multicast route, SCT. Now this particular output or this particular reference is belonging to 9300 catalyst switch. In 9300 catalyst switch, you have output like this. Then in the TCAM resources, you can see that you have security ACL, QoS ACL, service ACL. Inside that you have PBR, NetFlow, SPAN, MACSAC, SecCop, Tunnel Lisp. And even you have the entities for NetFlow as well. Now here you can see the exact partition. So for forwarding resources, we have 32K reserved, the host route 24K, IGMP 8K, longest prefix match 8K, multicast route 8K, SGT 8K. And then again you can see and have a reference for the feature resources for TCAM entries as well. In bottom you have the NetFlow entries 64K ASIC as well. If you want to see this in detail, so you can go and run this command in Catalyst 9K show platform hardware FED fed switch active forward ASIC resource TCAM utilization 0. And here you can see that unicast MAC addresses, max value, use value, IGMP L2 directly or indirectly connected states, and all those informations we have in this particular output. So if you run this output, if you want to see the detail of this from the CLI, you can go and execute this command and get it. Finally, just for the reference, you have the default STM template network interface. You can see the forwarding resources and the TCAM resources and the reserve entries. All right, so let's stop here. In our enterprise core curriculum, section 2 is belonging to virtualization and the percentage is 10% weightage. Here you can see the topics related to little bit of VMware type of thing. Like you have to learn, understand hypervisor type 1, type 2, virtual machine, virtual switching. What I have done that I'm going to record small 14 videos, and I'll go a little bit beyond whatever there in syllabus just to our knowledge and study purpose. So you'll find it very informative, all these 14 videos that will cover actually not only the Cisco aspect of hypervisor, virtual machine and virtual switching, but the VMware aspect as well. So I'm going to touch both. Then we have 2.2 where we have to learn about VRF, GRE and IPsec tunneling. And then 2.3 we have Lisp and VXLAN. Now for Lisp and VXLAN, I'm going to upload the same video that we have done in section 1 for Lisp and VXLAN. So one video for Lisp and one video for VXLAN. So here 2.3a and b you'll find some sort of repetition in terms of just section 2.3a and b that we have already done inside section 1. Okay, so this particular section you'll find that it will go over very quickly, and you'll find this section also is very informative and it will add up your skill set and knowledge base. Then what is server and operating system? What's the basic definition of server? Server means that someone who is hosting services, someone who is providing services. But you can see that server, they have various components, and these servers, they are taking requests from the client. They are processing those requests and providing certain services. Now the server consists of the CPU, the internal storage, main memory, interface card. Means there is various input and output uh, processing. There is various components inside the server. uh, After processing those servers, they are providing the services, correct? Now, what is the main component, and to be very precise, what is the main software component we have inside the server is nothing but the operating system. Now, the operating system is someone who is the brain, and you can see the definition of operating system. A very standard definition is that operating system can define as software that control computer resources and provide common services for other computer program that run on top of it. So for example, in my laptop I have Windows operating system, and once I have Windows operating system, then I have different applications. So for example, I'm using Gmail, I'm using web browsing, I'm watching YouTube, I am uploading courses to Udemy, watching courses from different vendors, uploading courses to here and there, doing some chat, playing game. Means all those applications that is hosted and that is actually connected with the operating system. So operating system you can think as a boss who is providing the time slots, who is providing the instructions. So you can think that operating system in the core and a small programs, they are connected somehow with this main program, this operating system program, and then operating system, they have their own mechanism to provide time slot, to provide space, to provide computation, everything that is provided by operating system. So you can think this is the heart inside the server, and which is responsible for all to run all the other programs. Main vendors: Microsoft, Linux, FreeBSD, Apple, Android, Cisco iOS, Chrome, etc. Some of the operating system here, you can see the difference that they are used inside the laptop or server, etc. But some of the operating system, they are used inside the networking devices like routers, switches, firewall, etc. etc. Correct? Now here you can see the view of the operating system. So you have the kernel space, that is the low level programming, and that is the program that is associated with operating system. And then maybe I have user space and various applications like email, chatting, online, um, video game, etc., etc., etc. And these applications, that is program, these kernel programming, that is again the program, they are associated, and again these hardwares that you are seeing, so for example RAM, NIC, disk, they also have their own programs. So actually behind the scene, all the programs from high level language to low level language, they used to consult to each other with different type of messaging bus in between them, and they are providing the output as requested as an input. So we are giving some input, processing happening, that is the program is happening, message bus, they are receiving the instruction, and then they are providing the output. So that's the basic of the operating system. Next section we'll learn about that how this hypervisor operating system works, and they are helping us to reduce the overall cost, reduce, or we can say the more efficiently we can use the different type of hardware component or resources with help of emulated uh, features that we have inside the hypervisor program. What is virtualization? And with help of virtualization technique, what we are going to achieve. Last section we study about the servers and the definition of server and operating system. You think virtualization is a type of emulation where you have fixed hardware. On top of that, you can use some emulated program, and then you can install various operating system. So what is the traditional way to install an operating system? Say I have my laptop, I can go to my laptop. In that laptop, that is my fixed hardware inside that laptop, I have fixed CPU, memory, RAM,
etc. So I have my laptop, and on top of my laptop I can install operating systems. So for example, I'm using Windows operating system. Now think like this, that you have the hardware. So I have the hardware. On top of that, so let me write here hardware. On top of that, I can install some sort of emulated software. So I can install emulated software. This is actually termed as a hypervisor. So I can install a hypervisor on top of hardware, and now whatever, say for example, RAM, CPU, network interface card, memory, etc. you have, those fixed hardware they can use, and they can think that I have my own RAM, CPU, network card, memory, etc. I can install operating system 1, operating system 2, operating system 3. Obviously there should be some limit that how many operating system you can install. I'll write here N on top of the fixed hardware and the hypervisor. Now, if we use this particular emulation or emulated way to install the operating system, actually this is termed as a host. So on top of host, and in this course we are going to study about VMware hypervisor, that is nothing but ESXi. So on top of host, I am installing a various guest operating system. So these are nothing but guest operating system. And in this way, we can save a tremendous amount of hardware resources. And that's a term actually, something termed as a server virtualization. Now there is difference between the server virtualization and hardware virtualization, and you will understand this thing coming forward or going forward. So for example, when you uh, perfectly use the hardware resources, that is nothing but the server virtualization. And suppose if you know the term, so for example, unified computing system inside Cisco. So you have unified computing system. Inside that you can install so many servers with server profile, etc. That is one of the example of server virtualization. The other example, just now we have seen that you have one big hardware resource, and then you are installing some sort of hypervisor emulated software on that, and then you are installing the guest operating system. So that is the example of server virtualization. When we are talking about network virtualization, now it is everywhere. So this network virtualization is used, say for example, SDN solution. So for example, my SD-WAN is a type of network virtualization, or inside that I have network virtualization. So for example, Cisco application centric infrastructure, VMware NSX, these are using network virtualization concept. Uh, Easy example, can I give the easy example? Yes, the easiest one is the VRF, virtual routing forwarding. This is again a type of network virtualization. Okay, so virtualization technique means, now here you can see this is the example of server virtualization. You have, suppose if you have one hardware, one operating system, that is we are not using any type of virtualization, but you can use in between the hypervisor or the virtualization software that is known as a host. On top of host, we can have n number of operating systems. So here you can see OS, different operating system we are installing, and then on top of that we are installing the applications. So in this way we can reduce the cost, and it is actually quite efficient. Almost all the companies are using that way, this method only. Again, here you can see that you have multiple ESXi, so you may have host 1, host 2, host 3, few of the host having a few of the operating system or guest operating system, few of the host having few of the guest operating system. And suppose if you want to manage entire infrastructure, later on we'll see that how to manage the hypervisors, cluster of host, data center, etc. So we have one VMware popular tool or popular software or suite of software protocol suite, whatever you tell this is, you have one management layer that is a vSphere server and vSphere client. And in our lab also we are going to use the vSphere client to manage. So here you can see that you have the server and here you have the client, and with help of one web browser, one application, you can manage the entire big infrastructure. So now you can see the complexity has been reduced, the overall virtualization of hardware has been enhanced, and in this way companies they can save lot of money. So now what is the hypervisor? The definition of hypervisor is a hypervisor can be defined as a software that can emulate the hardware like CPU, memory, RAM, storage, etc. for the installation of guest operating system. In the context of server technology, a hypervisor is essentially a program that allows creation of virtual server. So whatever we have discussed, the same thing. Again, if you want to see this diagram, you can see that you have your server, your hardware, you put your operating system and the application. But in this way, you are not using the virtual way or you are not using the hardware resource efficiently. Instead of that, what you can do that you have your hardware, put the host or the hypervisor, and on top of that you put operating system and application. So easily you can enhance the performance, reduce the cost, better use of the hardware resources, single plane of management for different guest operating system or application, etc. Again, we have one more diagram here. You can see that you have one big framework. You have fixed hardware, the 86 architecture. You have your virtualized software here, and on top of that virtualized software, you are installing operating system application, operating system application, operating system application. Now all these CPU, RAM, NIC card, disk, whatever you are seeing here in the diagram, actually those are termed as a virtual RAM, virtual memory, virtual NIC, etc. So you have your real CPU, memory, NIC, disk, and on top of that you are using everything as a virtual. And that's the power of the hypervisor we have. In this course, basically we are going to focus on the VMware ESXi, but there are so many good vendors. There are vendors like VMware ESXi is a hypervisor, Microsoft Hyper-V. These are the popular vendors. Then we have the Linux KVM. These three are the topmost trending hypervisor. Apart from that, we have the Red Hat Citrix XenServer. This is also very popular, Citrix XenServer. We have Oracle VM. Then we have, we'll see later on that we have two type of hypervisor as well. Then you have Microsoft Windows Virtual PC, Oracle VM VirtualBox, Pallor Desktop for Mac. You have these many vendors who are providing these hypervisor softwares. So I hope you understand that what is the meaning of hypervisor, why we are using the hypervisor, and in long term how we can go and manage them. Let us quickly discuss that what type of hypervisors we have and what is the benefit we have with the hypervisor. So clearly you can see that in case of physical server, you have your hardware, operating system, and application. In type 1 type of hypervisor, you have your bare metal, your server. On top of that, you are installing the hypervisor, and then you have the guest operating system and the application. In type 2, you can see that you have the bare metal, or you have the server, operating system, and on top of operating system you are installing the hypervisor and the operating systems like the guest operating system and the host operating system. Now this type 1 is actually popular and it's quite hardware efficient. So this is the preferred hypervisor technology that we have, and most of the places that companies they are using the server. So you have the hardware, you have the host operating system, that is nothing but the hypervisor, you have guest operating system, and then you have the application. Now doing so, we have benefit. Let me quickly show you the benefits. We can reduce the capital and the operating cost, minimized or eliminated downtime, because in this case you may have redundant host. So suppose if one host go down, still you have your different host and your VM can move to that particular host. So that's why it is redundant, means you have the redundancy in terms of host, in terms of guest operating system plus the application redundancy. You will see the design and architecture of virtualization with respect to, say, for example, VMware, and you'll find that the downtime is reduced. Obviously, if your operation cost is less, your downtime is less, it will increase the productivity, efficiency, agility, and responsiveness. Faster provisioning of application, yes. We'll see that how easily you can install a guest operating system on top of host. It's very easy. You can do with few clicks. It has greater business continuity and disaster recovery. We have some mechanism, we have some methods that we can do the disaster recovery, and it will simplify the data center management, and that's the key. So when we are simplifying the things with higher efficiency, agility, more productivity with lower cost, that's the goal of all the businesses nowadays. Let us discuss about the virtual machine and try to understand that how we are going to install over the hypervisor. We'll see the installation lab in upcoming session, but here we'll try to understand that how it will be emulated over the hypervisor or over the ESXi. So now what is happening, that we know it is clear up to this point that I have the server on the top of server. So I have server. On top of that, I have ESXi or the hypervisor. And on top of that, we are going to install the operating system. Those are nothing but guest operating system. Now these guest operating system, whatever actual hardware is there, they are sharing. So inside that guest operating system, they have shared, or you can say that they have shared actual physical hardware in terms of virtual CPU, virtual RAM, virtual hard drive, virtual storage, virtual NIC. So everything is virtual. Whatever actual we have, all those emulated virtual hardware they have. That's the first thing. The second thing, and very important thing we'll see in the upcoming slide, is that everything is in form of folder. Okay, so here you can see I will log into the vSphere client and I'll show you that you'll find that the CPU is virtual CPU, virtual memory, virtual hard disk, everything is virtual here, correct? So I will log into that vSphere client. I'll show you. The next important thing here you can mark or highlight is that everything is in the form of folder. We'll see that. I'll show you that database and the folders inside that. But now let's see the terminology and the extension. So we have .vmdk extension. What is this? This is nothing but your internal storage. So your virtual disk internal storage having extension .vmdk, correct? Obviously VM is for virtual machine disk, that is internal. Then you have the swap memory, that extension is .vswap swp, and that is used for what? So here you can see that is used for virtual memory whenever the process running on the VM reaches the VRAM predefined limit. It's nothing but virtual memory. Virtual memory is swap, vswap. Virtual storage is v.mdk. Then you have the log. Why? So there in the .log extension, all stuffs related to troubleshooting purpose they will stored. So the file store all the information a VM produces for troubleshooting purpose. Then configuration, that will be stored inside .vmx. So here you can see .vmdk, .swap, .log, .vms. Why I am explaining this thing? Because when I log into the vSphere client, from there you can go and check these folders and extension. So once you are seeing .vmx, that means it is there for virtual RAM size, VNIC information, and other references for the other files. Then we have non-volatile RAM, that is .nvram extension. Again, the use of non-volatile RAM, here also the use is same. Correct? So these are the important extensions we have, but apart from that also you will see further more extensions. I took the snapshot from there from the file system, and here you can see that .nvram, .vmdk, .vmst, vmx, .log, etc. Okay. So what's a virtual machine? Virtual machine is nothing but a machine which is installed on top of hypervisor as a guest operating system. They are using the virtual resources. Actually, they are using the actual resource in terms of virtual resource to run their operating system, or you can not or but and you can install the application on top of operating systems. So let me quickly go and log into the vSphere client. From there I will show you the virtual machine, how it looks like, and the various type of file and folder system. Here I'm inside the vSphere client, and we'll see later on that what are these entries or items inside the dashboard. So think this is a vSphere client dashboard where you have host and cluster, virtual machine template, the storage, networking, content libraries, global inventory system, and other stuff. So we'll see that these things later on. At the moment I am focused upon only on the VM virtual machine. So what you can do, you can go and click VM and template. Once you click, you can see a list of VM over the ESXi over the hypervisor. We'll go and check ESXi and their architecture as well later on. But suppose this is the tiny Linux, and I want to see the summary, what type of virtual hardware it has, what type of emulated hardware it has. So here you can see the list of hardware, the VM hardware, the CPU, memory, network card. I will discuss more about network card later on, video card, VMCI, and the other hardware related stuffs. Storage area, memory uses, and CPU info, the IP address and the hypervisor. ESXi 02a corp.local. It is having 32-bit of Linux operating system. The hypervisor is ESXi 5.5. These are the tools that is running. Okay, so this is the hardware. Now if I want to see that their file and folder structure, I can go to the data store. It is attached with this particular data store, and I am very much looking for my tiny Linux file and folder system. Here on the top you can see you have this expand button. If you go and expand that, you can see it is coming up, and now if I go and click to tiny Linux, the folder will open, and inside this particular folder you can see all the extensions that we have discussed: .nvram, vmdk, vmx, log, etc. Correct? So this is the way that we can go and check few of the things inside that. Later on we'll study more and more about this, and we are going to learn each and everything. Let's go through the hypervisor architecture of VMware ESXi. Now in the diagram you can clearly see that there are multiple ways actually to do the management of the hypervisor and the associated guest operating system, etc. So suppose if we have cluster of hosts, say ESXi 1, 2, 3, and I will log into the vSphere client, and I'll show you that from one particular management plane, and that is nothing but a web browser, from single web browser with help of vSphere server, with help of vSphere client software, you can actually manage, or you are able to manage, the entire VMware infrastructure. That's the overview or the top view of the architecture of the VMware. This is the VMware client, that from where we are going to manage everything. This is the web browser, and here you can see that vSphere Web Client is a web browser based application that you can use to manage, monitor, and administrate the objects that make up your virtualized data center. And that's the key. See, from one application, I am going to manage the entire virtual data center. And that's the power we have from the VMware. And that's the reason that VMware increased so much in terms of software defined data center. So from a single software, you can manage the entire data center objects spread across the globe. Now here you can see that what are the things that we can do from the vSphere client. We can go and check the health, the status, performance of the objects. We can do the management and the administration commands from the vSphere object. We can create, configure, provision, and delete the vSphere object. So think everything that whatever guest operating systems we have on top of host or maybe cluster of host, everything can be managed from one application, and that application is nothing but vSphere Web Client. So vSphere Web Client, it's very popular in terms of vSphere client. So we are not telling okay vSphere Web Client, but vSphere client. From vSphere client, we are going to manage, monitor, organize, check the health, and there are so many things. Plus, we have so many added new application. From there, we can actually go and add certain new capabilities inside this management plane, inside this management web application. Correct? So once you log in, how it look like here, you can see that this is the navigation tree or the navigator. Then the second is the main content area. So what's the inventory list, host cluster, VM, storage, networking, content libraries, vRealize orchestrator. So many things we can go and check from here. Then on top you have the search bar. Now my login will be a little bit different because again we are using some new or the latest version of vSphere client. But more or less you can see that you have work in progress, you have alarm, you have recent task, etc. It will look like that. You can go to the home button where you will get the list of all those objects or all those operations that you want to check. Once you click the global inventory list, it will give you the inventory list related to data center, host, cluster, network, storage, virtual network. So all the objects associated with these variants or these operations you will get from the global inventory list. Likewise, I can go to the home. From there I can go to virtual machine. I can go and log to a individual virtual machine. I can go and check their summary, their hardware, their capabilities. You can see I can go and check their hardware things. If I want to add any new vNIC or the NIC card, I can go. You can see 1, 2, 3, all these things I will show you in the lab as well. So I can go click and I can add one new NIC. Once you add a new NIC, what will happen that you will find that that particular NIC, once you add, you can see the work inside the recent task and the progress also you can go and see. So work in progress, all those things you can go and verify. So let me quickly log into the vSphere client and let me walk you through all those things that just now we have seen. Alright, so I logged in inside the vSphere client, and here you can see the task, the navigation, the task here, the main content page, the navigation, the search, all those things. The home button also here in the menu is little bit different than what we have seen, but more or less is the same thing. Now what I can do, I can go click to the menu, I can go to the inventory list. Here you can see the objects related to a resource related to data center, host, cluster, resource pool, data stores, data store cluster, network, virtual distributed switch or port groups, etc. All those things we have here. Here I have the task and the alarm also. So I can see the task, I can see the alarm, and all right. So what I'll do, I'll go to the host. Once I am inside the host, actually I want to go inside the virtual machine. So let me go like this. You have multiple ways. You can click to the menu, you can click VM template, you can reach here, or you can click here. You can go to the global inventory list. Once you are inside the global inventory list, you can see your hosts are there. Once you are inside the host, likewise you can go one by one. Inside host also virtual machine, I can go here. I have the tiny URL. I can go back. That's the power we have with this management. I can tell this is the management plane, or I can tell that this is the management web client URL from where we are going to manage, or from where we are going to give the instruction to all the objects inside the VMware data center. Think like this is a data center. We are managing a data center from a web application. All right, so I want to go to the this Windows client, and let's see what is here inside this particular hypervisor. Remember, when I'm going to global inventory, host is nothing but the hypervisor. Inside this hypervisor, I have the guest operating system. So how many guest operating system you have? You have two guest operating system, Tiny Linux and the Windows. I want to go inside the Windows. Once you are inside the Windows, you can go and click here. You can have the summary. These are the hardwares. I want to add one of the hardware here. So I can go click edit setting. Once we are inside the edit setting, I want to add one network adapter. So let's add one of the network adapter. And here I'm not getting the network adapter in the bottom, but here you can see on top you have the add new device. So this is actually a little bit newer display we have. So you can go click add new device. What you want to add? You want to add the network adapter. Once you click add network adapter, you can see the new adapter option came up. I want to select that. What is your network? So it is asking about which particular distributed switch, and let's add this one. Once I add this, and this is showing the connected as well. Connected on power on, yep. And then what we'll do, simply click OK. And if you click the recent task, here you can see that task is on. Let me show you this 6 millisecond, and this is related to Windows. This is the way that you can actually go and see the recent task. So task is going on with the Windows 10. We have added one of the NIC card. Task is completed. So let me quickly do one more thing. Let me do one more time so you can understand. Add new device. Add one more network adapter. And VM reason 1, something like that will add. So I will go here and I'll click browse. VM reason 1. Okay. And see the task queued, completed. Have you seen that? It was queued and now it is completed. So now we have the two tasks. Here you can see in the taskbar. So this is the way that see how easily we have added one of the hardware component, one of the networking component. Like that, it's very easy. Just with help of few clicks, you can manage, operate, check the health. You can do each and everything from this particular vSphere client. In this section, we are going to install one virtual machine over ESXi. You can see the steps. You can go to the home, click VM and templates, then go to the data center. From there, in the bottom, you can go and select create new virtual machine. Then you will get one page where you have to follow the steps one by one. So you have to go and check that select a creation type. It's a new virtual machine or deploy from template, cloning, etc. Then you can go and check the name and the folder, what's the compute, what's the storage. So let me show you one by one all these things. So I'll go and give the web server 01 as a name, select which is the data center belongs to. Then you can go and give what's the compute. Say for example, this is belonging to ESXi 1 or 2 or 3. Then I can go and give the data store, say DSISCSI. Then a few of the other things that the check and the compatibility, etc. Once you do up to this step, then finally you have to go, and here you can see some of the slides are overlapping. So from here, from point number 2C, you can go here and see 2C. For example, I'll select this DS ISK01, and then in my case, my ESXi is 6.7, so I can go and select that. Then I'm going to use the same guest OS and the guest OS version. Once I do that, then I'll go and select the new CD and DVD drive as well. And then all the steps you can see 1, 2, 3, 4, 5. Once I do ready and complete, finish, that's it. Then once my web server will be showing there, what I will do right click and then I'll power on. So let me do one thing. Let me quickly log into the ESXi or the vSphere client, and from there I'll show you that how you can follow all these steps one by one. So let me quickly log in there. Alright, so I logged in inside my vSphere client. I can go to the menu, and here you can see VM and templates. Here also you can see the VM and templates. We have the shortcut key as well, Control Alt plus 3. Once you are here inside the client, if you go and click to the data center, and let me scroll down, let me expand this first, and here if I do right click here, you can see you have option to create add host, means you want to add new ESXi, you want to add new cluster, you want to create new folder, you want to create distributed switch. Later on we'll discuss about this. You want to create new virtual machine, or you have the OVF template. So here we want to create new virtual machine, and now you can see all the list and questionnaire we have. So create a new virtual machine. Yes, I want to create this. What's the name? So let's go here and give the name, say for example web server. So I'll give name as a server 01. What's the location? Here you can see I can go and check the location. That is nothing but site A data center. Next it is asking about the compute. I have a 1A and 2A. I will select 1A for the moment. Then the storage. Now I'll select the first one, that is the ISK01, and on top you can see that we have option data store default, vSAN and vVol, no requirement policy. So we'll leave this as default. We'll go next, and then the compatible 6.7, and later we'll use 6.7 at the moment. We'll go and click next. Now select a guest operating system. What type of operating system this is? This is a Linux, and I want to use OS 64-bit. So this is the family, this is the version, correct? We'll go next. Now the customized hardware, it is asking me that this is the hardware details. You have the CPU, 1 core, memory 2 GB, new hard disk 16 GB, iSCSI controller, new network connected. Here I want to add this new CD drive, DVD drive. I want to add this, say for example, data store ISO. So suppose if I add this, it is coming here, it is asking that what image you have inside the data store. You can see that you have Tiny, Linux, etc. In NFS, what images you have. In VM image, what images you have, correct? So actually I'm looking for that Photon image. So I'll do one thing, I'll do cancel here, and let me try to check what is there in the content library ISO.
Inside content library, you can see that I have Photon 2.0, and I will save this. Means I will select this and click OK. I'll make this as a connected, and rest of the options also you can see here. You can go to VM option also, you can see all those options. So we are almost done with the installation of the VM, and let's click finish it. Once you click finish it, you can go and check the task as well. So here you can see the task is going on, and you can see that you have the VM server, web server 01, that is at the moment powered off, and you have this launch remote console as well for this server. But before that, what I'll do, I'll go here and I'll do power on for this server. Once I power on, I can go and click launch remote console just to see that how it is working behind the scene. So now you can see that the install option has came to install from the CD DVD that we have attached. So let's quickly go through it. All right, and now you can see that it is in progress. You accept this, yes, and then the virtual disk is 16 GB. Okay, I am just pressing enter. This will erase the disk. Are you sure? Yes. We'll wait for a few seconds. I want to install this Photon minimal. Yes. Hypervisor optimize. Yes. And then it is asking about the host name. So I'll give the host name as a, for example, web server. So web server 01 is the host name, and then I should give the passwords. So let me give the password, a long password. Let me try to retype this password and confirm password. Now the installation is in progress. You can see all the installation steps is going on. Congratulations, Photon has been installed in 20 seconds. Press any key to continue to boot. So I'll go and press enter, and now it is booting up. We'll wait, and here it is. Alright, so here you can see that now I have the username and the password. So I'll go and give the username and the password that I have set earlier, and now we are in. So now we have the web server 01, and if I see the IP address, because it is connected with the DHCP, and if I know what's the outside IP address, so let me try to ping from here. Say the IP, I know the IP from the outside is 192.168.1.0.10, and this command is not found in this Photon. Now because we have done this minimum configuration, so that's why this ping by default is not installed. So let me try to install this ping feature, IP utils. Let me try to do that. Just in this case, what we have done, that we try to do the minimum installation, because our goal was to install a particular VM, and in the minimum install for the Photon, the ping was not supported. So I have used this tdnf install IP utils, and just to install this feature, and let me try now. Still the ping is not there. So never mind. What we can do, that we can do the full install, and in the full install this ping will work. So our task is done, that our installation is successful. Let me minimize this and let me show you here. So let me go out from here, and now you can see this is power on. We have launched the remote console as well to verify this, and now it is up and working. Alright, so we can stop here now. This particular session is very important because we are going to start virtual machine networking, VM networking, and there are so many nice terms that we should learn and know. So let's start this. Now you can see that what's the problem we have. So once we have the host and once we have the hypervisor, so we know that we have the say for example host, and on top of that we have operating system or the guest operating system. So I have server, host, and the guest operating system. Now problem here is, so let me try to draw here. The problem here is that once you have host and you have operating a guest operating system, the first problem is that which software element should control the physical network adapter drive. So here you have your physical network adapter in the server. Who will control that? The hypervisor or the guest operating system? Obviously hypervisor has to control, but how? That's the first thing. The second thing, that how should communication occur between VM and the external resource. So now in this diagram you can see that you have your VMs and you have your server as well. Now these servers may be connected with switch, so for example L2 or L3 switch, and then you may have a router or you may have external world. So now this VM, how this VM will come, because this VM has their virtual NIC. So the virtual NIC adapter will come to the server and then it will go to the outside. Here we have the diagram. In this diagram you can see clearly that how these VMs will go and communicate to the outside. This is nothing but south to north or north-south traffic. So how this will happen? That's the second point, second challenge. The third challenge is that how the host will communicate to each other. So inside that I may have, so for example 25 VMs. So how this east to west traffic or east to west communication happen, and who has the control over this communication? Correct? So those are the questions. The solution that VMware came with in early 2000, that once you install this particular host, this particular hypervisor, at that time you have network standard switch. So you have host standard switch or vSphere standard switch, VSS. Now once you have the VSS, that means this particular VSS, obviously they have the VNIC from the vSwitch. You can think this as a switch in between. So now this is the switch, and then this switch will control the east to west or north to south or south to north traffic, etc. Now once we have this particular standard switch or the standard switch in terms of vSphere or network standard switch, we'll see the problem. Further, we have some problem. So before going to that particular problem, let's see this particular diagram here. So here clearly we'll see that you have your physical infrastructure, and if I try to analyze this with a switch, you think like you have one switch and here you have north. Just to analyze this particular diagram, here you have south, means here you have server, virtual server. So here you have virtual server, and here you have, for example, outside world, a router domain. Now we can think like this particular standard virtual switch or virtual standard switch, that in Cisco domain we used to study about access port. So access VLAN 10, access VLAN 20, access VLAN 30, access VLAN 40, etc. Then you have one interface that is going towards the router, that is nothing but trunk. So you can think at the moment this trunk is nothing but your uplink going toward the external router domain, and then you have this access port. These access ports belonging to certain VMs, you can think this as a port group. We'll learn about port group in the upcoming section, but you think this as a port group, and you may have certain specific port groups as well, certain specific VM port as well, that may be used for management traffic, that may be used for fault tolerance, that may be used for vMotion. So here you can see that
the blue color is nothing but complete VM related ports, and there you have the uplink or your physical interfaces. So here you have port group related to management, port group related to vMotion, maybe port group related to fault tolerance, etc. Then you have port group related to test, port group related to production, and this is over one host. So this is nothing but host one, and same type of thing. That's a problem here. So if you want to scale up same type of port group with the same name, everything, you have to create across, say for example, if you have 25 hosts, 25 ESXi servers, then you have to go and create the same name throughout. And that's why we have evolved to the distributed virtual switch that we'll discuss later on. But yeah, here you can see the production, here you can see the test, the port group. So the attributes having common properties or common properties inside the same group, a group of common properties, anything you can tell, that's a port group. Then you have the vMotion, you have the management. So here you can see the uplink and you can see the downlink, or you can see the VM link. So this is nothing but my VM link, and this is nothing but my uplink. Everything is defined inside the port group. Common property, attribute group, or grouping of common property or common task things. So clearly you have, say, VM1, guest operating system 1, guest operating system 2, 3, and 4. 4 VMs. 2 of the VM, they are part of, for example, sales. 2 of the VMs, for example, they are part of HR. So they belong to HR, they belongs to sales. Like that, you can group the ports and you can connect with the virtual machines. Alright, so you can analyze like your normal Cisco world also like this, but again now at this time we should understand that virtually how they look like, correct? We should understand that those terms. Now what is the issue we have when we are using the standard switching system? In that you can see that the standard switch is created. So at the moment you will install ESXi, you have your VSS up and running. Now the problem here is each switch on every ESXi must be created and configured individual. So you have to go create, etc. This can be time consuming, although we can do some sort of automation, but it is taking some time to do this. The second thing, one important note when using vSphere standard switch and some of the high availability features with vCenter in the standard switch must be named. You have this naming convention. So your naming should be common throughout the vSphere domain. Okay, and then also note that the features like input out network IO control, LLDP network health check, and the backup and restore means some advanced features, they are not supported in the standard switch. So these are the issues we have, and that's why we want to use the distributed virtual switch. We'll see in upcoming sections. In this important section, we are going to study about a VMware vSphere port group. That's the port group and the standard switch or the vSwitch. So what is port group and what is the significance of the port group? Now in this section, we'll understand 100% about the port group and the standard switch. Next section, we'll go and perform the lab task. So what is happening? I'll give you one example. Suppose you have one VM, virtual machine, and it has the VNIC. Now likewise you have other VM, say VM2, this is VM1 and VM2. This has VNIC. Now what you can do that these particular interfaces, virtual NIC, you can connect with a port group. Now again, what is the port group? So port group having common properties. Port group having common policies. So suppose if these VMs related to HR, so you can go and set common properties, common attributes inside the port group,
And whenever you are associating different VMs to this particular port group, they are part of same port group. Okay. Now, one interesting thing, suppose if you know ACI, application centric infra, inside Cisco ACI, inside that we have concept of endpoint group, EPG. So suppose if you create VMM domain, and then if you go and create endpoint group, this endpoint group inside ACI is equal to port group as well. Now the concept of endpoint group is also same. You may have common EPG. So for example, EPG related to web or HR or sales, etc. Now those common EPGs, that means here uh, part of port group, or the port group is equivalent to endpoint group. Okay, so VMware port group and then Cisco has evaluated their endpoint group. Both are actually same. Common attribute, common properties. You can common properties interfaces, or interfaces that you are going to connect with the common properties. Those are nothing but the port group. Right. So what's the definition here? Let's see. So definition of vSwitch connectivity policy, which essentially define how the virtual device handle traffic that belongs to group of VM. In case of VMware vSphere, this policy is called as a port group. So you have one group where you are collecting all the ports, and this group having the policy that will be applicable to all the interfaces or all the ports connected inside this group, like that. Alright, so later I will log into the device and I'll show you how we can select or deselect the port group. With respect to this particular image that is here, you can see that I have, this is the vSwitch. I will log in and I'll show you all the properties in 6.7 vSphere client, and you will find the display is a bit different, but these policies or the properties will be the same. We'll see that in the upcoming recording. So they are belonging to, say for example, VLAN 105, then you have the security policy, traffic shaping, and the teaming. If I go back in the slide, so let me go back in the slide, here you can see that, let me go back one slide back. So here you can see that your vSwitch having security policy, traffic shaping, failover policies, and the VLAN tagged with that. We'll see that. We'll see that you have VM port group belonging to 100, and how we can we'll go and connect all these things. We'll see. So at the moment, just think common properties interfaces grouped inside a group, or common interfaces grouped together with the common policies and properties of the port group. I'll show you. I'll log into the VM, I'll go to the network adapter, and that network adapter I'll connect with the port group. This network adapter is nothing but virtual interface, VNIC. Alright, so we have already discussed that once you have the standard switch, at that time you have issues. What issues you have? That suppose if you have same type of port group, you have to go and create those port group in all the host. So host 1, host 2, host 3. Suppose you have HR here as a standard switch, you have to create here, everywhere. That's the problem. Means you can think like Cisco access switch. So all these VSS standard switches are working as a Cisco access switch, but again all the access switches are going to be connected with the distributed switch, and that's the term that we'll see later on, that what's the use case of the distributed switch. I have complete set of slides for that. We'll discuss inside that. But yeah, for the operational efficiency, to support new features, you need a distributed virtual switch, and inside that also you can go and attach the port groups. So port groups belonging to distributed switch we'll see later on. Alright, in this section mainly we are going to focus inside the standard switch. So how I can go and add the standard switch, I'll go and I'll show you all these steps. Now there are multiple ways to create the standard switch. First of all, we'll go to the host and see that do we have do we have a standard switch already? If not, then we'll go and add that. This is one of the way, but we have multiple ways. I'll show you different ways to go and add the network. So you can right click to the host, you can add the network. Once you go inside that, you'll find that what you want to add: VM kernel, physical network adapter, or virtual machine port group for a standard switch. Now VM kernel, clearly you'll see here that it belongs to vMotion. So vSphere, vMotion, iSCSI, NFS, FCOE, FT, that is the fault tolerance, and virtual SAN if you are creating the VM kernel. I'll show you all these ports, interfaces, port group, and switch, or the standard switch, in the upcoming recording. Then you may have the physical network adapter. A physical network adapter handles the network traffic to the other host on the network. Then you have the standard switch. A standard switch, and then we have the group for a standard switch. We'll see that. So suppose if you select the third option, then you will get the option either you want the existing standard switch or you have the new standard switch. You can go and add the adapters. So you can click unuse adapter, click plus sign, then you will get the option for the physical network adapter. You can use one adapter, two adapter. Once you have one and two adapter, you can use this up and down arrow. You can set the different networking parameters or the properties of the adapters. All these things I will show you. And finally, you can see that this network having label network label, and the VLAN at the moment is untagged VLAN 0. That's it. So this way we can create the standard switch. Now suppose if you want to go and edit something, I'll go and log in and I'll show you that you can edit the vSwitch also. Obviously you select the vSwitch, you have the pencil button here for the edit. You can go and edit. So you can go and change the properties. So for example, if I go and select, it is asking about what's the MTU, what's the security policy, what's the traffic shaping, teaming, and failover. All those things we can go and select one by one. But it's still, just for knowledge purpose, we are studying that, okay, we have the standard switch option or vSwitch option, but later and in the production, generally we are using the distributed virtual switch. So this is also an option we have that we can go and check. Likewise, in the next section, in the lab section, I'll go there and I'll show you that you can go and select the physical adapter as well. And this is the way I'm going to show you. So I will go to the dashboard first. From there, from the dashboard, I will go to the ESXi. Once you go there, you have this networking option. So you can go and check the virtual switch, VM kernel adapters, physical adapters, TCP IP configuration. Once you are inside the physical adapter, here you can see you have the add network options. You can go and check all these things. I will show you one by one, all these operations. Yeah. So what is the takeaway from this particular section is, the takeaway is that what is port group. You should understand what is port group, irrespective of virtual switch or a distributed virtual switch. The significance of port group is there. Means you are going to connect the interfaces or VNIC interfaces having common attribute properties with a same type of port group. Once you have the port group, that's the first thing that we study, the port group. Second thing we are going to study, or we have studied so far, or we have seen the slide says, how to create the standard switch. And then again, a few of the slides you can see that how you can go and edit the physical adapter as well. So all these things, when we see this in a lab, then we'll understand more than these slides. But still, these slides are just for your reference, that you can go and you can do any type of change. Say for example, if I understand that what's the theory behind all these port groups and the standard switch and the distributed virtual switch, then it's actually very easy and straightforward that we can use the GUI, and inside the GUI we can go and do all sort of changes. Correct? So here it is showing that how we can go and do the load balancing in between the physical adapters, say for example active or active standby, etc. Correct? So let's stop here, and in the next section, uh, I'm going to show you the port group and a standard switch, and we'll see that how we can edit, create, even if you want, we can delete also. Let us perform the lab task. So I want to make this particular video very clear that you understand what is meaning of host, what is meaning of physical interface, what is the uh, virtual or VM interface. So suppose I have one host. In this case, we have host 1 and host 2. Now here you should understand, I'll go and log in, I'll show you all those things. Now inside this host, few of the interfaces will be physical interfaces. So I'll mark this as a physical. We'll see both the hosts, they have their individual physical interfaces. We'll see that what is the physical interfaces. And these guys, they have their vSwitch, and these guys, they have their DVS. Now DVS will be common for all the hosts, correct? And that's the use of DVS. DVS having global view for all the host and the networking. But these hosts, they may have their local switch. So VSS, say for example, VS0, VS0. Now again, where we are going to use the port groups, that is also very important. So let's understand all these things. So let me go to the host and cluster. Inside host and cluster, if I go, let me walk you all these things. So I'm inside, say, host 1, and if I go and click, say for example, you have configured. So first of all, let's start with configuration. Inside configuration, you can see you have the networking tab here. Inside networking, you have virtual switch. So what type of switch I have inside the ESXi or the host? Virtual switch, VM kernel adapter, physical adapter, and TCP IP configuration. Now this VM kernel adapter, you think this is related to control plane traffic. Control plane traffic. This physical adapter that is going outside, this is nothing but uplink, correct? Control plane traffic, it is going outside like that. You have to think now. So you have the host, you have the control plane adapters, you have the uplink, and then you have the virtual switch where you are connecting your VM interfaces or VM NIC, or generally we are telling VNIC. We'll see, we have one diagram. We'll check that. So VNIC, virtual NICs, we are in VM, we have virtual NIC, we are connecting with the virtual switch. Now this switch, this virtual switch may be a standard switch or maybe distributed virtual switch, correct? So let me go and show you that. So I will go here and click virtual switch. Once I click that, you can see here inside virtual switch, you have two category of switch. One category is this distributed virtual switch. Other category is standard switch, that is the V switch. Now on the top you have the option, you can add network and add those switches, we'll see later on. But because this particular section is focused on vSwitch, standard switch, so we'll explore on that. But suppose if I go and click this distributed switch, let me expand this. Now here you can see that this particular virtual switch is connected with different type of network interfaces. So we have the ESXi region, it's just the name, belonging to VM kernel. This is not attached with any VM. So you have different networking, and these networking interfaces, you can think these networking interfaces nothing but as a port group, correct? So here you can see that you have one of the port group that is nothing but a VM region, VDSCOM. This is just the name. It attached with one of the virtual machine, that is Windows 10, correct? Now here you can see clearly that this Windows machine, this is a part of port group or the networking. They have their VNIC is connected here. that is pinned towards two uplink. Now these uplinks can do the NIC teaming, load balancing, etc. etc. So many features that we can achieve with the grouping of uplink. But this uplink that is inside one of the group, one of the networking, they are part of uplink region 01 network. So you have 1, 2, 3, 4 and 5 different type of network inside this particular distributed virtual switch, and the name of this particular distributed virtual switch is nothing but region A0 VDS comp. So before showing you this section that is the standard switch, I want to show you one very important thing. So if I go here and click networking, either you can go and click there or you can go to the menu and you have this networking. Either way is fine. So once you are inside the networking, you can see here that you have the switch. This is the DBS switch. Inside that you have the groups, correct? So inside that you can see that you have different network. This is the one way to see this. You can see distributed switch. This is actually the port group network. You have some uplink. So uplink having two hosts. This is the switch, and this particular switch is combined or can be combined with multiple hosts or the ESXi, correct? Now let's go back. We'll go to the cluster here, and inside the host, again I want to show you some other things. So suppose I'm jumping ahead of the time. Suppose in this place, if I go and click network, you can see here the network. So you can see you have the network distributed port group. You can say distributed port group. Then you have uplink port group. Then you have the standard network. We'll see this also. What does it belong to? One of the VM is part of this particular standard network. This is actually belonging to our switch, our standard switch. Then you have distributed port group, distributed port group. So you have port groups. You have uplink port group, and one VM network is there. This also I can think as a port group at the moment. It's like this. Now, before moving further, let's quickly go and check the vSwitch, because I'm very much interested in the vSwitch. So I'll go to host configuration and the vSwitch, and let's see the standard vSwitch. So now you have on a standard vSwitch, you can see one uplink and one of the VM, vNIC. So one vNIC connected with one uplink. This is nothing but Tiny Linux, correct? Now if you want to see more detail about this, you can go and check the MAC address adapter type. You can go and check the properties related to that. All these properties we'll discuss in the upcoming section. But yeah, what are the things you can do with the standard switch? Now you can put the security features like promiscuous MAC address changes for force transmit. By default, you can see these are the default settings. Traffic shaping option we can do. We have the NIC teaming. At the moment only one NIC is there, so we'll not do any load balancing type of thing or teaming type of thing, correct? So here you can clearly see that you think that you have your host one. Say this is my host one. Say host one. Let me write it one more time. Host one. This host having DVS, but this has a vSwitch as well. Now this vSwitch, and obviously you have the VM as well. One of the VM, that name is Tiny Linux. One of the VM port, that is nothing but vNIC, is connected with the vSwitch 0. And this vSwitch 0, you can see that they are tied with one of the uplink as well. The uplink is nothing but VMNIC2. Okay, so first of all, let's see that this particular guy, this particular host one, having how many uplinks. So if you want to see this, you have to go here to the physical adapter. You can see that it has 0, 1, 2 and 3. This 2 is connected with this particular access switch. For the moment, I'll give the name as an access switch. So this is your standard switch or access switch. Here you can see. But two other NICs, say for example, the physical link, say VM NIC 0 and VM NIC 1, they are connected with these DVS. So they are connected DVS, but still I have one VNIC that is called VM NIC 3 that is not assigned anywhere. So what I will do, I'll go and attach this guy here. Okay, so let's do this operation. I'll go and attach this leftover VNIC to the standard switch, and then we can do certain operations. Correct. But at the moment, I think that you are able to understand that how this local switching or how the access or the standard switch and DV is working. Correct. So here you can see you have this option of add the network, but I'll go to this switch. If I'm here in the virtual switch, I can click add network. When you're adding the network, again you can see now we are going in depth. Again you can see you have option to create VM kernel network adapter that is related to control traffic such as vMotion, ISKG, NFS, FCOE, fault tolerance, vSAN and host management. Other thing, you have the virtual machine port group for a standard switch. You have the physical network adapter. Because I am focused on virtual switch, so I'll do one thing, I'll use this. Now suppose if you want to create a new standard switch, you have option here that you can use the existing. So I can go and use this guy vSwitch 0, that is my existing switch, and then I'll go next. Now the network label, I'll leave this as default. I'll leave this VLAN ID as default. I'll click next. Ready to complete, finish. Now you can see, first of all, what I have shown you here is that I simply went on and added the extra network here. So I have added, say, VM network and then VM network 2. This is nothing but a local port group. You can think this is a local port group local to this particular vSwitch. So once I have created this, then what I will do here, so now we have two port group, local port group. I can go to the Tiny Linux here. If you go here, you can go here and you can click, do right click here, or you can go to the configure also. So Tiny Linux and configure, I think in configure also you should get the option related to add the VM, but we are not getting it here. Configuration, never mind. You have multiple ways to do the same thing. What you can do here, let me check the action also if I get, yeah. So you can do like this. You can go to the action, you can click edit setting, or you can do right click here. You can go to the edit settings, and now if you see here, browse, you can see your VM network 2 has been created. You can add this. So this is what we have done. Now let me go back to the network. First of all, now you can see that it is connected with network 2. So let me go back one more time because I want to add two network. So for that, what I can do here, that okay, I'll roll back to VM network first. This is with the local switch, and then add new device. Let me add one more network adapter, and this network adapter, this time I will add network number 2. Okay, so now what is happening, we can go and check the task as well. So we have successfully added extra network. Now when we are talking about these networks, even we'll see later on, not with the standard switch, because we are not going to do much things in the standard with respect to a standard switch. Whenever you see the production network, you will find only distributed virtual switches, and those are heavily used. So I'm not stretching much inside this, but still you can see that you can go and add the standard network. So if I go down here, you can see that now inside that we have two network here. What about adding physical network adapter? So let me go and add the physical adapter as well. And so let's do this. I'll go to the physical adapter. I have one of the physical adapter that is unused. I can click this. I can click edit, and let's see, edit. I can simply change the speed and reflex, but I'll do one thing. I'll add the network physical adapter. Let's add the physical adapter now, and physical adapter with the existing switch. I have this V switch. Okay, we'll go next. I have this. Let's click if I have any unused. Yes, so I want to add this VNIC 3 there. So now you'll see initially in that vSwitch we have one uplink. Now you have added one more uplink, and here's the trick. So what you want? Do you want active standby, or you want active like this? You can see all the properties, or you want to do the unused. So for example, I want active. Then you can see you have all sort of properties here, CDP, LLDP, all these options we have. We'll check this later on, but I can go next here, finish. So once I finish this, now you can see these two physical interfaces part of vSwitch. I'll go quickly back to the switch, and inside the switch you can see now you have two. You can see. So clearly you see that how I have added the VNIC, virtual NIC, and then added one interface inside the VM machine, and both the interfaces you can see here, they are part of the NIC or the port group, and then the port group related to physical interface, but it's the physical interface. Use as active. You have option, you can use this as a active standby as well. You can go and check the settings. So I hope you understand how we can do the operations related to networking. Now on the top you can see manage physical adapters, add the networking. So from here also you have the option. So multiple options you have when you are adding the VM kernel for this particular switch. So that option also you have. Okay, existing standard switch, if you are adding the VM kernel name, what is the IPv4 address, what's the use of this, it's the vMotion or whatever is the management interface, obtain IPv4 address automatically, or you have any address that you want to put, you have any subnet mask you want to put, you have the default gateway and all. I'm just showing it for an example. So enter a valid subnet mask. So I'll do one thing, I'll give 24. I'll do this thing, we'll use this notation, but it is not telling you that in which format you have to put, etc. And finish. This will fail because this is the wrong address and all, but let's see what error we are getting. So we can go and check the alarm and events as well, that what errors we are getting adding this particular VM kernel NIC. Occurred during host configuration, and we have error because that IP is not existing and the other stuff. But I'm just showing you that from here also you can add. If you want to edit anything, you can go and do the edit. So with respect to vSwitch, I can go and change the properties. I can go and change the security setting like MAC address changes, force transmit. We'll see all these things later on. What does mean? What is the overall? So for example, use of this and the definition of this we'll see in the upcoming slides. Load balancing method, you can see you have plenty of load balancing method like IP based, MAC based, virtual port, etc. Fallback, notify, and the failover order. Then if you want to click manage, you can do up and down. So this is actually all the operations related to local switch. And this actually we are not using much, but it's good that we understand that how we can add, delete, change, modify, etc., etc. So how we are doing n number of operations related to this. But our more focus will be on the distributed virtual switch. So let's stop here, and upcoming section will again learn more about the virtual networking. Let us discuss the port group properties. Here you can see that we have the properties, security, traffic shaping, and the teaming and the failover option. When we are inside security, we have promiscuous mode, MAC address change, and the force transmit. And the order that we can select, or the options that to select, is accept or reject, correct? So let's see one by one. In case of promiscuous mode, if it is uh, chosen as a reject, that means there is no effect. But if you accept this mode, that means you are detecting the frames with respect to whatever policy you have configured for that particular port group, or for that particular adapter inside the port group, correct? So if it is accept, that means you are detecting all the frames passing through the vSphere standard switch. You can see the default setting here. The default will be like this: promiscuous is reject, MAC address change, and the force transmit is accept, accept. So let's see what is there in the MAC address changes. In MAC address change, one thing to note here, that the vSphere, that is inside the VMX configuration file where they are storing the MAC address. So suppose if they see that any change inside the MAC address, means if you make this as a reject, if any change in the MAC address, they will start dropping the traffic. Rather, if you make this as a accept, that means in that case they will allow those frames. So what is happening here? Changing the MAC address from the guest OS has the intended effect. Frames sent to the altered MAC address are received by the virtual machine. So even the MAC address change is there, the frames will be passed. Force transmit, reject means, again, force means someone is doing some sort of spoofing in case of MAC address. So here what will happen, and this is again applied to the outbound frame. So any outbound frame with a source MAC address that is different from the one currently set in the adapter is dropped. So if while doing the transmission of the frames, it will see what's the source MAC address, what is set in the adapter, and if it is reject, it will drop that. If it is accept, it will allow that. So it depends that what security policies we have. According to that, we can accept or reject. Alright, traffic shaping, it's very much like Cisco configuration, Cisco traffic shaping, or the QoS configurations. What is happening here, that you have, say, average bandwidth, then you may have certain peak bandwidth, so say peak, and then if you are going or for some slice of time, if you are going little bit up, then you have burst traffic. Okay, so these are the normal actually option inside the Cisco QoS as well. What is the standard, what is the peak bandwidth, and how much you want to buffer in case of the burst. Okay, all right. Then we have the important thing, that is the load balancing option and the failover in case of teaming. So here you can see that we have multiple options. I think we have 6 load balancing options here. So let us see all those load balancing options one by one. So first load balancing option, here you can see that route based on the originating virtual port. Now what will happen, that the select an uplink based on the virtual port ID on the switch. So once they select the uplink, then they will stick some sort of pinning type of option. You have 2 or 3 uplink, you select one of the uplink and you are sticking with that. That's the default load balancing option we have. Then we have the route based IP hash and the MAC based IP hash. This is very much like if you are comparing this with the LACP port channel.
in switch when we are creating the ether channel. So at that time they can do route based, they can do uh, sorry, they can do IP MAC based, they can do IP MAC port address based. Means there are also so many load balancing methods in case of LSCP and PAGP, that is the Cisco Ether channel term. There are here also you can see that you have a route based IP hash, means you are checking the hash value of the source and the destination IP, and then you are sending the frames over the uplink. Then same thing with respect to MAC also we have. Then we have the load balancing option with respect to NIC load. So suppose if we have two NIC, one of the NIC having load 30%, one have 10%, automatically load will shift to the other NIC. So this is also a nice feature. Then we have explicit failover order, means according to the high interface number, suppose this is number 2, this is number 1, you are always pinned to number 2. So what is happening? Let me read. From the list of active adapters, always use the highest order uplink that passes the failover detection criteria. And this is no actual load balancing is performed in this option. Obviously, this is something like user defined. You can go and define the load balancing method. So once we have the load balancing methods, then what options we have? Rest of the options you can see we have the network failure detection, link status only or beacon related. Then you have notify switch and fallback. Link status means it's very flat. If link is up and down, it will tell us, oh, this particular link you are sending the traffic is down, use the other link. Then you have the beacon probing. This is a smart, intelligent way to detect the link status. So 1, 2, 3, whatever number of links we have, we are sending the probes after every 1 second, and we are checking that okay, link is up or not. And then if it is not up, obviously the traffic will go to the some other direction. Very much like we are doing in Cisco also, but generally we try to check the ISP link. So we have some sort of IP tracking SLA type of thing in Cisco. So you are checking one link up to with respect to other link, sending some sort of IP, ICMP, unreachable type of beacon or probes, and you're checking that link is up or not. If it is not, if it is unreachable, after every 1 second you're sending the probes with, say for example, hold down timer of 3 seconds or 5 seconds. If it is not responding, you can go to the other direction. Notify switch. We have this option, specify where the virtual switch notify the physical switch in case of failover. So if any failover, it will notify the switch. And then finally, you have this failover option. This is also very logical. Failover option, you have the fallback is set to yes if fallback is set to no. So suppose if you have two link and fallback is set to yes, suppose this link is down, this will become active. Suppose if this link will come back, this will become active standby in case of active standby. So whatever original state of the link was there, once it will get recovered, it will start forwarding the traffic. And that is not the case in the if the fallback is set to no. So what will happen, that two links are there, active standby, this is gone, this standby become active, or maybe active. So now he is the primary who is sending the traffic. Now suppose if this link will get restored, still it will sending the traffic until unless something will happen here, and then it will become active and sending the traffic. So these are the failover fallback options we have, and these are all the options we have inside the vSwitch. You can see still we have multiple options related to security, traffic shaping, teaming, and failover. This recording session is going to be very small. We are going to understand about a distributed virtual switch. And now suppose if you see this diagram, now this diagram is a little bit confusing, but let's come back to this diagram after this. So now if you see this particular diagram, you can see that the distributed virtual switch having host wide visibility. So all the hosts, they can connect with the distributed virtual switch, although these hosts, they have their own standard switch.
This particular own a standard switch, you can see that they have a VM kernel NIC, they have uplink, these are nothing but a physical link you can think, VM NIC as a uplink, and they have a VNIC, that is VM hosted NIC. So if I draw this diagram, you can understand, say you have guest operating system. This is nothing but the guest OS and hosted over the host. So you may have multiple guests. All these multiple guests, they may be part of this vSwitch. Here you can see, just for an example, it is shown like this, and they may be part of DVS. But what is interesting and important to note here is that you have VM kernel NIC, you have VM NIC, you have VNIC. So you have three different type of NIC. You have NIC for management, you have NIC for uplink, you have NIC for virtual machine, correct? And the difference here is that this distributed virtual switch has a global visibility. So it will be visible for all the hosts. Now here you can understand this diagram now. So let me change the color of my pen. Now here you can see that you have the physical interfaces here. Now these physical interfaces are nothing but VM NIC. So you have VM NIC 1, VM NIC 2, here you have VM NIC 1 for this, VM NIC 2 for this particular host. Like that you can think. And you can see the uplink. Now you have the VM. So this particular VM, what is the name? This is nothing but VNIC. So they are VNIC, they are VNIC, VNIC, VNIC. So they are VNIC, they are VNIC. Now you have the distributed virtual switch. Here we have the port group A, B, C, D, etc. Now in the diagram you can clearly see, suppose this A belong to HR. A is a placeholder for HR. So these two VMs, they are belonging to HR group. So these two guest operating system, they are, for example, HR server 1 or HR server 2. Okay, or generally we are giving this name like web server 1, web server 2. Okay, then you can see that you have VM, and here it's showing like this, but you have VM with multiple VNIC. So here I have VM with two VNIC. They are part of, for example, this is app server 01. Then you can see the other host inside the cluster. So they may be, all these hosts are part of DC cluster 01. So other side that VM, they have their VNIC. This guy having the VNIC, they are part of one of the other port group, that is nothing but DB. So this VM name is, say, DB, I'll write DB server 01. This is DB server 02. So now you can understand that you can group all those different VMs as per their attributes to the same type of port groups, and then you can apply certain rules, certain policies over the distributed virtual switch inside the port groups, and those will be applicable to all these endpoints or all these VMs. So here you can see the endpoint is nothing but your virtual machine. So either the traffic is going to east to west, or traffic is going from south to north or north to south, but when it is going outside, it is leaving the cluster, or when it is leaving the vSphere, at that time they are using the physical interfaces. So this is actually the important analogy, and I hope that you understand that. You please pause the recording and then you can check these definition. Whatever we have discussed so far, you'll find the same thing written here. Let us do the walkthrough of the distributed virtual switch. So we have one distributed virtual switch. I can go here, I can show you that what's the summary, how to do the
configuration inside this distributed virtual switch. So I can go here, I can select configuration, and then we can check the properties. Now here you can see clearly that you have properties related to general properties, advanced, discovery protocol, some sort of administrator contract or contact, sorry. These are the properties we have. I'll log into the switch and I'll show you all these options. Then you can go and view the topology. You can create the private VLAN. You can do the configuration related to NetFlow, port mirroring. You can go and do the configuration related to health check. So I'll show you all these options one by one. Suppose if you want to set some of the properties. So what you can do here, you can click to the configuration and then you can go to the properties. You can click edit. Once you click edit, then you will get the option general and advanced. In general, you can go change the name, you can go and change the total number of uplink ports, your IO control, you can make it disable, enable, you can put the description, correct? Then what is the meaning of uplink? You can add more number of uplink, you can add more number of ports, you can give this enable or disable for the IO control, you can put the description. Then suppose if you go inside the advanced option, here you can see the options related to MTU, multicast filter mode, discovery protocol, administration contract. Now MTU we can go increase or decrease, means depending upon the use case. But in multicast filter mode, you can see that you have two mode, basic and IGMP MLD snooping. Basic means from the IPv4 address, it will make out what is the MAC address, and then it will forward the traffic. In case of IGMP or MLD snooping, as per their IGMP membership, they will forward the traffic. Discovery protocol, we have two options, CDP, LLDP, and disable also. So suppose if you are using CDP, Cisco Discovery Protocol, you can see here the CDP, LLDP, and disable as well. So if you are using CDP, you have option that you are the listener, or you are advertising, or you are listening and advertising both. We can go to the health check and again we can click edit. Once you click edit, then you get the option related to VLAN and MTU. What is the state? What's the interval? These intervals are in minute. The teaming failover, what's the state? What's the interval? If you want, you can change those values, correct? So what I'm going to do before moving further, let me go log into the vSphere client and I'll show you all these options where we'll find. All right, so I logged in inside the vSphere client. What I can do, you have option. You can go to the menu. You can go and select the networking. From here also you can see the networking. So let's go and go inside the networking. Inside network, I want to check this switch. Inside switch summary, you can see that switch detail. So how many network you have? This is nothing but your port group. How many hosts you have, how many virtual machines are connected, how many ports are there. Then if you have any nodes, then if you have any tag, what features you have, we'll go and see all the features. So IO feature, NetFlow, you can see all these features are supported. NetFlow supported, LLTP supported, link aggregation control protocol, that is basic support, port mirroring supported, IGMP MLD snooping supported, health check supported, and then you have the custom attribute. So how you can go and configure this, go and click to the configure. We are inside the setting and properties. If I go click edit, here you can see that I can go and change the name. I can change the number of uplink ports. I'll leave this as 4. Then you have the IO control. You can enable, disable. If you want to put any description, you can put the description. Then we can go to this advanced option. We have the MTU option. Here you can see the multicast option, either the basic or IGMP MLD. Then the discovery protocol, we have option LLDP, CDP, disable. Then the operation, what operation you want. You want listen, advertise, both. We can go and give the administrator contract name and the other details. Apart from that, you can see inside the setting, I can go and check the topology. This thing actually we have checked earlier.
So earlier, uh, previously we went here and we have done the walkthrough. We have seen the port groups and the VM. Basically, they are nothing but uh, VNIC and VM kernel interfaces, and these are nothing but the uplink interfaces that's belonging to the physical interface. So you have the topology. Then if you want to create the private VLAN, like in Cisco, we have private VLAN type. So for example, a community, isolated, promiscuous, etc. So I can go and create VLAN inside VLAN that will work as a second. Here clearly you can see primary VLAN, secondary VLAN, VLAN type. So we can go click edit and we can define that. What's the primary VLAN you want to add? What's the secondary VLAN you want to add, etc. etc. Correct? And you can see the type is by default promiscuous, but here you have options. So let's see that the options that we have, it is creating. So once I click here plus, you can see I can go and change the number, say for example 30, and this is the secondary VLAN. What's the VLAN type you have? So if you click here, by default it is taking promiscuous, but I'll not go deep inside this. I will leave this at the moment as it is. So I have primary VLAN, I have secondary VLAN. You can see primary VLAN, secondary VLAN, both are 3030 like that. Then we have the NetFlow, very much similar to the Cisco configuration of NetFlow, who is the collector IP, collector port, what's the domain, switch IP address, and then you have the collector sampling, inactive or active timers, etc. Then we can do the mirroring. This is nothing but the span or ER span like in Cisco we have. So if I go and check the options, you can see clearly here that you have the port, distributed port mirroring, remote mirroring source, remote mirroring destination, encapsulated remote mirroring source. So we have all those options related to port mirroring. Finally, you can go and check the health alarm. So VLAN and MTU, teaming and failover. So I can go and check this health check, the state for VLAN and MTU. You can go and enable. This is for 1 minute teaming failover state. You can go and enable, you can click OK. This is the setting that we can go and do inside the vSwitch. Later on we'll add the rest of the things as well, but you can go log into the vSwitch, you can go and check most of the features, and here you can see the difference now with the standard switch and the distributed switch. In the distributed switch you have so many added features. So you have private VLAN, you have NetFlow, you have mirroring, health check, etc. So that's why this distributed virtual switch is actually important and popular in the production network. Now we are going to learn that how to create the distributed port group. It's actually very easy. I can go to the distributed virtual switch, right click, and then I can create this distributed port group. So I have that option. I can go and give any name. I will give any logical name. Then we have the configuration setting. What's the port binding option? It is static or femoral. What's the port allocation option? Is it elastic or fixed? Then number of ports, then the resource pool, VLAN, some advanced option. So what does it mean by port binding? Here you can see the first option is port binding. Either we can use a static, so statically the VM interfaces or VNIC, I can go and attach with the distributed port group, or there is no binding, that is the femoral port. Then in the port allocation, you can see you have the elastic option, you have fixed option. Elastic means that is the default option. By default, you have 8 port assigned. If that 8 port will get assigned, it will create again 8 ports. Fixed means the default number of ports is set to 8. No additional ports are created when all the port will get assigned or exhausted. The number of ports, we can go and give the number of ports. Then we have the option related to network resource pool. Why we are using this network resource pool? If you have created a network pool to help control traffic,
you can select this. Just for the control traffic, we have this option. Then in bottom, you can see you have the VLAN type. So VLAN type may be none, uh, trunking, private VLAN, etc. So whatever option we have over the interface to the VLAN, we can go and assign it, very much similar to Cisco interfaces where we have switchboard mode, access, trunk, and add some uh, VLAN over the trunk, etc. Then we have the private VLAN option also in the switch interfaces. So we have all those options. Then finally, you have the advanced option. Select this checkbox to customize the policy configuration for the new distributed port group. So if you want to customize, I can go here and use the advanced option. Here you can see advanced, check this, customize default policies configuration. So like that, we'll go and create the port group. Once you create that, you can go and check inside the VM networking. This new port group will be created. Now next, what we can do, we'll go to the topology section and we'll see that where exactly this port group is. You can go and check that port group. Not only you can check the port group, but what I will do in the activity that some of the VM with the VNIC I will assign with this particular port group, and then we can see that the VNIC, how they are mapped with the VM NIC or the uplink. Correct. So those things we can go and see. Also here you can see in the diagram that you have the VM kernel ports. You have the VM kernel port with the different port groups as well. All right, here you can see this tiny URL is the VNIC is mapped with the VM NIC. So let's log into the vSphere client and let's complete this task. All right, so I logged in inside the vSphere client and we are inside the VM network. We are inside the network option. So here you have the network. Here you can see that you have the distributed virtual switch. Simply go and do the right click. You can create the distributed port group. Yes, I want to create the port group, although I have option to import the port group, manage the distributed port group. So I don't want that. I can give the name, say I'm going to use this as a, say for example, I give name as a tiny web server group. Okay, location is this particular switch. That's okay. We'll go next. Then you can see the option. You have the port binding, a static or ephemeral, that is no binding. So static and binding, you have elastic and fixed option. By default you have the 8. After that it will go and add. Network resource pool for network control traffic, we'll leave it. VLAN type, I'll leave it as a none, but you have the VLAN trunking, and the private VLAN option. Customize default policy configuration. If you enable, then you can see that you have traffic shaping, teaming failover, monitoring, miscellaneous. All those customization option will get appeared. So I'll make this on, so we'll understand, we'll see all those options as well. We have already discussed about promiscuous MAC address and the force transmit. And let me go back. All is reject, reject, reject. I'll make this as a accept for the moment, as we have checked in our last section. Then the traffic shaping, at the moment I'll leave this as it is. Then you can see that you have 4 uplink, all are active. The default is route based on the originating virtual port. That's the load balancing default method. Then you have the network failure, link status. You have probe also. We have study about this. Notify switch, yes. Fallback, yes. So it will restore the original status of the interface if it will get fallbacked. Then monitoring, I will not use NetFlow at the moment, but if you want, you can go enable and then you can use it. At the moment, I'll make this as a disable. Then you have the miscellaneous option. Inside miscellaneous, block all ports. Option is yes or no. We'll leave this. Next. So now you have your distributed port group with all those options. And now here you can see that you have tiny web server. This is attached with 2 hosts, that is 2 hypervisors. Network protocol profile is not there.
Rest of the things are not there at the moment. So here you can see that it is attached with two hosts, but suppose if you want to attach the host here, we'll see that. I'll show you that how to do some sort of manipulation later on. At the moment, what I want to show at this point of time is that once you create the distributed port group, first of all, I want to go to the switch and I want to show you, let me go and show you the changes that happens. So if I go here, now I can see this that the network is 6. So 1, 2, 3, 4, 5, 6. 5 plus 1, initially it was 5. Rest of the things will leave this as same at the moment. I can go to the configuration. Inside the configuration, I want to show you this topology option. Once you are inside the topology, if I scroll down here, you can see here. So you have this tiny web server group as per the alphabetical order they have taken. So E, S, and then T, and then V. So now what I want to show here is the few of the port groups. So for example, this particular port group, that is VM regional A0 VDS comp, having two virtual machine, Tiny and the Windows. And now they are mapped. So they are mapped from here up to this point, correct? If you want to see the setting, you can see it. So what I want to do here, that I want to remove this Tiny and I want to attach this Tiny here. So you can see that the number of virtual machines will increase, correct? So that will be the valid test. What I can do here, multiple ways we have. I can go to the host cluster or maybe VM and templates, because I'm looking for the Tiny, Linux, and the two, both I am looking for. So what I can do here, I can go to the edit setting. That's the easiest way to reach there. I can go to the network controller. I can browse this, and now you can associate with the Tiny web server. Remember, port group is the same type of attributes, same type of properties that you are connecting your endpoint or the virtual machine interface to this particular group, correct? So I have done this. Once we've done this, then I'll click OK. Then I'll go to this Tiny 2 as well, and there also we'll go to the edit setting. Once we are here, instead of VM network, click browse, and then I'll go and use this Tiny web server group. Okay. Then we'll go back to the networking and we'll go to the switch, configure, and topology. We are already inside the topology. Now you can see this Tiny URL. Two are connected, correct? To VNIC, going to this particular uplink, and if you want to see this uplink and the associated host, so this host has these two uplinks, this host has these two uplinks, VMNIC 0001, like 0, 0 and 1, VMNIC 0 and 1, both the hosts having those. So like that, you can see that it is mapped. Few of the uplinks, 3 and 4, they are unused. Few of the uplinks are in use. So this is the way you can create the port group. Once you have the port group, how you can go and attach the VM interface with the port group. And if you want, you can go and verify from this particular configuration and topology option. All right. So I hope you understand up to this point. Let's stop here. Next section we'll do more lab related to this. Let us create a new distributed switch and then we'll add some ports and VM, etc. So let's try to complete this activity. So to create the new distributed switch, what you have to do, you can go to the data center. You can see I have the data center, and then I can do right click, but there are multiple ways to do the same thing. So I can do the right click here, and then I'm getting this option, create distributed switch. So inside distributed switch, we have the option to create it. Or suppose if you can import also, you can create new also. Then we'll go and give the name. We are using 6.6 and the ESXi version is 6.7 and later. So you'll get the option. What is the configuration option? How many uplinks you are putting? What is the IO control? What is the default port group? So create a default port group. The port group name is D port group. So with the switch, we are creating one default port group as well. Now, once you are here in the ready to complete, you can see the summary and then you can click finish. So now you can see how easy it is to create a DVS, distributed virtual switch. Simply we can go and with a few clicks, maybe 4 or 5 clicks, we can go and easily create a switch. Now once I have a switch, so what's the logic here now? That once you have the switch, and sometimes what is happening that we are importing that switch from the ACI. So inside ACI, when we are doing some sort of VMM integration, at that time we have that VMM. So I have created a virtual switch inside the ACI from ACI, application centric infra from Cisco. That vSphere, they will download that switch. So either that's the case, or like we have created the new switch here. In both the case, once you create the switch, then you have to add the host to this particular switch. So this is a flat switch without having any host attachment. So I can go and add host 1, host 2, host 3, etc. Correct? So once we have the switch, I want to add the host, the ESXi hypervisors. So here you can see I have a new VDS. I can click add and manage the host, add the host, manage host network, remove host. Now while you are adding the host to this particular switch, this is the switch we are going to add the host. You can see you have option that manage the physical adapter, manage the VM kernel adapter, manage the VM network, and then its summary. It's ready to complete. So one by one you go add the host. Here we have two hosts, ESXi1 and ESXi2. You can select both. You can add this with this particular switch. Once you add this switch, then you have this option called manage physical network. Now what you can do that whatever unused interfaces you have, physical interface, that is nothing but the VM NIC. We have discussed already this thing. You select this, assign uplink. So you have to select and assign as an uplink. You can go and select this. So here you can see that one of the uplink where I have the VM NIC 3 assigned. Like that we can go and assign it. Then apply the uplink assignment to the rest of the host. So this uplink will be assigned with both the host 1 and host 2. So here you can see that, okay, I'm assigning the uplink that is nothing but VMNIC 3 with host number 1, VMNIC 3 with host number 2. And that's why even in the previous section also you have seen that VMNIC 0, VMNIC1, they are part of host 1, and similarly VMNIC 0, VMNIC1, they are part of host 2 as well. So in this case what will happen that VMNIC3 also part of host 1 and VMNIC, nothing but the physical interface, also the part of host 2. This thing will happen, correct? But the moral of the story is that you select these interfaces, assign it, that's it. So you have to go select it. So suppose now you are selecting the VM kernel interfaces, you select this and assign it. Then it will be attached to the host. Alright, so like that we can go and attach. Then finally you can see that migrate the VM networking. So here you can see that few of the VM virtual machine, they are attached with other host. Few of the virtual machine, they are attached to the other host. If you want to do it now, you can do it, but later also I can come back and I can go back to the VM and I can do this association. So it's very easy and straightforward. Once you do that, ready to complete, and you are done. Once you do that, then you can go and verify as well. So I can go inside the VDS and I can check the host association. If VMs are associated, I can go and check the VMs. If you have the port groups, you can go and check the port groups, like that. configuration, we can go and check the topology and all. So this is the way that we can go and create the new virtual switch. So what I will do now, that I will go and log into the vSphere, and from there we'll go and create this. Alright, so I logged in inside the vSphere client, and what I can do here, you can see that you have the site A data center, and if you go and right click here, you can see you have add host, add cluster, etc. But what we want distributed switch, new distributed switch. So click there. What's the name? I can give any logical name, so I'll give this, say for example, VMM, and with other. I can give any name, correct? Okay, what's the location? This is located as the site A data center. No problem, we'll go next. Now you can see that we have the switch version and the ESXi version. That's okay. Then number of uplinks, the IO control is enable. The default port group, we want to use this default port group. If you want, you can change the name as well. So what I can do here, I can go back, I can use this name, I can come back here, and I will make this as a VMM distributed port group, so DPG, any name you can give. Then you can click next, and now you have the summary. Very easily you have created one more switch here. This particular switch having the network, so you can see here that you have the DPG and you have the uplink as well. So it's actually very interesting to go and verify the network related to this. I'll come to this topology as well, but if you go if you want to see here, you can see that you have the distributed port group. See, they have created with very default configuration, and we have the uplink port group. So whenever you are creating the new distributed virtual switch, at that time all your uplinks, whatever uplinks, so in this case we have, say for example, 4 uplinks. All those 4 uplinks, they are part of one port group. The name is very much similar that whatever we have given to the switch, and then you can see the name as well. So you can see the VMM with other DV uplink 262, and if I want to go inside that, we'll go and check more inside this also. But what is happening here, that those uplinks, so let me show you the topology so you will understand this, what I try to explain here. I can go to the switch and the topology. You can see all your 4 uplink that you have added, they are part of this port group. This is my, for example, this is my physical interface, correct? And then I have one port group. That port group is associated with or I am going to associate with the VM interfaces. So it will be used as a VNIC, and this will be used as a VMNIC, inside and outside. Very easy and straightforward. Now if you want to do any changes and all, everything we can go and do with this particular switch. All these options we have. So if you want to change any LSCP thing, you can go and change it. There is no problem. Load balancing and all options are there. If you want to add NetFlow, you can go and click add NetFlow configuration. There is no problem in that. So that's the thing. You can see that now if you compare with the standard switch and the DBS, you have plenty of options here that you don't have inside the standard switch, correct? So I very much here want to show you this topology because now we have the visual representation, correct? So what I want to do, I'll go to the VM and say for example Linux, Tiny Linux 2. This particular guy, if you go and check the network related to this guy, he is belonging to this particular port group, correct? Tiny Web Server group. What I want to do here, I'll right click here, I'll go to edit setting, and then this network adapter 1 I want to attach with the new group that we have created. So what is our group name? Let's see. Here you can see that storage tiny VM. I don't have that group here, correct? Why we don't have group showing here? Because the reason behind this, so once you created this DVS, the distributed virtual switch, and if you go to the host, you can see it is not attached with any of the host, any of the ESXi. So first of all, you should go and attach this with this host. So what you can do, simply right click here, and then you have option attach host. So let's see, we have the edit setting and all those things also, but we should get the option related to attach the host. And you can see add and manage host. We have this option. So what you want? You want to add host? Yes. Go next. What are the hosts you want to add? So go and click new host, and you can select one or both. Now with this particular switch, we are adding the host. The next option we have is manage physical adapter, correct? So what we can do here, I can click this VNIC 3 because this is free at the moment, and I'll click here, select this and click assign uplink. So if you do that, what will happen? Assign to uplink 1, both the host. So ESXi1 assign with 3 and ESXi2 will also assign with 3. So it should be like this, that both should be assigned here. If not, then you go and you select one by one like I have done. So now you can see that both the hosts are assigned. If you want to unassign, then that option is also there. So one by one, what you can do here, you select it and then assign uplink, and then scroll down and assign the uplink. Like that, we'll go next. I don't want to do anything related to VM kernel at the moment, but if you want, you have that option as well. We'll go next. Then migrate VM network. This migration we'll see later on. We'll go next, and finish. So now once I finish this, I can go and check the recent task. Now you can see the tasks both came here. Consume memory also you can see. What we can do now is that now we can go to the VMs. I'm interested to. Now you can go to the edit setting, and now you will see that port group option. So I'll go here and I can see this VMM with DPG. Click OK, and once you click OK, click connect. So let me do this. You can go and check the recent task. It is completed. If it is completed, then we will go back here and let's go back to the networking so I can show you the topology option. Now here, if you go and check the configuration topology, now you can see that you have the VM that is connected here, and if you want to see the uplink attached, which interface, so here you can see. Okay, so you're seeing this option. Now from scratch we created one distributed switch, and then we have created one port group, attached this port group with the VM. We went here, we have attached the uplinks here, and you can see how it can be done. Previously we have studied that how to change the settings with the uplink, how to change and play around with these port groups as well. So this is a way you can see that plenty of options are there related to this, and we can easily create and manipulate the distributed switches. All right, so let's stop here. In 2.2 and 2.3, we have to learn about VRF, GRE, IPsec tunneling, Lisp, and VXLAN. So let's start VRF, virtual routing and forwarding. what is the use of VRF? When you are creating virtual routing and forwarding instance, so at that time you can segregate or segment the routing table. So for example, you have one global routing table, and then you may have a routing table for segmented, or for example, you can think like for customer A, you have one, customer B, you have one, customer C, you have one, like that. So it's like segmentation in routing. And what's the use case for that? So you may have business VPN services, network segmentation, data center access, etc. Now, this term that VRF that we are seeing here is actually layer 3 virtualization in terms of routing. But if you see and verify that, do you have any layer 2 virtualization technique? Yes, we have VLAN, virtual LAN, as a layer 2 virtualization technique where you have, say for example, every VLAN having their own spanning tree instance. Every VLAN has its own MAC forwarding table. Likewise, if you go and check VRF, you'll find that all the VRFs, they have their own CIF, they have their own routing processes. Means most of the routing protocols, they are supporting VRF. And in the diagram, you can see that you have one global table, and then you can have VRF. So what we are doing that we are creating a VRF, and then we are associating that VRF to one of the L3 interface. So that means that one L3 interface, or one interface specifically, can have only one VRF. And later in the lab section, you'll come to know about this. Now we have various techniques related to VRF to provide fast switching or fast pathing. VRF Lite and then MPLS. MPLS is quite a bit popular. So what's the idea behind this is that you may have end-to-end segmentation. So suppose if I have diagram, so here you can see that maybe you have one end where you have VRF A and VRF B, and then you want this segregation, or you want this virtual routing forwarding instance to propagate throughout the network, means end-to-end routing instance or end-to-end segmentation. Now, if you go and use VRF Lite, so in that case, whatever devices you have in between, here you can see, although you have only one switch in between, but it is showing green and red, means you have two VRF, two routing forwarding instance, two inside process, or two virtualization inside one box. We can think like that. So the idea here is that if you are using VRF Lite, then you have to go and enable VRF Lite to all the devices. And that's the problem, that VRF Lite, although they are very easy to use, but they are not scalable. So that's the reason we are using MPLS, multi-protocol label switching, where again you are using LDP as a protocol to create the labels and then to exchange the label. Okay, so this is one of the use of the VRF. Although we are going to have, so we are going to perform one lab, and in that lab you will see use of this VRF or front door VRF with IPsec and with the tunneling method. So we have that lab. At this point of time, VRF is a technique where you can create or where you can divide a global routing table into a small independent routing tables, and all these VRFs, they are holding their own forwarding table and the route process. Okay, if you want to propagate it end to end, you can use VRF Lite, but in that case you have to enable VRF Lite and those VRF to all the devices in between. One other thing here, you can see that this VRF, they are supporting encapsulation as well, that is 802.1q. All right, so this is the things related to VRF. We can stop here, and in next section we are going to learn about GRE. Next topic, we have generic routing encapsulation. What's the use of generic routing encapsulation is that you can create the tunnel from one place to other place with the use of GRE. Now, the interesting thing about this GRE is that as long as you have IP reachability and you don't want to expose your intermediate devices, you can create a GRE tunnel from one place to other place. Now, maybe we can think at this point of time, okay, I'm creating the GRE tunnel, so what about security? Now, we can integrate GRE with IPsec as well. We can integrate GRE with IKE as well. So in the lab section, I will show you that not only that will create the tunnel in between two endpoints, so whatever intermediate devices we have, uh, we are going to create tunnel on top of that. The source and destination tunnel will be the endpoints of the source and destinations egress interfaces. In this case, what we are achieving is, first of all, that we don't want to go hop by hop and take the routing decision, although we are directly reaching from one tunnel endpoint to the other tunnel. So we are creating the tunnel. Then for security reason, for security purpose, we can integrate our GRE with IPsec as well. So both the things or both the features we are achieving here, we are doing the routing, we are doing the IPsec as well. Originally it was developed by Cisco, but later on it becomes industry standard. And later on in this session, I'll show you the packet format as well. Here you can see that the usefulness of GR is that you can integrate with IPsec for security reason, first thing. Second thing, one of the great advantages of GRE is that it allows routing of IP packet between private IPv4 network which are separated over public IPv4 internet. So that is also very interesting use case we have, that you can create the GRE in between the private and the public network as well. Okay. Now this GRE also supports encapsulating IPv4 broadcast and multicast traffic. So these are the high level features we have for GRE, how this packet format will look like, taken from the RFC 1701, this GRE header. So here you can see that you have certain flags. Let me quickly go and highlight those flags. So we have flag says C, checksum, route, key, sequence, source route. Then we have this recurrence is something like a recursive route. So it is written in short like recur, but this is for recursive route. Then you have the flags, you have version, what protocol type you have. So for example, if you are using IP packet, then what will be the protocol type? Checksum. Now interesting thing here, so that's the reason I'm highlighting this thing, that this checksum, if you have checksum, this field will become 1. If we have routing, this field will become 1. If we have authentication key, this will become 1. If we have GRE sequence, this field will become 1. Okay. Although I have the explanation in the upcoming slides, so let me quickly show you that. You have the checksum, see routing present, that will become R. So here you can see R and routing means if your flag is 1, that means you have the routing. If you set the key for authentication, then key flag will become 1. If you have the sequence number for the packets, then this S flag will become 1, and here you can see the sequence number for the GRE packets. Correct. Again, if you have a strict source route, then the small s will become 1. For recursion, control and version number, generally they are set to be 0. A protocol type for IP field, it is set to 0800. Means suppose if you are doing the packet capture to understand that what type of packet is it, if you are getting 0800, that means it's GRE IP packet. Then the checksum, then the key and the sequence number, same that we have discussed. All right. So let's finally discuss the packet format, the normal packet or original IP packet, how it look like, and then when you are doing the GRE encapsulation, how it look like. So once you do the GRE encapsulation, here you can see that your original packet, so you have the your original IP TCP UDP application layer. On top of that, you are putting the GRE header, and then you have the outer IP header. Okay, so now you can think like this, that you have the inner header, and then you have the outer header. Inner header, that's your actual IP and your payload, and the outer header is the encapsulation with GRE with the tunnel IP addresses. All right, so let's stop here, and next section we'll start IPsec. Next topic we have IP security. Nowadays you will see that almost all the companies, they are using IPsec, because nowadays we are sending our corporate traffic over internet or public media. So at that time we have to take security measures, like we should provide the authentication, confidentiality, integrity, key management, etc. Now the popular term is CIA, C for confidentiality, I for integrity, and A for authentication. Confidentiality means that your data packet is not seen by other. You are sending encrypted packets. So if someone is still, if they are spoofing the packet, or somehow they have those packets or those files, still they are unable, or it's very difficult to decrypt and get the value of that data. Integrity means it is not altered by others. So whatever you are sending, whatever data you are sending, that other side, they are getting the same information. Authentication means you have the valid source, and maybe you have the valid destination as well. Means two parties, they are authenticating and then they are exchanging the data. Now here you can see in the diagram that you may have two types of IPsec. So IPsec actually has two flavor. One is a remote access VPN, where you are putting the VPN client inside the machine, or maybe it's a client or less, or maybe client full, or you are using site-to-site VPN. Now this site-to-site or point-to-point VPN may be point-to-point or slash point to multi-point. So either it's a IPsec, or it may be DMVPN, or any other type of advanced IPsec methodology. What's the fundamental behind this? That any case you are doing the encryption, you are doing the authentication of the packets, and then you are sending the data from one place to other place. Now IPsec is actually a suite of protocol. It's not an individual thing. It is an umbrella where you have so many other things as well. So you have IPsec here, but you have ESP, or authentication header. ESP is nothing but encapsulating security payload, and the supporting things, we'll see that you have, say for example, phase 1 and phase 2. In phase 1 you have ISA-KEMP policy, say Internet Security Association Key Management Protocol, and phase 2 actually you have IPsec itself, and we are telling it as a transform set policy. You'll see that. So you have phase 1 and phase 2. Inside phase 1 again, you have so many things that you can do in transform set, where actually you are moving the data with help of either ESP or authentication header. Here also you can put various security parameters that I'm going to show you in the coming slide. So let me quickly go and show you phase 1. What are the things you can put? Say for example, in phase 1 you can put the encryption, either days, triple days, or AES. Again, AES having bits, say AES, advanced encryption standard, etc., where you have bit either 128 or 192 or 256. Again, tighter the security, tighter way or tighter encryption methodologies we are using. You can use hash MD5. You can use authentication either pre-share or you can use certificates as well. Then you have the group, Diffie-Hellman group, and inside Diffie-Hellman group, again you have options to choose. All right, so this is phase one where exactly you're building the framework, and then you have phase two, that is the IPsec transform set or IPsec transport, where you are sending the data with the header, so ESP header, and again you are doing the combination of encryption, you are using MD5, HMAC, etc. So phase one and phase two, if you go and check the IPsec there, you will find that not only you have the phase one and phase two. So suppose you have completed ISACMP, and suppose I have two devices. In between, I want to create IPsec tunnel. So you should know, first of all, you should have IP reachability in between these devices. And suppose outside IP here is 111 and here is, for example, 11.1.1.1. So these outside interface should ping to each other, and over these interfaces, you are going to create, or we are going to apply the IPsec policy actually. So phase two is IPsec, for example. Then you have to create the ACL. So what type of interesting traffic you have that you want to put inside the IPsec tunnel. Or for that you are creating the IPsec tunnel. Then fourth number, that you have to go and create the crypto map. Inside crypto map, you can define the ACL, you can define the peer, you can define the transform set, correct? And finally, you have to apply over the interface. So these are the steps, but the phase is phase one and phase two. All right, so let's quickly go and check other theoretical aspect. So you have security architecture. Inside security architecture, you have two security header, AH and ESP. We'll go and discuss more about those parameters. Then you have the security association. All the tunnel, they are associated with security parameter index, that is SPI. But this security association having three component: SPI, destination address, and security protocol. Okay, and now this security association have a database of security association, determine IPsec processing for sender, determine IPsec decoding for destination. Essays are not fixed, generated and customized per flow. So per flow, you will find if you go and check the security association for phase one and phase two. Actually, for phase two, you can go and check show crypto IPsec essay. We'll see that later on in the lab section. You can check that SPI indexes. Now they can up to 32 bits large, and according to the agreement with the header, what are the things you have inside security association? Inside security association, you have SPI, destination IP, IPsec protocol, either AH or ESP. Correct? So that's about security association. Now let's quickly discuss about AH and ESP, authentication header. It is used for data integrity. Entire packet has not been tampered with authentication. Can trust IP address source. Use MAC to authenticate. Symmetric encryption like this. One-way hash also. They can use anti-reply. They can use integrity check values as well. So what does it mean? Let me quickly show you here in the diagram that this is the actual IPv4 packet. Now you have two mode to use IPsec. You can use transport mode, you can use tunnel mode, correct? Now transport mode is that you are not changing the IP. So whatever IP you have, you can see the packet is going with the original IP. So what you are doing, that you have data, you have TCP field, and then you are putting the authentication header. You are sending with the actual IP, correct? But in case of tunnel mode, and that's the preferred mode, we should use tunnel mode, that cover entire original packet. So here you can see in the diagram, we are covering entire packet Then we are putting this authentication header, and then we are sending the new IP header. That's the difference, but still you can see that we are doing the authentication for packet. So that's why the need of ESP, encapsulating security payload, that will provide message content confidentiality. uh, Again, this is coming with the encryption, so we are putting extra thing, that is the encryption. Provide limited traffic flow confidentiality, can optionally provide the same authentication header service as AH, support a range of ciphers. So they are robust than AH. They are supporting DIS, triple DIS, RC5, IDEA, CAST, etc. A variant of DIS most common, pad to mid block size for traffic flow. Now here you can see original data, then transport and the tunnel mode. And you can see that we should use this tunnel mode, because when we are using the tunnel mode, then we are changing the IP, means we are protecting the IP as well, because whatever actual payload we have, so here you can see that you have the payload and original IP, and then you have the ESP header. So up to your original IP you are doing the encryption, and up to your ESP you are doing the authentication. Correct. So here we are providing both the features, encryption and authentication, and that's why the ESP is the preferred way that we can do in the phase 2. All right, so remember that we should use the tunnel mode because we want to use uh, gateway to gateway, or we want to encrypt our IP from one gateway to other gateway. We are in the lab section. What we have to do in the lab, you can see the topology diagram here. We have 3 routers. Router number 2 will work as a transit router. So what I'm going to do here is that I'm going to provide the IP addresses over these physical interfaces, and then router 1 and router 3, I'm going to create first of all normal tunnel with respect to front door VRF. So we are going to learn about VRF, about how to create the tunnel. Once we have the VRF, once we have the tunnel created, once we have the IGP up and running, after that I will go and add the IPsec configuration. So whatever we have studied in these sections, these sections like VRF, GRE and IPsec, everything you can see here in this lab section. So let me go and log into the devices. Alright, so we have 3 routers here. You can see router number 1, 2 and 3. And let me show you the IP addresses over these interfaces. So I can go here and type show IP interface brief, and you can check that. So what I have done, that I have created one interface as per the topology and assign the IP. Let me quickly go to the loopback 0 and assign the IP address there as well. Say for example 10.111.10.10.1/24, and you should give like the subnet mask. Alright, so we have the IP address assigned here over the loopback interface, over the physical interface. Let's do the rest of the configuration. So what I want here, first of all, I want to create one VRF. Say name of VRF, I am giving say front door VRF. So front door VRF is the VRF. Now if you go inside that, you can see that you have options that you can define: export, import, route distinguisher, route target, etc. At the moment, what I want to do, that this particular VRF I want to assign to the physical interface. So what physical interface we have here? Now here you can see that we have physical interface gig 0/1, and we have assigned the IP address as well to that interface. Now if you go to gig interface 0/1, And if you assign this, say for example, IPVRF forwarding front door VRF, so FVRF, you will see that it will erase the IP address over that interface. So that means you have to give that particular address one more time, correct? And that's the important point we have. Now if I go and check show IP interface brief, and if I check show VRF, so now here you can see that you have the VRF, and we haven't defined any import export RD route distinguisher or any other things on this. All right, so these are very basic and very initial steps that we are doing at this point of time. So what we have done, that we have created the VRF name called front door VRF or FVRF. We have assigned to one of the physical interface. We have one loopback interface as well. Next, what I want to do, that I want to create one tunnel. So let me quickly show you the diagram. We have this topology, and I want to create one tunnel interface as well, and I'll give the IP 192.168. So let's go and create one tunnel, say tunnel 0, and the IP address is 192.168 1.1 255.255.255.0. This is the tunnel source IP actually. Now over this tunnel, what I want to do, that tunnel source is obviously my physical interface. And what's my physical interface? Gig 0/1. And what will be the tunnel destination? Now tunnel destination I haven't assigned yet, but if you go to R3 and if you check the tunnel interface, that is 222.3. That's the tunnel destination for router number 1. So this will be the tunnel destination, and tunnel VRF is front door VRF. That's the name actually. All right. Now once I created this tunnel, I can go and check the tunnel configuration. This is the tunnel configuration, and then you can go and check the tunnel interface. Now if you go here and check the tunnel interface, the loopback is tunnel, and tunnel protocol is, here you can see that protocol is GRE and transport is IP. So by default, whenever you are creating the tunnel, that will be GRE. Okay. All right. So once we have the interface configured, once we have the tunnel configured, then we should give the routing as well. For this routing protocol, I'm going to use, say for example, EIGRP in this case. So I'll go and start EIGRP. What network we have? We have one network, say 10.10.10.0, and I can give the wildcard like this. Then I have other network 1.0, and I'll give the wildcard like this. I'll do not assembly. So one last thing I have to do, that for front door VRF, I should create a route for that as well. So I'll create one static route for my front door VRF, FVRF, and that is default route pointing towards the gateway. Okay, so here you can see section IP route, or I can go and do include IP route just to check the IP route command, and then we can go and check the GRP as well, and then we can go and check the tunnel 0 configuration as well. So these are the configuration that we have done for router number 1, that is source of the tunnel. Likewise, I'll go and configure the router 2, that is going to become the transit. So here if I come and if I check show IP interface brief, this is a transit router and we have already assigned the IP addresses, so no need to do any further things to that. Now we'll go to router number 3 and we can do the same thing that we have done for router number 1. So here we can follow the process or follow the steps. IPVRF is the name, and then obviously I'll go to 0/1 and then I will forward to front VRF. Then I'll go and assign the IP one more time, and we can verify that. So this is the step number 1. Then in step number 2, that I want to create a tunnel. So interface tunnel 0, IP address for this tunnel as per our diagram. Say IP address is 192.168.1.3.255.255.255.0. Now once we are inside the tunnel, I can give tunnel source as gig 0/1. Tunnel destination will be 1111, correct? That is router number 1 physical interface. And then finally, tunnel VRF is FVRF, and we are very much done. So this is step number 2. I can go and check interface tunnel 0, and here you can see this configuration. Likewise, here you can see the configuration. So we have almost same identical configuration matching. I'll quickly go and enable the EIGRP process. We know the network here. So what network we have? I have network, say 192.168.1.0.000.255. That is one network. And other network is that I want to give this loopback, that is 30.30.30.0. If you go to router number 1, here you can see that you're advertising your loopback, you're advertising your tunnel. Alright, so we are very much done, and next thing we have to do, that we should create one default route for the transit router. So that is IP route VRF, front door VRF 000, and what will be the IP for these interface? That is this IP. Alright, so we have created this tunnel. I can see that tunnel is up and we are getting the agency as well. So if we go and check show IP EIGRP neighbors, show IP route, and we are getting the routes. Likewise, if I go here and check show IP route EIGRP1, you can see that they are receiving the route. So this is the very first basic step that we are doing here. We are enabling the VRF, and then we are checking the GRE as well. So you can go and check show interface tunnel, and here you can see that your encapsulation is GRE. This point you can see the source and destination as well. So let's stop here, and in the next section I'll go and add the IPsec configuration in this. We can continue our lab, and now we can add the IPsec profiles in this. So let's start with router number 1. What I can do here, first of all, I'll go and create the keyring. So here you can see that you have crypto and you have this keyring. I can give the name for this as well. So GRE IPsec is the name, and VRF is front VRF. Okay. What's the key you want to give? So pre-share key, and the address for the destination is so 2.2.2.3, and the key I will use, for example, Cisco. Okay, great. Now once we have this keyring, then I'll go and create the ASICemp policy. So let's go and create that. Alright, it's a bit slow. We can wait here. Alright, it's back. So now what we can do, that we can go and create the ASICemp policy. So for example 10, and then I can go and use the authentication as pre-share. Okay. Now once we have the keyring, once we have the ASICemp policy, next I want to create the profile for the ASICemp. So let's create the crypto ASICemp profile, and the name of profile I want to give, say, GRE IPsec. Okay. So a profile is deemed incomplete until it's matched the identity statement. So we'll go here inside the profile and we'll give the keyring. So keyring is GRE IPsec, and then match identity for the address 222.3, that's the destination address, and then 255.255.255 for front door VRF. So what we have done so far, let me quickly show you that we have created ASICemp configuration, and we have created the keyring as well. So better I will use crypto. From crypto you can see everything that we have created. So first of all, we have created this keyring, then we have created ASICemp policy, and then we have created ASICemp profile. Correct. Now these commands we can copy and then we can reuse inside R3 as well, and we can change the address and we can use it. So let's complete. So now we have the ASICemp policy. Next we know that we should create the transform set. So we can go to crypto IPsec transform set, and this also I can give the name as GRE IPsec, but we can give different name as per the standard. I can go and use, say, ESP, and what options we have, say for example DES, and we can give the mode as well. At the moment I'll use mode as a transport. Now we have phase 1 configure, now we have phase 2 configure. Finally I'll go and create the profile for IPsec as well, because this profile I'm going to map inside the tunnel. So crypto IPsec profile, and name also I'll give the same, GRE IPsec. What are the things we can set here? So transform set is GRE IPsec, and then the ASICemp profile is GRE IPsec. We are very much done. Let's quickly check the configuration, show run, and then section crypto, because everything is starting with crypto. Here it is. So we have created the keyring policy, then ASICemp profile, then transform set profile, and then obviously the IPsec transform set profile. So this is the configuration. Finally, what we need to do here is that we should go to interface tunnel 0, and inside interface tunnel 0 we can go and match this. So I can go here, use tunnel protection. Once I'm inside tunnel protection, then I can go and apply it. Tunnel protection, and then you can see IPsec profile, that is GRE IPsec. Okay, so I'm not using shared at this point of time because this will solve my purpose. Great. So what we can do here, that now we can go and use this section crypto. What it is telling, this log here, you can see that you have this GRE. You are sending some encrypted packet, but you are not receiving, etc. Because one side you have uh, created this configuration, but other side you haven't done anything. So what we'll do here, we'll go and open the notepad, and we know that other side the IP will be 1111. Rest everything will be the same, correct? So we'll copy and paste this configuration to here, and we'll go to interface tunnel 0, and here also we'll run this tunnel protection IPsec profile GRE IPsec. Alright, so this is the way that we can go and do the configuration. Now you can see this, we are getting the up message. So we can stop here, and next section we can do, or we can run few of the verification commands. Let us run a few of the verification command. So first of all, I want to ping from here to the source or to the other side of the tunnel, and behind the tunnel we have some loopback. So I want to ping that loopback address. My source is loopback 0 itself, and now you can see that I'm able to ping from this source to this destination and vice versa. Let's go and check the phase 1 security association, and you can see that we have QM ideal, that's correct. And now I want to check the phase 2, that is the IPsec SA. Now here you can see that you have tunnel, actually you have two tunnel, inbound and outbound. First of all, you can see that you have the local ident, you have the remote ident. So you have this source and you have this destination. Actually the front door VRF IP addresses it is showing. We have some allow flags. Origin in is ACL. Now here you can see that in-cap and decap packets, almost same number of in-cap and decap. That means the transmission is happening properly from both the ends. You can see this local endpoint and the remote endpoint. Few of the policy we haven't set here, so that's why it is showing none. PFS is showing no, etc. Now we have learned about the SPI index. Here you can see that you have the inbound SPI index, and then you can see that you have the outbound SPI index as well. Right? Now here also everything is okay and correct. The final output that you want to check is the crypto session, and here you can see the port number and the protocol number. Everything is working up and fine. So this is the minimum basic configuration that once you do the configuration, you can go and verify from the show command. The best thing or the best command to verify all of your crypto configuration is show run section crypto. So if you run this command, you'll get whatever crypto related command that we have run, it will show. Okay. So this is the baseline verification that we can do once we complete our lab section. What I'm going to do here, that I'm going to save the configuration. Topology obviously will get with the slides. This configuration I will put there in the slide as well. So if you want to practice, you can practice from your side. Either you can use GNS or you can use Viral. In my case, I am using Viral. In section 3.0, we have infrastructure. That weightage you can see that is 30%, and the topics that we have is belonging to layer 2. So here you can see the layer 2 important topics. Say for example, trunk, VLAN, Ether channel, and RSTP and MST. In layer 3, we have to learn important protocol about EIGRP, OSPF, and BGP. Then wireless, and finally we have IP services. So let's start with section 3 and with layer 2, that is 3.1. So agenda here is that to learn about the VLAN, trunk, and various troubleshooting options that we have. So let's start 3.1, that is the 3.1a belonging to layer 2 troubleshooting, trunks, etc. Let's start 3.1a, where we have to learn about layer 2 technology and few of the troubleshooting steps. So before starting 3.1a, I just wanted to quickly revise about VLAN and trunking protocols. So here you can see in the diagram that when you have two switches, and when you're connecting two switches, obviously you want to allow different VLAN inside that. So that's why the distribution layer switch and the access layer switch, we have 802.1q trunk. Now what is trunk, which type of trunks we have, that I'm going to discuss. So let's first understand that what is VLAN and why we need VLAN. Say, what is the default nature of a switch? We know that by default, whenever a switch there and whenever it receives a frame, so for example, you haven't enabled any type of VLAN, or you're not working, created any VLAN to the switch. So whenever the frame will come and hit to the switch, it will broadcast that particular frame to all the available interfaces, correct? And in this way, number of collision domain or number of collision will increase. Rather than, what you can do, that whatever switch you have, you can divide that switch into a smaller group, and that smaller group is nothing but the virtual LAN. So this LAN segment you're dividing into a smaller group, that is, if for example VLAN 10, VLAN 20, VLAN 30. Now in that case, when a request will come, it will only broadcast it to that particular group, because different VLAN, they have the logical boundary. So VLAN is nothing but a logical boundary to reduce the broadcast domain. Plus, when we are creating the VLAN, uh, by default, we are providing some more security as well. So VLAN 10 and VLAN 20, they will not communicate until unless we have a router in between, that we can use router on a stick concept, or maybe the switch, they are supporting SVI. So they need some sort of gateway to communicate across the VLAN. So here you can see in the diagram that you have VLAN 100 and VLAN 200. They are purely in different IP subnet. So two different IP subnets or two different broadcast domains, they will communicate only if they know how to reach to the gateway, or they have to cross the gateway or the boundary. Now how to create the VLAN, it's very easy. You can go to the global config mode. You can give VLAN and the number, and then you can define, then you can give the name. So VLAN number and name, you can define like that. Now here you can see that we are supporting although up to 4K number of VLANs, means we can create up to 4094 VLAN starting from 1. VLAN 1 will be default, but this number 1006 to 4094 will be supported in transport mode, means they will be supported inside extended VLAN range. You can go and create up to 2005, where 1002, 3, 4, and 5 they are reserved for token ring and FTDI purposes. Okay, so we can go and create the VLANs. It's very easy to create. Let me quickly log into the switch and let me show you that how you can create the. So here I am inside the switch, and what I can do, I can go and create, say for example, VLAN 100, and then I can go and give the name as, say for example, servers. Then we can check the VLAN. So here you can see that you have VLAN 1 by default, and all the interfaces by default they are part of that VLAN. Then you have the reserved VLAN 1002 to 1005. But again, you can go and create the VLAN. So for example, I have created the VLAN 100, and I should exit, and then we can go and check that VLAN. So here you can see that now you have the VLAN 100 created here. I will not add any interface, but if you want, we can add the interface as well. So for example, any of the interface, show interface brief. Let's see that what available interfaces we have to this particular switch. These are the interfaces that I can see here, and if I can check the interfaces and the summary, so now you can see that you have these interfaces because this is the virtual switch. So you are seeing less number of interfaces, but I can go to any of the interfaces, for example, 1/1, and then I can go to switch port mode access. We'll discuss about this mode access and trunk, and then I can go and assign switch port access VLAN 100, and then I can go and check about this particular interface, that is show interface E11, and we have this option of VLAN. Even we have option for the trunk as well. So this mapping will not work, but if we go and check show interface E11 and then trunk, so here you can see that the encapsulation is negotiated. This is non-trunking. What is trunking, what is non-trunking, we'll see. The number of VLAN allowed over this interface is VLAN 100 that we have created. So like that we can go and check it. So here you have the command, and you can check show VLAN that just now we have checked. Now if you want to assign that particular VLAN to the interface, you can go and use switchport access VLAN 100. Again, you can go and check show VLAN. So 100 is assigned to this particular interface. Now, what type of ports we have that we can assign to VLAN? We have access and we have trunk. So what does it mean? It simply means that suppose if we have switch, and that switch is connected with the terminating device, means where you are terminating the network. So that particular interface you can put inside access VLAN. Say maybe access VLAN 100 or 200 or 300, etc., etc. And that's the reason in corporate network we are creating certain type of VLANs. So for example, VLAN name data, VLAN name wires, VLAN name sales, HR, etc., etc. So terminating devices generally we are assigning to the access port, but where you want to connect the other networking devices and you want to extend that access VLAN throughout the network, or you want to propagate that VLAN throughout the network. So whenever you're connecting a networking device to other networking device which is non-terminating, that you want to extend the network. So at that point, you want to create the trunk. So trunk simply means that can allow multiple access VLAN, or that can allow multiple VLAN. Access means they are part of only one VLAN. Later on, we'll see that we have different type of trunking protocols. So here you can see that rather using three different cables over one interface, once you enable the trunk, you can allow different VLANs over that. So for example, VLAN 100, 101, 102. We have trunking protocols. We have ISL, that is Cisco proprietary, inter-switch link, and then we have industry standard, that is 802.1q. Now in this diagram, it is quite clear that if you have terminating devices, so these terminating devices, they are part of same VLAN or a VLAN. Here you can see VLAN 100, here you can see VLAN 200, here you have VLAN 200, like that. And suppose if you want to extend, or you want to pass multiple VLANs over the trunk link, then you can go and allow those VLANs over connecting networking devices. Correct? So either we can use ISL, or we can use 802.1q. Here we have dynamic trunking protocol as well, which is something you can think that this is uh, dynamically negotiating the trunk, or dynamically negotiating two switch properties, although we have option to do this configuration manually as well. So how we are going to do this manual configuration, how we are going to do it dynamically, I'll show you in upcoming slides. Now the characteristic of 802.1q, that is now the standard, and even Cisco also uses 802.1q, is because this is lightweight rather than this ISL that is encapsulating entire frame. 802.1q, the feature or the improvement it has is that they are embedding. So here you can see that they are embedding 4-byte VLAN tag. So they are adding some tag to the frame, and once they add the tag, then the default size of the frame will increase up to 1518, because they are adding 4-byte of frame, and then it is supporting maximum 4096 VLAN. Now how it look like? It look like this. So you have the frame. When you add 802.1q VLAN tag, inside VLAN tag itself, you have VLAN ID 12-bit, and that's the reason it is supporting 4096 VLAN, because 2 to the power 12, if you check this number, then you will find it will be 4K, correct? So 2 into 2, if you do 12 times, we know that uh, uh, you can do the math, so you'll find that it is 4K. Apart from that, we have priority bit, we have the protocol tag, we have some bit as well, that is the canonical format bit. Okay, so we have just a overhead of 4-byte, and it is propagating the number of VLANs through this tag. So let me quickly log into the switch, and I'll create a VLAN 200, and then in between two switches, I have switch 1 and switch 2, I will enable the trunk. So let's do that. Mode trunk. And now it is telling that, see, this command is rejected because the trunk encapsulation is auto. If you want to do it manually, you have to do switch port trunk encapsulation. And here you can see that you have .1q ISL negotiate. So I'll do .1q and then switch port mode trunk. Okay, and what type of VLAN you want to allow? Switch port trunk allowed VLAN, say 100 and 200. Although I haven't created the VLAN 100 and 200, I want to create 100 and 200, and I don't want to add this VLAN 10. So I can do remove 10. Okay. Now we can go to the interface, say E0/0 and even 0/1 as well. So what command we are using? We are using switch port. First of all, switch port trunk encapsulation .1q. This is that manually I am telling that encapsulation is .1q. Switch port mode is trunk and we are allowing VLAN 100 and 200. Now same thing I can do to this side as well. I can go to interface range E0/0 to 1 and then now we can go and check show interface E0/1 trunk. This is one very good command. So allowed, here you can see that over E01 the allowed VLAN is this and this. The VLAN allowed over certain interface is this. We can go and check show and interface E0/0. So this is the command that we are working at the moment. I haven't created VLAN 200 to other switch, so I should create that also, but just for demo purpose. This is solving the purpose. So this is the way that we can go and create the VLANs, and then we can create a manual trunking, or we can do manual trunking as well. Next, we have to understand about the trunk and dynamic trunking protocol, DTP. We know that we can create the trunk or to pass multiple VLANs across two different switch or inter-switch link, we can create the trunk. We have option that we can do it manually, and then we have option that we can do or we can use dynamic protocol as well. So for example, if you have an interface 2/24 and if you run this command switch port mode trunk, first of all, it will throw an error. It will tell you that first you do the trunk encapsulation protocol or run the trunk encapsulation protocol, either ISL or .1q. So if you do that, and suppose if you have two switches connected back to back, say I have one switch here, another switch here. Here if I do ISL inter-switch link and here I do .1q, then obviously they will not form the trunk. So both sides we should give the same protocol, same encapsulation in other words, and then only they will form the trunk. So for example, if I give same encapsulation, so for example 8.1q or 802.1q or .1q, etc., then they will form the trunk. Now here we have the option. Either we want to do it manually or we want to use the DTP, dynamic trunking protocol. So for that case, what you can do that you can go to one side and you can do encapsulation negotiate. The full command is switch for trunk encapsulating or encapsulation negotiate, but they will prefer ISL. They will not prefer 802.1q due to these other Cisco switch. So they are going to prefer ISL. Better we can do it manually as long as possible. Now, once you have multiple VLAN and you want to allow it, you have option switch port trunk allow VLAN, and then you can give number of VLAN or range of VLAN. If you want to remove, you can remove that also, that we have done in the previous section where we have removed one VLAN, we have allowed certain VLANs. Now with this TTP dynamic trunking protocol, that is again the dynamic way to create the trunk. Again we have options. So this DTP has two modes to dynamically decide whether the port become a trunk or not. We have dynamic desirable and then we have dynamic auto. So here you can see if I go to certain interface and if I type switch port mode dynamic and question mark, I will show you in this in the switch as well. So then I have option dynamic desirable, dynamic auto. Now we have one long list that if two different switch, what mode they are running in and how they are going to initiate the trunk. So for example, you can do manual, you can do with help of DTP automatically. So manually, if you are making trunk, obviously they will form the trunk. One side trunk, other side is dynamic desirable. Dynamic desirable means you are sending the packets to form the trunk, means you are sending the negotiating packet. But dynamic auto will not send. So we'll see that. One side trunk, other side is dynamic auto. They will form the trunk. If one side you have dynamic, say desirable, other side dynamic desirable, they will form the trunk. So all these cases they are forming the trunk. And suppose if you have dynamic desirable and dynamic auto, they will form the trunk. But if you have dynamic auto, they will not form the trunk, because both these sites, they will expect that they are ready to listen the frames, but they are not actively sending the frames. So that's why they will not form the trunk. Now suppose if you want to disable DTP, you have option switch port, no negotiate. Correct. So in that case, we are not using this DTP to form the trunk. And again, you have the summary slide, whatever we have discussed here. Now, what are the troubleshooting option we have? Suppose if you're forming trunk and this trunk is not coming up. So you should check these things like what's the trunk mode, ISL versus 802.1q with respect to frame tagging protocol. So this is trunk mode will be, you should check what is the mode of the interface, say access or trunk, etc. Then the tagging protocol is ISL versus 802.1q. Then do you have a native VLAN mismatch? Suppose one side you are allowing 100 and 200, other side you are allowing only 200. Do you have any VTP domain configured? We'll see that VTP in the upcoming section. And that is only true when you are using DTP to negotiate the trunk. So these things one by one, you should go and check. Then we have one very important command here. Here you can see in the bottom that show interface name and switch port. This is actually very important command included with show interface trunk. So these two commands are there for verification, and both side you can go and run, means both side means both the switch. You can go and run this command and you can check that which VLANs are allowed, which protocol is running, what is the mode of trunk, etc. So let me quickly go and log into the switch and we can do some of the verification commands. So I am inside the switch, and if we go and check show interface description, we are just checking that switch 1 and switch 2, which interfaces they are using. So E00 and E01, these are the interfaces that is connecting to switch 1 and switch 2. And if you go and check show interface trunk, one very important command. So here you can see that E00 and 01, they are allowing these two VLANs, although the management domain it is showing only 100. Why? Because if you go and check show VLAN, you have only one VLAN. So what I'll do, I'll go and create VLAN 200 as well, and name I will give, say for example, clients. Now if we go and check show VLAN, we have server and we have client. Although we haven't assigned that to any of the interfaces, now we can go and check interface trunk, and now here you can see these VLANs are coming. Okay. All right. Now the status, you can straight away see that 00 and 01, they have status of trunking. Native VLAN is VLAN 1. The mode is on. Okay. Now show run interface E0/0. This is the configuration we are using. If I go to other side, so interface and then trunk 100, 200, because we haven't created any of the VLAN, so it is not showing anything. Mode is on, encapsulation is 802.1q. That's okay. Then I can go here. Also, I can create VLAN 100, name servers, and then VLAN 200, name clients, and then we can go and check show interface trunk. So you'll get the same result. Now next very important thing that we can check, show interface E0/0 and then the switch port. This is actually a nice output that will give you detail about VLAN and trunk. So administrative mode is trunk, operational mode is trunk, encapsulating 802.1q, negotiating of the trunk is on, access mode VLAN, that's the native VLAN, is 1, that's okay. Tagging is enable, voice VLAN is none. We are not using private VLAN at this point of time. Trunking is enabled, we are passing 100, 200. Pruning is there, means there are some default options as well. All right, so what we can do now at this point of time, we can check all the DTP option. So if I go to interface E0/0 and once I am inside switch port, you can see that what options you have. So you have a no negotiate if you don't want to, or if you want to turn off DTP, you can use no negotiate. Then if you want to check mode, and then you have this dynamic, you can see auto and desirable, and we have seen that list. So DDDD one side and DDD other side, that will form the trunk. If you have auto both the side, dynamic auto, they will not form the trunk and vice versa. Okay, so this is the way that we can create the trunks and we can verify as well. All right, so let's stop here. Next we have VTP, VLAN Trunking Protocol. And what is the use of VTP? We'll see that. This is something that we want to replicate or propagate the VLAN dynamically or automatically. And this will be useful for the large infrastructure where you don't want to create the VLAN switch by switch or hop by hop. So in this case, we can use VTP as a feature so that can replicate the VLAN, or in terms of the VLAN database, from one switch to the nth switch, correct? So how we are going to do this, what are the terminologies used and all, we are going to discuss and learn all those things in this particular section. So you have this VTP, and VTP, they have their own features. So what features they have, we'll see that. First of all, they have versions, say version 1 and version 2. Version 2 is quite a bit popular, although we have version 3 as well, which has again some added advantage. So let's focus on version 2 and we'll see what features we have in version 3 as well. VTP version 2 that can do VLAN consistency check. They are domain independent, transparent pass through. Means there are you have some added advantage in version 2. And in version 2, we'll see that how we can configure it. In version 2, what are the key component we have, that we'll see in the upcoming slide. Now what important thing we have in version 3 is that not only version 3 can replicate the VLAN database, but they are able to replicate the other databases as well, such as MST, multiple spanning tree protocol. Apart from that, version 3 can have support up to 4000 VLAN. They are supporting private VLAN. They have improved authentication. Whatever issues you have in version 2, and we have one issue in version 2, that suppose that you have switches and you brought new switch inside the VTP domain, by mistake, if the domain name is same, and suppose if the revision number for that new switch is higher, so whatever database that new switch has, they will go and write those databases or those VLAN to all the switches, and you can understand how big that issue is, how big outage it will be. So there is no database protection mechanism that we have in version 2 that is there in version 3. So here you can see that protection from accidental database overrides by using VTP primary and secondary server, ability to enable VTP on per port basis. Okay, what modes we have for VTP? We have three modes. Actually, we have four modes. Let me show you here in the diagram. So here you can see that you have server, you have client, you have transparent, you have off. Server means you can create the database, and from there with the revision number it will go and write to all the client who is listening those and updating their database, transparent who is simply passing that information. So here in the diagram you can see that you have server who is sending the information, because this switch is in transparent mode, so he is passing that to the other client who is learning that new information. Likewise, here you can see that server is sending to the other client. If the VTP is off, so they will ignore the VTP update. So in a switch where you don't want that VTP update, you can turn that off, so that particular switch will not get the VTP updates. Correct? So the same thing you have explained in this diagram, and then you have the notes that you can refer. We have version 1 and we have version 2. In version 2, we have added advantages and feature. One of the very interesting thing and important thing we have with respect to troubleshooting as well is the revision number. Now in the lab section, we will see this revision number, the format of this revision number as well. Not only the format, but uh, when you go and check show VTP status or show VTP, you will find that you have the revision number. So at the moment you will add the VLAN, the revision number will upgrade, and then since he has the higher revision number, he will send the advertisement to the other peer switches or downstream switch to update that database that you have added inside the server VLAN. Correct? So that's the reason the revision number is important, because it is one of the component of the VTP advertisement. So here you can see that if you want to change this revision number, because accidentally you don't want to connect any switch by default in a network who has higher revision number, if because by default the switch mode is server. So if revision number is higher, it will start sending the VTP advertisement, and other switch they will think, oh, his revision number is higher, so I should overwrite my database as well. So you don't want to do this. So in that case, the safe thing is that you change the mode to transparent and then change it back to the server or client. So if you made that to transparent, what will happen that they will change their revision number to 0. And this is particularly for the new switch. The other option is that change the VTP domain name and then change it back to the original name. So you can change the domain name and change it back. The best option we have is the option 2, that change the mode to the transparent. Okay. Now we have already discussed about VTP version 3. They have this protection mechanism because they have VTP primary and secondary server. What type of messages we have inside VTP? We have summary advertisement, we have subnet advertisement, we have advertisement request. Summary advertisement, here you can see that it is sending the VTP version, domain, configuration revision, timestamp, and MD5. Correct? So suppose if two switch, their domain name is not the same, means if they are not in the same domain, obviously they will not read those databases, or they will not override those databases. And same is true with the MD5 digest as well. They should have common password so they can replicate the database or understand the database and override it later on. So a switch is sending the summary advertisement and the subnet advertisement. In both the summary advertisement and the subnet advertisement, you will find that you have configuration revision number. So here you can see inside the subset, not subnet, it is a subset advertisement. Inside the subset advertisement, again you have the revision number, and revision number simply means that if you are getting some information from higher revision number, you have to overwrite it. Now suppose um, here you can see that there is one use case of advertisement request. What it is that if switch receive a summary advertisement with a revision number higher than its own. So suppose I am getting a update with revision number 3, but mine is, say for example, 2. so I am lower in the revision number, then I will send the advertisement request that, hey server, my revision number is lower. You write all the VLAN information and update my revision number. So all the devices in a network should have the common revision number. Okay. All right. So how we can do the configuration? It's very easy. You have to do at least two things. Domain. So you have to go and define the VTP domain and then VTP mode. You define the VTP domain, VTP mode, even we have to define the VTP version as well. So you do a VTP domain, you do VTP mode, you do VTP version, and if you want to do the protection, you can use the VTP password as well. So it's very easy to configure if you follow these configuration steps. So it's easy to do the configuration. How we can verify it? You can go and check show VTP status. So here you can see that its VTP version is 2, configuration revision is 42, maximum VLAN supported 1005, number of existing VLAN is 7, the operational mode is server, the domain name is my domain, the pruning mode is disabled at this moment. We'll see that what does it mean by pruning, and this MD5 digest is also there. Again, we can go and check the VTP counters as well. So now here you can see that we have the VTP pruning. What does it mean by VTP pruning? Pruning means simply that you cut off unnecessary information. That's the prune. Now VTP pruning means that you don't want to propagate unnecessary information to the switches. So here you can see in the diagram. So suppose if switch B will advertise the VLAN information, he will send switch C VLAN 100, 200. That switch C anyways is not going to understand. And switch A, he will advertise VLAN 300. Again, he will not understand because he don't have that. So in that case, what you can do, that simply you can cut off these information to advertise in first place. So here you can see that you can go to the switch globally, you can enable VTP pruning, and then once you enable that, then you can go to the switch interface where this interswitch link is connected, and you can do switch port trunk pruning, and you can prune those VLANs. Apart from that, you have other options as well, like VLAN add, remove, etc. All these options we have with the normal trunk as well. So we can prune those unnecessary VLAN to propagate from one place to other place. Correct? Now, if you want to do the optimizing convergence, already we have studied about the DTP in the previous section. All right, so this is the VTP pruning, and this is the VTP. If I want to summarize this, how I can understand VTP. So we can think like this, that VTP, if you want to configure, you have to configure actually minimum two things, but four things are required, like VTP domain, VTP version, VTP mode, and password. VTP has version 1, 2, 3. 2 and 3 is most popular to use. Their modes are client server and transparent. Transparent means that simply bypass the advertisement. Server who is creating, client who is receiving. And the common factor in all these modes and things are the revision number. So if the revision number is higher, he has the authority to update the database to the other devices. Correct? And then we have seen that we have the advertisement like summary and subset. And if your revision number is less, you will send the advertisement request to update that revision number. How we are going to configure it, we'll see in the next section. Let us perform the lab task. So we have this arrangement where we have switch 1, switch 2, and switch 3. Let me quickly draw the diagram. So I have switch 1, and then it is connected with switch 2, and then it is connected with switch 3. 1, 2, and 3. Even switch 3 and switch 1 is also connected back to back. But we will make this interface as off, or we'll disable these interfaces. All right, so switch 1, 2, and 3, what interfaces they have? say 00 and 01 in between that, and here you have 02 and 03. So it is connected like that, and here it is say 00 and 01, and here it is say 02 and 03. I'll shut down these interfaces, so I don't want any cross communication in between the switches. So this is the topology, and we want to run this VTP. So what I will do that switch 1 I will make, or switch 101 I'll make as a VTP server. So let's do this. I'll go and create VLAN 10 to 20, and here you can see show VLAN. So now we have the list of VLAN. A few of the VLANs we have created earlier as well. Then I'll go to the interface range E 0/2 and 3. So E0/3. Even I can go and give the hyphen as well. These interfaces I will do this shutdown because I don't want switch 1 and switch 3 do the communication. Alright, we can go and check show CDP neighbor, and we can check what switches we have in communication. So here you can see that I can directly communicate with switch 102 or switch 2, and that's the agenda we have. Alright, so let's go and create the VTP, say domain. I'll make this as a my domain, then VTP version. Here you can see that we have the syslog message telling that the domain name has changed from null to my domain. Version is 2, and then VTP, what options we have. Here you can see that we can give the mode, we can give the password, we have the pruning option. We'll see that. So now I can go and give the mode as a client server transparent and off. So this is the server. By default it will be the server. I'll go to the other switch here. If you check number of VLANs, so it is replicating. Why? Because if I go and check show VTP status, so here you can see that this version is version 2. It is running version 2, although it is able to understand 1, 2, 3. The domain is my domain, and by default you can see that this is also server. What is the configuration revision number it has? That number is 4. Number of VLANs is this. Let's check this in the first switch as well. So means that by default the VTP is on the switches. So I'll go back to switch number 1, and inside switch number 1 we can check the VTP status. Let me run the command show VTP status, and here you can see that you have version, you have mode, and you can see number of VLAN supported. So everything is perfect and correct. There is no problem here. Now if I go here and create one more VLAN, say for example VLAN say 55, and now if you go and check the status, you can see that number of VLAN become 19. The revision is 5, and the same thing should be replicated to the other switches as well. So the revision from 4 it become 5, and now if I go here and check the VTP status, now here you can see 19 and 5, although the mode is server, that I will change it to client, and we'll check the transparent as well. Here if I go and check show VTP status on switch number 3, so let's check that. Now this is also server, and number of VLANs is 5, configuration revision is 0 and he is not able to get the information from switch 1 to switch number 3, because switch 2 and switch 3 even they are not forming the trunk. So what I will do, I'll go quickly here and we have one interface here, interface E0/2. I can go and manually assign the trunk, or we can do this dynamically as well. That's the DTP. So I'll do this thing, switch port and then trunk. You can see that you have uh, encapsulation and you have native pruning allowed as well. What I want, that I want to do switch port mode, and that's dynamic. We have desirable option. The switch port mode dynamic desirable, and then switch port mode trunk. Now the flip side of this is this, that if both side you are enabling this, they will go and execute ISL instead of .1q. So the recommendation is that we should do the .1q, correct? So that's the reason. Let me quickly go and do this switch port trunk encapsulation .1q, that because that's the standard, correct? So what we have done over show run interface E0/2 is these commands, switch port trunk, and then I don't need switch port mode dynamic desirable because I can go and make switch port mode trunk. But anyways, let's go here and run these commands here as well. Interface E0/2. So interface E0/2, then we can check show VTP status. Now you can see that they have formed the trunk and now multiple VLANs are passing. Next thing, what I want to do here is that the VTP mode I want to change as a client. Okay, and then we'll go and check the show VTP status. Then here I will go and create some more VLANs, say VLAN 6270, and then we'll check the status, show VTP. What options you have, you can see that counters device interface status and the password. So now total is 30, revision number is 6. We can go ahead and check. Total is 30, revision is 6. Now I can go here and check 30 and 6. So still we can see that the client is sending some information to the server as well, and he is updating his database. Now what I want, I don't want to do this thing. Rather what I want here is that the VTP mode is client first of all, okay, and then I will go and create some more VLAN just to verify, say VLAN 8290, and we can go and verify the VTP status on switch number 3. So now this is 41 and 7. Now in between the switch, I will go and make this as a VTP mode transparent, and then we'll check the revision. Now you can see the revision number become 0, although they have this 41 VLAN that they have already learned. So now if I go here and create some more VLANs, say for example 100 to 110, And if we go and check the status, now this is 8 and 51. Here you will see this will become 0 and 41, but it should become 8. Now here you can see that the status is the same. So as per the transparent mode, it should pass the information. Although you can see that revision number is still 7 and the number of VLANs are 41. That should be 51. So clearly we are seeing that they are not updating the revision number in between if we have the transparent. And this is the issue with the virtual devices, but ideally, as per the theory, they should update the database. So I'll do one thing, I'll go back to switch number 2 and I'll make this VTP mode as a client one more time. And now we should see here. Now they are replicating in the client mode. So server in client mode is working perfectly. Transparent mode, although they are changing the revision number, but they are not propagating the number of VLANs, correct? Now if I go to VTP mode and then I can make this off and we can check the status now. So now revision number becomes 0 and whatever number of VLANs I have, they are learning that. Obviously, if revision number is 0, that means that they will not learn those data in case if it is off. So now if I go here and create some more VLAN, say VLAN 150 to 160. So we can go and check the revision number 9262, and here also we can go and check the revision number 9262. Here this is off. Okay. The last piece that we have to learn and understand here is the pruning method. So if I go here and first of all I should enable VTP pruning globally. Once you enable that, so cannot modify pruning unless the VTP is in server mode. So that's the restriction. First of all, the pruning should be inside the server because the server has the authority to create the VLANs and then it is replicating the database. So VTP pruning is on. Now what we can do is that we can go to switch port and let me go to the interface. The interface is 0/0 switch port trunk, and then you have pruning, and then you can use VLAN, and you have add, accept, remove, none, etc. Okay. Now we can go to the switch port interface E0/0 and we can check the switch port related to E0/0. Here you can see that the mode, the encapsulation, the trunking, and you can see the pruning VLAN is enabled. We have made that as a none, so that's why it is showing like that. Okay, so this is the way that we can create the VTP and we can do the verification as well. 3.1 we have Ether channel configuration. We know that Ether channel is something that we can bundle the interfaces to overall increase the throughput. So here you can see in the diagram that you have core, distribution, and access layer. Generally, where we want to do this bundling or aggregation of the port or interfaces, they are at the level of core and the distribution layer generally. That doesn't mean that we can't do at the access layer. We can do as per requirement. So what we are achieving with Ether channel or the port bundling, that that we want to give much more throughput whatever we have at this point of time when you are connecting the interfaces back to back. That simply means very simple term, that suppose I have switch A and switch B. So let me try to draw here. Say for example one switch here and one switch here. If I have 1 gig interface, then obviously the overall throughput is 1 gig. But you can take, say for example, 4 interfaces and you can bundle and they can work as a 4 gig interface. So overall throughput obviously will increase, will become 4 gig. Now the important thing here is to understand is that this 4 gig interface is per application. Means suppose if you have only one application and you think that one application is getting 4 gig of interface, that's not true. And the algorithm or mechanism behind the scene is that suppose if you have two interfaces, they will do the load balancing. So 1 gig and 1 gig will get load balancing or get load balanced per application flow. That's the key thing we have here. Whenever we are doing the port bundling, that doesn't mean that this become one 4 gig pipe and all the applications are getting 4 gig of speed. It's not the same thing. All right, so we have different type of methodology behind this, and we'll see that we have LACP, Link Aggregation Control Protocol, and we have Cisco proprietary, that is the PAGP, Port Aggregation Protocol. But moral of the story is same, that you are aggregating the port for higher throughput. Now we have to go and check that how we can create this Ether channel or bundle. We have option, we can do it manually, we can do it dynamically as well. Manually when we are talking, so for example I have two interfaces, I can go and I can use this command interface range and then channel group 1 mode on, or maybe you can use some other number like 10, 20, 30, 40, etc. So when you are using mode and on, and we have multiple option. So for example in LACP we have option related to active, passive, and on. So for example, if you are using on, this is a manual thing. Manually, you are turning on this LACP protocol or channel protocol. Okay. Now, once we are running this command, what is happening behind the scene? Automatically, port channel interface 1 will get created. Now, this port channel 1 interface that you are creating, here you have to go and write your logical configuration, or you have to do the coding. So for example, if I have two interface 23 and 24 and I want to run commands related to switch port mode trunk and allow certain VLAN, then I do not have to run the command over the member interfaces. Rather, I have to do it inside the logical interface. So we should understand some of the technical term here, that I have a switch and I have two member interfaces, so for example 23 and 24. When you bundle these interfaces and you are using manual method turning, so for example LACP on, so at that point of time, so for example the group you are using is 1, so you are going to create interface port channel. Here you can see this port channel 1, and whatever configuration you want to put over these interfaces, you should put here over the port channel. The switch port mode trunk and allowed VLAN we should put there. Suppose if you want to create a layer 3 port channel, then you can go to the port channel, you can do no switch port, and then you can assign the IP address as well. Okay, so this is the manual way to do the configuration, although we have the automatic way as well, and we have the protocol as well to do this. We'll see that in the upcoming slide. One important note here, that whenever we are creating the port channel among 2 or 3 or 4 switches, obviously these are point-to-point configurations. So in between two switch, whenever you are creating the port channel, So at that time, your speed, duplex, and other hardware related properties should be the same. So what I'm telling here, that you are creating port channel here, no problem, you can create it. Like that, you can create other port channel here. So for example, number 10 and 20, etc. So these interfaces, so for example, speed, duplex, should be same, correct? Otherwise, they will not form the port channel, and constantly they will throw an error as well. All right, so next we have the dynamic way to do the configuration. We have a link aggregation protocol, we have port aggregation protocol. Uh, Now everyone is using LSCP, and even in the syllabus also, um, it is recommended that we should learn, understand LSCP. Although if we learn one methodology, the second will come automatically. So I'm going to focus on LSCP, link aggregation protocol. This is the dynamic way to create the bundles. We have mode for LSCP is active and passive. If both side of switch is active, they will form the port channel. Both side is, say one side is active, other side is passive, again they will form the port channel. If both side is passive, then they will not form the port channel, because no one is sending the LSCP control packets. So obviously both are the listener for LSCP, and they will not auto negotiate the ether channel or the bundle. So here you can see that when you are doing the LSCP negotiation, means when you are doing this automatically, so you can go to the interface, channel protocol you can define, then you have to go and give the channel group name, mode active. So suppose one side I am using active, other side I am using passive, so they will go and form the port channel. It's very easy and straightforward. There is no much thing behind this. Now we have some important thing related to LSCP, that we can have 8 interfaces inside group, and 8 interfaces we can work as a backup. So 8 plus 8, they are supporting total 16 interfaces that can form LSCP, but these 8 interfaces are working as a backup. Now who will work as an active? That depends upon port priority. By default, that will be 32768, and lower is the better. Okay. Now apart from that, we have other variable as well. Other variable is system priority. So suppose if you have two switch, and which switch will take the active role and which will work as a standby or secondary role. So who is the primary, who is the secondary? So that depends upon the system priority. By default, that is also 32768, and lower system priority is better. So suppose this is 500 and this is 32768. So obviously he is the active initiator and he has to take the decision. So by default both will be the same, so that again if you have the tiebreaker, so in that case always the lowest MAC address will be preferred. So whoever switch having the lowest MAC address, he will take the decision, because by default we are not changing the port priority, we are not changing the system priority. So as per the MAC address, in terms of system priority, lowest MAC address will win. In terms of port priority, lowest port number will win in case of tiebreaker. Now once you do the configuration, you can go and check show ether channel summary. That's the nice command. There you have the legends or flags. So for example, D for down, P that they are in the port channel, I for a standalone, S for suspended, R for L3, S for layer 2, etc. So you have the legends and you can check the status. So these devices, S stand for layer 2 and U stand for port channel in use. So this port channel is successfully formed. This is layer 2 and up and running. Okay. On Cisco Nexus switch, the syntax is little bit different, obviously, in the Catalyst switch and the Nexus switch, but the concept behind the scene is the same. So this way we can go and create the port channel. Here you have some difference, means what is the difference between port aggregation protocol and link aggregation protocol. In port aggregation protocol, we are using the mode as auto and desirable. Desirable is equivalent to active, and I think there is some typo here. So desirable is equivalent to active. Okay. All right, so it's not a typo mistake, but in the diagram, there are different use cases. So manually, you can do on, either it's a PAGP or link aggregation protocol, they will work. Now, on off, one side on, other side off will not form the channel. That's true. Then one side auto, other side desirable, they will form the port channel. Now here you can see that you have auto. So let me write here auto, and then you have desirable. This auto is passive for LSCP. So for example, PAGP, and this desirable is active. So if both side is desirable, they will form the port channel. Both side is auto, they will not form the port channel, and same is the case with LSCP that we have discussed earlier. So these are the use cases, these are the scenarios we have that will work here to form the Ether channel. Let us perform the lab task here. In our lab, so for example, we have switches, and these switches, so for example, switch 1 and switch 2, their interfaces are 0, 0 and 0, 1 both side. So we'll go and form the LSCP port channel. First we'll try to form with the manual method. Method means you can make this on, and then we will use the LSCP as well. Even we have option for PAGP as well, but we'll focus on manual and LSCP. So let's go and do this. First of all, what I will do, that I will do the default for the interfaces that we have E00 and 01, because we have done some configuration earlier and I don't want to do that here again. Means I don't want to have the old configuration, so I can go and default the old configuration. Now once I delete this, then I can go here and I can take the range of E0/0 and 1. Let me type it. So 0/0 and 1. And then we have this option of channel group. So for example, channel group, you can see the number is from 1 to 255. I can take 100 and then mode. Mode on means we are making this on, we are turning this on. So now here we can see, because this is the virtual device, so maybe we'll get some error. So port 100 invalid group slot number, etc, etc. Let's go back and try to make this 10. Okay, so this is the problem with the virtual switch itself. This is not the problem with the actual hardware. So if I use 10, it took the 10, and likewise I can do one thing, that show an interface E0/0. Let's copy and paste this configuration other side as well. So here interface range E0/0 to 1, and then I can paste the configuration, or we can go to channel group 10 or whatever we have. Let's see that we have created 10 and mode on. So 10 mode on. Now once we create this ether channel, then we have option that we can go and check show ether channel summary. Now here you can see that S stand for switched layer 2 and U stand for up. So we have this is up and running, and ports are in bundle. Now, if you want to know detail about this, so we have option of ether channel, and then you have this option of detail. Even you can go and check the load balancing method as well. So I can go here and check this detail as well, and in detail you can check this information in detail as well. So here you can see all these detail options that we are getting. Now this is the manual method. Now suppose if I want to do this with the uh, automatic, or if I want to use any of the protocol, so in that case I should go to the interfaces first. We have the interface range, and then you can go and define the protocol. So this channel protocol is either LSCP or PAGP. That's a Cisco proprietary and the industry standard. Now because they are already in bundle, so we are getting this error. What I'll do here that I'll exit here and I'll remove that group, or maybe we can go here and then we can remove that statement. So I'll do no here, and then I'll go and remove that statement from the other switch as well. So let's go to the range and paste this configuration, removed. All right. Next, what we can do here, that we want to give this channel protocol as a LSCP. Then I can go and define the channel group, say for example 20, and then you can see the mode we have is active and passive for LSCP, auto and desirable for PAGP. But I want active, say for example active this side, and other side I can go here, and there again I can go and type say channel protocol is LSCP, then channel group is 20, mode is passive. So either it should be active active or active passive, so it will form the port channel. Now if I go here and check show ether channel summary, I can see the ether channel summary. I can see that now we have this, and they haven't negotiated everything, so that's why it was showing as suspended state. Let's see what is the actual code here. So waiting and S and N. So here you can see that you have layer 2 not in use and waiting for aggregation. So still the LSCP was not negotiated, and that's why it was showing that it is waiting. Now you can see that 20 has been formed and it is working properly. Correct. So this is the way that we can go and bundle the ports. If you want to see more things related to this, so still we have the option that we can go and check the protocol and then enter. So here you have the LSCP protocol, you have group 20, you have that mode is on. So like that we can go and check this. Now suppose if we have some issue that is keep coming and coming and coming, so you have the option to do the debug for LSCP. Once you do the debug for LSCP, then you have to check that who is the sender, who is the receiver, etc, etc. Okay, so you need to understand that this debug how it is working. And if you go here and oops, so I can go here and I can debug LSCP events here as well. I can go to conft and monitor, or let's see if I can monitor over the screen, otherwise I have to go and check the logs. If any problem will be there, it will start sending these LSCP related negotiations problem that we can go and check. So I think terminal monitor is the command. Console already monitors. All right. Now if I go here and do any type of if any type of issue will come, so let's see. And channel protocol is PAGP. So if we create any issue here, and then if we verify this, we can see some problem. So I'll do one thing, no channel protocol LSCP, and then you can go and check the debug. So this is the way that we can go and verify the debug as well. Remember that whenever you are creating the debug, it's not recommended that you should do in the production network. You should have the maintenance window, or if the issue is major, you can take Cisco TAC online, and then you can do the troubleshooting, deep dive troubleshooting. In 3.1c, we have to configure and verify RSTP and MST. So let's start with RSTP, that is Rapid Spanning Tree Protocol. Now it's very good that if we know the other spanning tree protocols as well. So for example, it's good if we know STP, PVSTP, PVSTP plus, and then RST, and then RSTP, and then MST. But I'm going to revise those spanning tree protocol, at least the core behind the spanning tree protocol methodology. What exactly happening when we are talking about the switching network or switching architecture? So in that case, to prevent from the loop, we are running actually STP. So suppose if we have three nodes connected like this, like a triangle, suppose switch A, B, and C. Now here you can see that if you build your network like this, obviously uh, you will find the loop. So frame will be looped across this triangle. So uh, now again, you may think that why we are creating network like triangles or looped network. The answer is for redundancy. We are creating such type of network so that can provide us redundancy. So for sake of redundancy, we are creating such type of network. So for example, if one link is down, still you have one backup link, or maybe you have other links as well. So two links is down, still you have one link, etc. So for sake of redundancy in a switched network or in layer 2 network, we are creating loops, or we are at least creating such type of network design. Now the question here, second question may be that, okay, since we are creating the loop, then what is the loop prevention mechanism? And then the STP is the answer. Spanning tree protocol is loop prevention mechanism. What it is doing, that as per the priority, one of the switch will become root, and then obviously you have second root and non-root. But what is happening, that whatever interfaces that is going towards the root, they are termed as a root port. So you have root port, and whatever interface you have in front of root port, those are termed as a designated port. So you have DP and then you have RP. Now what about those switches where you have least priority? They are not root, they are not secondary root. So in that case, they will go and check the priority. If priority is same, then they will check who has the lowest MAC address. So one of the interface will treat as a blocking, BLK, say BLK as a blocking, and other will treat it as a designated port. So this is the blocking port, and then you have the designated port. So the summary of this explanation is that since you have such type of arrangement, So one of the interface is working as a blocking port, and suppose if your main interface is down, so still the traffic can go from this direction, because from blocking it will move to listening, then it will move to learning, and then it will move to forwarding. Okay, so it will take some 30 to 50 seconds to converge, and after that period of time the traffic will go from the blocking, because finally it will become the forwarding port. Okay, now here that's a problem, that we don't want to use STP, rather than we want to use rapid STP. We don't want to wait for this time to converge the network, and that's the solution is to use the rapid STP. So let's see that what are the things we have in the rapid STP. This is under 802.1W, or rapid spanning tree protocol. It's similar to STP, but there are dissimilarity as well. There are differences as well. We'll see that what are the differences we have. So BPDUs, here also you have bridge protocol data unit. These are the, you can think these are the control type of messages upon which the switches, they are building their STP, or they are building their RSTP. Here also they will select one root bridge as per the lowest bridge ID, that will be 32768. We'll see that in the next slide. Then the root and designated ports are elected and functional identical to STP. These are the similarities. What is not similar? You can see that here you have root port, alternate port, designated port, and backup port. In other hand, in STP you have root port, designated port, and blocking port. So let me show you in the diagram. It's always easy to understand with respect to diagram. Here you can see that you have the lowest priority, so priority 100, who will become a root bridge. So this guy, and this is with respect to STP, and this is with respect to RSTP. So this guy is the root. Whatever going towards the root bridge is root port. There you can see these are the root port, and then as per the high uh, priority, one will become block, one will be the designated port. If you have any issue in this direction, then it will move to the forwarding state and packet will flow like this. Correct? On other hand, you can see that in RSTP, he is the root bridge, for example. So these are the root port. We have the designated port, same like STP, but instead of blocking, here you can see that you have alternate port. Correct. And if you have two link, so one link is designated port, other one is the backup for the designated port. So instead of blocking, we have alternate port inside RSTP, and that is one of the reason for faster convergence, but there are other reasons as well. Here you can see that instead of blocking, listening, learning, and forwarding, we have discarding, learning, and forwarding phase. So we are not waiting for that particular amount of time, rather than we are moving to the forwarding state as soon as possible, as quickly as possible. Now, initially, a switchboard starts in a discarding state, obviously, then he has to start his learning. Now, a discarding port will not forward frames or learn MAC addresses, as the name suggests. A discarding port will listen for BPDUs. Alternate and backup port will remain in the discarding state. So you have your alternate and the backup port. They are still listening, but they are not actively participating. So they are listening. Otherwise, if failure will happen, how they will start forwarding the frame. So they are not they are not in the forwarding state, but they are still listening the BPDUs. Now RSTP does not need a listening state. Instead, if a port is elected as a root or designated port, it will transition from discarding to a learning. So here you can see that now if you have root selection, then in that case the port will move from discarding to the learning state. Now what will happen in this case? A learning port will begin to add MAC address to the CAM table. However, a learning port cannot forward frames still. So here you can see that you have three state. In discarding, you are listening that. In learning, you are start learning the MAC address, but in discarding and in learning, still you are not forwarding the packet until unless you reach to the forwarding mode. Finally, when you reach to the forwarding state, then it will send and listen for BPDU, learn MAC address, and forward the frame. Root and designated port will eventually transition to a forwarding state. Okay, so once you have the selection of the selection of the ports, like root port, designated port, alternate port, etc., they will move from discarding learning to the forwarding state. Now the main question here, that why RSTP has faster convergence, and now you will see the core difference between STP and RSTP. Why? So BPDUs are generated by every switch and sent out as a hello interval. Switches no longer required artificial forward delay timer. Now what is happening in this case, that all the switches, they are generating their own bridge protocol data unit and they are forwarding to their peer switch. Okay. Now what is happening in STP? STP code is 802.1d. Now in STP, BPDUs are generated by the root bridge. Now, if switch receive a BPDU from the root bridge on its root port, it will propagate the BPDU to the downstream or its neighbor. This convergence process is slow and STP relies on forward delay timer to ensure a loop-free environment. So now you can understand that rather in RSTP, switches, they are generating the BPDU and sending to the neighbor. But in STP, that is 802.1d, you have one root port or you have one root bridge election. One switch will become the higher authority and then he will generate the BPDU, and all the downstream switches will listen as per their delay timer or as per their timer. So you can see here that the default nature of STP is slow rather compared to RSTP. Now in RSTP, switch will handshake directly with their neighbors, allowing the topology to be quickly sync. This allows port to rapidly transition from discarding to the forwarding state without delay. So you have one-to-one handshake, and then from discarding it will quickly move to the forwarding state where they want to forward the packet. Now again, we have some port type in RSTP. We have edge port, and suppose if you know at this point of time about port fast. Port fast is one of the very popular term that whenever you are connecting the switch with the terminating device, say for example server, so you don't want to send the BPDU. So I don't want to send BPDU, or I don't want to send STP control packet to the device that is non-switch, which is not a switch. There is no meaning of that. So that's the reason this particular interface, we are making this interface as a port fast, means quickly it will go to the forwarding state. Likewise the edge. Now this edge port is working as a port fast, immediately it is going to the forwarding state. So there is no listening, learning, forwarding like STP, or there is no discarding, learning and forwarding like RSTP, but directly it will move to the forwarding state. Now second port type, we have the root. Root ports are connected with other switch and has the best path cost to the root bridge. Obviously we know that root port is there. That is one side you have root port, other side you have designated port, so you can reach quickly to the root bridge. And then finally you have point-to-point port. What this point-to-point port is doing, that port that connect to other switch with the potential to become the designated port for a segment. So it can become DP, and now if you go and refer the actual diagram that we have here, so you will understand. So you have root port that is going towards the root bridge, and here you can see the adjacent to root port is the designated port. Designated port adjacent is root port, but here you can see that you have designated port and backup port as well. All right, finally we have some important notes here related to RSTP. So let me quickly cover this. Now if edge port receive a BPDU, it will lose its edge port and status and transition normal through the RSTP process On Cisco switch, any port configured with port fast become the edge port. We know that. Say edge port, I already explained this, is port fast. Quickly move to the forwarding state. That's the summary for the edge port. Now the RSTP converge process is below. So let's quickly understand the convergence process of RSTP, why they are converging so fast, and we have discussed this in the earlier slide as well. So let me quickly revise this. Now switches exchange bridge protocol data unit to elect the root bridge. This is valid for all the spanning tree protocol. Now edge port immediately transition to forward state because they are nothing but the port fast. All potential root and point-to-point ports are start with the discarding state. So this is actually important. By default, the ports will start with a discarding state. Correct? Means they are actively listening the BPDU. They are not learning the MAC addresses. They are not forwarding the frame. They are learning. So you can think behind the scene. It's not learning actually. They are listening. So you can think this as a listening active listener. Then if a port receive a superior BPDU, it become to root port and transition immediately to the forwarding state. So obviously once you learn the BPDUs, then you will move to the forwarding state. Superior means that suppose if you are getting one BPD, because in this case what is happening, all the switches, they are generating their own BPDs and they are exchanging it. So suppose this switch has low priority, say 32768, the default priority. Suppose this has priority 32769. He has 68. 69 is not a valid number, just for example. So obviously when he receive the PPTU, he will understand, oh, I am getting this with the higher or the superior switch, and then this will become, so this particular point-to-point interface will become the forwarding state. Okay, for point-to-point port, each switch will exchange a handshake proposal to determine which port become the designated. Obviously, you can do the handshake and you have to define who is the designated. It's okay. Once the switch agrees, the designated port move immediately into the forwarding state. So here you can see the convergence is like little bit different than STP. So ports, they are starting with the discarding state and then they are moving to the forwarding state. At the moment you get some superior BPDU, it will become the root port. So again, remember, if he is the root bridge, that means that you are the root port and he is the DP. Okay, so if he is sending the BPDU, it will be superior BPDU. Correct? And when he is sending the BPDU, he is not superior BPDU. So that's why it is telling that it will move to the forwarding state, because you have only one blocking type of a state, that is the discarding. So either you will be at the learning or you will be at the forwarding and you will be at the discarding, but there are less chances that when you have the superior BPDU, you are in the discarding state. All right, so this is the summary for the RSTP convergence. Now every switch will perform this handshake process with each of the neighbors until all the switch will get sync. Complete convergence happen very quickly within the second. So all the switches, they are sending their BPDUs, and then switches, they are calculating on basis of BPDU and the superior BPDU. Now, whoever is sending the superior BPDU, he has become the root bridge and his interface will become the designated port. The adjacent port will become the root port because he has to reach to the superior bridge, and according to that all the switches will converge. Once they converge, once they sync, then RSTP will up and running to all the switches, and then it will take a few seconds, and that's why it's TCN in STP and RSTP both have different way. TCN is nothing but topology change notification. Now what is happening in STP, say in case of when the switch move to forwarding state, or in a state of when they are going to blocking or down state, at that time they are generating the TCN, particularly in STP, that is 802.1d. Now that TCN bit will go to the root bridge because we know that root bridge has to take a decision. Now what root bridge is doing now, that now if they are sending the BPDU, they are setting the TC bit, that is the topology change bit, and then they are forwarding this to all the downstream switches. So all the downstream switch will come to know that the port is going to the forwarding state, or switch interface is going to the forwarding state, or blocking or down state. Correct? Now again, this is little bit time consuming process. Rather than in RSTP, what is happening, first of all, only non-edge port when they are moving to forwarding state. So we know that this edge port are working as a port fast, or they are equivalent to port fast. Directly or quickly they are going to the forwarding state. So only non-edge port, when they are transitioning to forwarding state, they are generating the TCN. Now good thing about RSTP that all the switches that they can generate the BPDU and send the BPDU. So in this case, what has happened, that they are not waiting for the root bridge to understand or recognize that particular change or that particular topology change notification, and then it will send to all the downstream switch. Rather than the switch, whenever he got that change notification, he will update the other switch. So that's the reason this process is faster. So here you can see that any switch can generate the TC BPDU, allowing the topology to quickly converge via the handsets. Now, a switch receiving a BPDU will flush all MAC addresses learned on designated port except the port where they are receiving the TC or topology change BPDU. So again, the core thing behind the scene is that all the switches in RSTP, they can generate and send the BPDU, and they can sync the RSTP database, or they can sync the RSTP states. Correct? Rather than they will wait for some max age timer to be expire, or some age timer to expire, or rather than they are waiting for some central authority, say for example the root bridge, to send the updates, to send the updated BPDU to all the downstream switch in the STP. All right. So here again you can see that we have some flavor of RSTP, and next section we are going to do the lab related to that. We'll learn on more on that. Now here you can see that not only the RSTP, their convergence is faster, but they are taking care of two failure. So either it's a direct or indirect failure. We know that the optimization of STP, if you read that STP, you'll find that you have certain mechanism that you can optimize the STP, like uplink fast, backbone fast, port fast is also one of the optimization technique. So port fast is already taken care inside the edge, or the nature of STP, or the edge port. Edge port is working as port fast. Then for direct and indirect failure, this is also taken care inside RSTP. So we don't need to optimize because these features are already included. So in case of any direct or indirect failure, the alternate ports or the backup ports, they will not wait. Rather than they will move to the forwarding state. Okay. Now we have two implementation of RSTP. One is rapid per VLAN RSTP, that is the Cisco proprietary. So because we are going to run the RSTP on a Cisco switch, so we will go and use this spanning tree mode rapid PVST. And the other one is the multiple spanning tree that we'll study in the upcoming sections. Okay, so we have our lab setup. Let me quickly show you this lab setup and what we are going to do here. So for example, this is the topology diagram that we have. What I can do in this, that, so for example, I have switch 1 and switch 2 and switch 3. So here I'm going to run the RSTP in between switch number 1, 2 and 3 like this. At the moment, I'll not use all the interfaces, all the switches, but this will solve our purpose if we run the RSTP in between that, and then we'll go and run few of the verification commands. Okay, so let's stop here, and in the upcoming section, we have a lab related to Rapid PBST or Rapid STP. Now we have the lab section. So what we are going to do here, I'm going to run the RSTP in between switch number 1, 2, and 3. They are actually 101, 102, and 103. So here you can see in the diagram that we have the ports that is connected like this, say 1, 2, and 3. So here we'll run the STP, and then we are going to verify that. Here are the interfaces E00 from switch 1 to 2, and then 1 to 3, and then 2 to 3. I'll figure out in the with help of show-DP neighbor, and then we'll run that. So what I'm going to do, first of all, I'll go and create a VLAN to all the switches. So let me quickly go and create the VLAN. So for example, VLAN 10, because we know that all the VLANs, they have their own STP instance. So I can go to this script, and then I can select all. I can go to conf t and VLAN 10, and then we can exit. All right, so send this script to all the switches. All right, now once we have this, and we can go and check show VLAN. So we have VLAN 10. Now we can go and check show a spanning tree. And for spanning tree, we have a few very important and interesting commands that we used to apply all the time, or we used to run all the time, like show spanning tree detail, show spanning tree summary. So here I can go and run the show spanning tree summary. Here you can see this summary of all these instances. Here you can see that blocking, listening, learning, forwarding, etc. Now we know that by default we are running STP, so that's why you're getting this result. We haven't enabled rapid PVST. We have to change the mode for that. We'll do that. Then you have the detail command. In detail command, you'll come to know most of the things like the topology change, notifications, the timers for STP, etc., and etc. So here you can see that we are dealing actually with switch number 1, 2, and 3. I don't want to add other switch and the interfaces, but we have so many interfaces that is coming here. So let me try to run few more commands, and then we have, say, interface. This is also very important command. So for example, interface 0/0 and enter. So now with this command, I can see that this particular interface is in forwarding state. The role is designated, and like that, I can go and check. So basically, say for example, I have 3 switch, and in this switch, I want to know that who is my root. So suppose I have switch 1, and then I have, say for example, switch 2 and switch 3. They are connected like this. So let's try to figure out first of all who is the root. Okay, so for that I can go again back to the show spanning tree detail, and here we'll see that who is the root for VLAN 10. I am not considering VLAN 0, so let's leave this VLAN 0. Everywhere we are seeing this VLAN 0. So let me quickly go and check that do I have VLAN 10 everywhere. So I can see I have VLAN 10 here, and then I should have VLAN here. So I have all the VLAN, although I haven't added any interface inside the VLAN 10. So what I will do, that I'll move some interfaces inside VLAN 10. So let's do that. I'll show CDP neighbor. Let's check that who is connected with switch number 2 and switch number 3. So here you can see these are the interfaces. I can go here, interface range E0/0 to 1, and this is switch port access VLAN 10. Likewise, I'll go and select the range that is from, here you can see 0/2 to 3, and this is also I'll make as switch port access VLAN 10. Okay, I'll go to switch number 2, and here also we'll run sociodp neighbor conf interface range E. Let's see. So we have 0, 0, 0, 1, 2 until like that it is connected. So from 0, 0 to 0, 3, and finally we'll go to switch number 3, and we'll check that neighbors for 1 and 2. So these are the ports. So I can go here and do interface range 0/0 till 3, switch port access VLAN 10. Alright, because we want to verify this only for VLAN 10. So show spanning tree VLAN 10 and then detail. So now here you can see this is telling you the information about VLAN 10. That's okay. And if I go inside VLAN 10 and if I go and check who is the root, so here you can see that the root port ID is this, the priority into the MAC address. So let's verify that this MAC address belongs to which particular switch, correct? So now if you go here and check, your MAC address is AABB C006500. Now if you see this particular output, and what is the priority? 32778. Why this is 778? Because 32768 is the default priority plus the VLAN ID. So that's why it is showing like this. So everywhere you will find that the priority is 32778. So whoever has the lowest MAC address, that switch will become the root, correct? Root bridge. All right, so let's continue this. All right, so we can verify like this, and because we have two interfaces connected, so you are seeing interface E0/0 up to 0/3. Although if you go to any of the port and you'll see the detail, you can see clearly. For example, E0/2 for VLAN 10 is the designated forwarding, that is the DP. Whose cost, whose port priority, port identifier, you can see here, they have the priority of 32768 plus 10, that's the VLAN number, and this is the address. Now the designated bridge has priority this is the MAC address. Then again you can see the port priority and all other data. Now the question here is that in this scenario, who is the root and then who is the non-root, or maybe who is the root and then what about the designated port and the root port and blocking, etc. Because we are running this spanning tree protocol at the moment. So for that you can go and check show a spanning tree, and then bridge means yourself. So we have two options here. One is the bridge option, that is my, and then what about the root? So I can go and check the bridge address and then the root address, and here you can see that bridge address for VLAN 10, we're focusing on VLAN 10, and root address for VLAN 10, both are same. So that means that this particular switch is the root. Now, since this is the root, I want to know that what is the port status. So now if you go here and check, say for example, VLAN 10, and say we have option for interfaces as well. Interface wise, we can go and check, say E0/0, and then I can check the state as well and detail as well. So interface wise also you can filter. So for example, 00 is the designated port. So if you go and refer the topology diagram, we'll find that we have different port from switch that is going to switch 1 to 2, say 00 and 01. And here also you have 00 and 0/1. So this is a DP. That means if you go and check here, this must be RP, correct? Again, whatever we have a study, we are following the same thing. So now if I go and copy this command here, you can see here this is a route forwarding. That's correct. So DP and RP, like that we can go and analyze. Now what we want to know here, I fully want to know the root address and the bridge address. So root address we know that will be 6500. And now again if you go and check the bridge address for this particular switch, what is the MAC address? Because priority is the same. Likewise, if you go and check the MAC address for this particular switch, you'll find this is 6700. So as per the lower MAC address, switch 1 is the winner. Now if you go and check this particular interface, that the interface between switch 2 and switch 3, here you will find this blocking. So spanning tree VLAN 10, say for example detail. Now for VLAN 10, you'll find that few of the ports, so this is root, it's okay, 00. You'll find blocking, and you'll find uh, ports here in switch 3. A few of the ports are in blocking stage. Okay, so this is related to STP. All these commands related to STP. So what are the big commands we have or important commands we have? Show spanning tree summary. It will give you the summary, the spanning tree, and for that particular VLAN, you can check the detail like this. Then you can check, so spanning tree. So for example, sometimes we used to use filters as well. So for example, I can go and check include, and then um, we can filter certain things here. So for example, designated, or then I can add here designated, and say for example other also if I have. So everything is designated forwarding because of this is the root. So here you can see all the ports, they are coming like this. Yeah, so we have option, we can filter, we can add multiple filters as well. Here you can see that we have only 2 port address designated. All right, but what we have to do in this lab, that we have to go and run the RSTP. So I'll go to the switch and we have to change the mode. So spanning tree mode is, and if I type question mark here, you can see that you have mode MST, PVST, and rapid PVST. Now, if you are changing the mode for rapid PVST, you should do this to all the switches, correct? So we'll go here and paste that command to all the switch. Then these switch will get converged. Once these switch will get converged, now we can go and check show a spanning tree, and you have the same options here, correct? So here you can see that for MST you have some other option, but show a spanning tree, and then we can go and check detail. Inside detail you can see that VLAN 1. I don't want to check VLAN 1, but still VLAN 1 is executing RSTP compatible spanning tree protocol. You can check this. Better I can go and run the command show spanning tree VLAN 10 and then detail. So we can check only VLAN 10 commands. Now we will see that the port role will get changed. So DP will be DP. There is no problem on that in switch number 1. But if you go and check this in switch number 2 and 3, as per the rapid STP, the designation will get changed. So this is root, it's okay, designated forwarding, designated forwarding. Now here you can see this alternate blocking. So now you can see that the designations are getting changed. The role of the port is getting changed. So VLAN 10, so a spanning tree, VLAN 10 and detail. Now here also you can see this is the forwarding, alternate blocking, alternate blocking. Alright, so this is the way that we can go and run the RSTP and then we can verify that. Alright, so we can verify like this. Again, if you want to check more options, you can go to show spanning tree VLAN 10. If you want to check root and then other options, here you can see that you have options related to priority, port, hello interval, details, cost, etc, etc. Then if you want to check some other stuffs, here you can see if I go to a spanning tree, again if I want to check the bridge and then the protocol, and if I press enter, so here you can see it is running in RSTP. Same thing that we have in STP, there is no much change, slight change in the configuration, but the verification options are the same for STP as for the RSTP as well. Next topic we have multiple spanning tree, MST. Now why we use MST, and it's very interesting that we should go and check the generation or the evolution of a spanning tree protocol. We have three different type of spanning tree protocol or STP. We have common spanning tree protocol where you have a single instance of STP for all the VLAN. Then to optimize that, we can use PVST or PVST plus, that is per VLAN spanning tree. Say when we have single instance for all the VLANs, so for example, I have VLAN 10, 20, 30, 40. At the moment you enable the STP, you'll find that that STP is running for all the instances of VLAN or all the VLANs. Rather than we can go and optimize this behavior with PVST, PVST plus, but still further we can go and enhance this process with help of MST. Because the problem with PVST or PVST plus is that you have to maintain a separate STP instance, and that will be overhead in terms of CPU and memory for the switch. So if you have, say for example, thousands of VLAN, so at that time it's actually very difficult for switch resources to manage that much amount of databases. Now what we can do in multiple spanning tree is that multiple VLAN instances can be mapped with one STP instance, or multiple VLANs can be mapped with one STP instance. By default they will be mapped with MST0, but we can create from 0 to 15, means total 16 instances of MST is possible to create. Now here you can see that each MST instance, that is MSTI, builds their own RSTP topology database, including electing its own root bridge. Now the selection of root bridge and the various parameters are almost exact that what we are doing in the STP. Only the way that we are going to configure is different. So how we are going to configure the MST First of all, obviously, we have to change the mode of a spanning tree to MST. Once we change the mode, then MST further separates the STP topology into regions, means we have to define the regions. All switches in region must be configured with identical MST parameters. So what are those parameters? We have 32 byte of configuration name, 16 bit of revision number, and then we should do VLAN to instance mapping. Now what all these things you can see here in the configuration, even in the lab also you can understand more about all these terms and terminologies. Now here you can see that important information that if two switches are configured with different MST parameter, they belong to different MST region. We can have up to 16 MST instance, 0 up to 15. So suppose if uh, I just started MST, so what will happen? Obviously, everything will be fault inside MST 0. So if you do not do any configuration, simply you enable the MST, they will fall under the MST 0. We have this internal spanning tree is responsible for maintaining the topology for the entire region and all the MSTs. Only the IST can send and receive BPDU and encapsulate the MST information within the BPDU as an MST record or M record. The IST is always mapped to instance 0. So we have internal spanning tree as well, who is going to map or manage all the record inside the MST0. MST is compatible with other implementation of STP, and MST region is uh, obfuscated from non-MST switch, which will see the entire MST region at STP or RSTP switch. So it's not that, say, once we have multiple VLANs, so for example, I have VLAN 10 to 20, 21 to 30, I can map with MST instance 1, MST instance 2, etc. But still, they are compatible or backup compatible with other MST as well. Okay, and those information will come as a non-MST region. So it's something like you have MST, STP, and then you have non-MST STP. They are compatible. Alright, how we are going to configure? First of all, we need to change the mode, and then we have to go inside the spanning tree configuration. We can give the name revision, and then we have the instance to VLAN mapping, and that's it. Once we do the instance to VLAN mapping, we can go and check the pending. And earlier I told you that the way that we are configuring the STP, like how you're creating the primary or secondary or root or etc. Likewise, we have to do the things in MST as well. Okay, so the commands are very much similar. Instead of VLAN instance, they will be the group of VLANs or the instance mapping. Okay, so what we are doing inside MST is that we are mapping various VLAN to one instance. So instead of running the commands over VLAN, that is the default nature of traditional or the STP 802.1d, we are running the command with respect to instance. Now, where this instance is pointing to, it is pointing towards the group of VLAN, right? So this is the way that we can utilize the resources efficiently. If we have the VLANs, we can group those VLANs, we can map with the various instances of MST, and then behind the scene MST will work with those groups, and the overall performance for the switch, say for example the resource utilization, the CPU capacity, memory, etc. will be efficiently utilized. Alright, so let's stop here, and in this section we'll perform the lab task. Let us perform the lab task related to MST. So first of all, what I will do that I'll go and create say VLAN 10 to 100, because we are going to map these VLANs with MST instances. So in all the switch, I'll go and do the same. So now we have VLAN 10 to 100. and we can go and verify this VLAN. I can see that you have these many VLANs that I can map inside the MST instance. So what will be the command number one? That I should go and change the spanning tree mode. So now the spanning tree mode is MST, and I should do this with all the three switches that we have. So let me go and go to the configuration mode and oops, conf t and copy paste this mode command. Again, I'll go to conf t and do the copy paste. Now what we can do, that we can go to the spanning tree and MST configuration mode. Once you are here, you can see that what options you have. You can go define the name, revision, instance. So we'll do that. First of all, I'll go and give the name. So for example, my MST. Then the revision, for example, revision is 2. Then we have this instance. So instance and VLAN, say for example, instance 1, and then the VLAN range is from, say for example, 10 to 50. Then then we have instance 2 VLAN 51 to 100 that we have created. We can go and check the configuration with show pending. So here you can see that you have a VLAN instance, and whatever VLAN that we haven't mapped here, you can see that they are mapped with MST0. Correct? So now we have two instances like this. Great. Now once we have this, then I can exit and we can run the normal spanning tree command. So we have show spanning tree MST, and then we can check the configuration. We can go and check the detail. So instead of MST, you can think like you are running spanning tree VLAN. So instead of VLAN, you think like MST. That's the command. So we don't need to memorize the commands and all. So here you can see this in detail, and the port ID, priority, and everything is in detail. Now different type of VLANs actually is mapped with the MST instance, so that's why it is looking like this. Likewise, I can go and run this command to other switches as well. So I should go and change the mode to MST. Then we should go to the configuration mode and run these commands. So let's do it. And we can verify with show pending. And then we should go here and do this here. Show pending, and then we can exit and exit. Now we can go and check show spanning tree MST. And if you want to check the details, we have the detail option. If you want to check any of the interface, we can check that also. If I have my MST, that's the name of my MST. So MST instance list, say for example, if I give a word, and let's verify this. So what word I have here, you can see that show spanning tree MST. You can see the output in detail, and this is the name. And if I go here and check the output, say show spanning tree MST, this is not supported here. So if I give, say for example, number like MST1, Not like that, but we can go and give the instance list that we have. So what instance list we have created that we can actually verify in the configuration. So we have instance 1 and instance 2. When I'm giving 1, so MST1 is coming like this, and if I give 2, it is throwing error for 2. And if you go and check, so MST in detail, so we have MST0, we have MST0, we have MST1, and that's the reason. So it is showing only 2 instances. Rather, if I go here and check the instance in switch number 1, and if we go and check 2, we don't have information for 51 to 100, like MST2 is not created, but it's okay. This is the way that we can go and map the VLAN to the instance mapping, and then we can go and verify the commands as well. Now, one last thing, that if you want to change the priority, because switch 3 is having the lowest uh, it's the highest MAC address, so its priority is lowest in terms of selecting the root bridge. That's why here you can see that who is the bridge, who is the root. So root is the switch number 1 because its MAC address is the lowest, but if you want to change it, you can go and change spanning tree, MS tree, and then you can go and check the, let me quickly check the configuration. So we can do like this. If you want to change the priority, we have, say for example, VLAN 10. You can see the priority is there. Now this method is for the STP, but here we are focusing to MST, and then the instance, say for example, instance is 1, and here you have the priority. So this, we have two options. Either we can use the priority command or the root command. I just wanted to make this switch as a root, and we can go and give him a root primary. And now if we go and verify the MST command, so here you will see that who is the bridge and who is the root. So this switch for MST1. So now his priority automatically get decremented, and now that switch 3 becomes the root. Now you can see their port status is changing. Initially it was forward blocking, but now everything will become forwarding because now my switch number 3 is the root switch. Okay, and same rule is applied for STP as well. In STP you have to give the VLAN, in MST you have to give the instance ID. Alright, so let's stop here. Now we reach to 3.2. 3.2 is belonging to layer 3 technology. In layer 3 specifically we have to learn about routing protocols such as OSPF, EIGRP, and BGP. So let's start with OSPF. Now, OSPF, that is Open Shortest Path First Protocol, is a link state protocol like ISIS. Now, what link state protocol is doing, that instead of sending the entire topology table hop by hop, they are sending the state of a link to the neighbor device. Now, how this technology is working, and let me try to draw here. So generally, all the link state protocol, they are forming, first of all, the neighbor table. So they are sending the update to all the adjacent device or the neighbor. With help of neighbor table, they are forming the topology table. Sometimes we are referring this as a entire database as well. And finally, they ran the SPF algorithm here. From the topology table, they are going to form the best path, that is the routing table. So we have three different types of table: neighbor table or database table, topology table, and then finally the routing table. Now the mechanism behind this and the theory behind this we'll see in upcoming slides. So OSPF is entirely dependent upon areas. Generally, we are telling that we have one backbone area. So here you can see that you have area 0, and logically all the areas are connected with area 0. Now these areas are 32-bit. They can be a flat number, or you can define like in dotted representation 000 like this. Areas has continuous means area. You can see that you have area 0 and then area 1, 2, 3. Um, so maybe you can think that can't I connect area 3 with area 5 or 4? Yes, we can do that connection, but you can see that area 4 is not directly connected with area 0. So somehow I have to create tunnel, or the area 3. Uh, I have to create area 3 as a tunnel, or we have to use some sort of virtual link. So area 4 can think that is directly connected with area 0. So such type of arrangement we need to do, and then the link state advertisement will flow from one place to other place. That's the LSA, correct? The OSPF send LSA when there is a change to one of its link, and will only send the changes in the update. LSAs are additionally refreshed by after every 30 minutes. So how we can summarize it, that OSPF is a link state protocol dependent upon area. They are sending their LSAs or their advertisement to all their neighbors, and with that they are forming the neighbor table, topology table, and finally the routing table. Apart from that, that OSPF traffic is multicast. They are using 224005 for all the routers and 224006 for the designated router. The theory behind this we can discuss in upcoming session. They are using the Dijkstra shortest path first algorithm to build the routing table from the topology table, and they are supporting the variable length subnet mask. So here you can see that first of all they form the neighbor table, then they form the database, then they do their algorithm, that's the SPF algorithm, Dijkstra's SPF algorithm. Finally, they will form the best path table, that is the routing table. OSPF supports IP routing. Their AD value is 110. Their metric is cost. They are going to form the neighbor table, topology table, and routing table. Uh, all the areas should be supposed to be connected with a backbone. That's the area 0. If we have non-backbone area connected with any other area, then you have to create tunnel or virtual link in between that. Now, suppose we have such type of topology here. You can see that I have area 0 connected with area 1 and area 2. So now what we are going to tell about these devices, these routers, router A and C, they are termed as a ABR, area border router. They are termed as a ABR, area border router, because they are in the border of different areas. Okay, and we'll see that according to that the routes are also going to get reflected. So when we are talking about the routes, you'll find that you have O routes and then OIA, that is OSPF intra area. So you have two type of route, OSPF intra area route, that is this. Then you have inter area, across the area, that is this, and we'll see that we have E1 and E2 routes as well, that is coming from the external as well. Now if you see this diagram, it's actually very simple, straightforward, that we have 2 or 3 routers in area, but assume that if you have 50 or 100 routers in area. And suppose if I have 200 routers and all the 200 routers are inside area 0. So at that time, what will happen? The computation means to run that SPF algorithm becomes CPU intensive rather than if you have a small areas and then you have 50 device, 100 device and 50 device in those areas. So in that case, all the areas they will run their independent SPF algorithm and then they will send the update to the backbone. So in that case, the way that we are going to run the SPF algorithm, or in other words, the process, the CPU utilization, the memory will be optimized and will be used betterly because now you are running the SPF algorithm across small areas, and then those areas are going to send their LSAs to the core or to the other areas. Correct? So that's the thing, and that when we are uh, that's why we don't have only area 0 rather than we have multiple logical areas, and then we are going to divide the devices or the routers inside the area. Then here you can see that suppose in case that if you have device and that is not connected with the area 0, so in that case you have to create the virtual link, the device which is separating the area, they are termed as a ABR. Then you have internal router, then you have backbone router. Again, these are just the terminologies. All right. Now here you can see that you may have chance that you are connected with non-OSPF protocol. So you are getting the route, say for example, from the EIGRP domain. So in that case, that router is termed as a ASBR, Autonomous System Border Router. So now here you can see that C and D, they are ABR, Area Border Router, but router G is ASBR because now the routes is coming from the other routing domain to the OSPF. Okay, so uh, here you can see that if we have any other routing domain that will term as a separate autonomous system, and then you have to do the redistribution. Obviously, the router G will do the redistribution from EIGRP to OSPF when it is coming to OSPF, and OSPF to EIGRP when you are sending your update to the EIGRP domain. Now in that case, we have E1 and E2 type of area. Now what is E1 and E2? Here you can see by default it will be OSPF external area type 2, that is the E2. So include only the external cost to the destination network. External cost is the metric is cost advertised from outside the OSPF domain. This is the default type. Then you have E1 that will also have the metric value, that is the cost, but this will be additive, means it will add the cost per hop per router. So include both the external cost and the internal cost. So that's why you have the external cost plus the internal cost to reach uh, the ASBR to determine the total metric. But E2 having only the external cost that will be constant. So in summary, here you can see that you have internal routers, that all router interfaces belong to only one area. You have ABR, you have ASBR, you have backbone router that is inside area 0. Okay, so this is the baseline summary for the OSPF routing protocol. In the upcoming sessions, we will learn more about OSPF terminologies, and we have to perform the lab as well. So what type of LSAs we have in OSPF? OSPF has a long list of LSAs. We are going to discuss the top 5 at least because these we are going to use more and more in the course. So we have LSA, here you can see type 1 and type 2. Now these type 1 and type 2 LSAs are reside within the area. They are very much area specific LSA. Then we have type 3 and type 4 generated by ABR, area border router. They can flow from one area to other area. We'll see in the upcoming slide. And then we have type 5 LSA that is generated by Autonomous System Border Router, means non-OSPF protocol. They are going to generate that. Now here you can see the detailed explanation of all the LSA. Type 1 is LSA and type 2 as well. They are within the area. Use of type 1 LSA is that they have the link, obviously, the status and the cost of all those links, and they are generated by all the routers in a network. So you can think that type 1 as a default LSA generated by all the routers within that area. Then we have type 2 LSA generated by DR in the OSPF network or OSPF domain. Again, this is also specific to the area. When we have the broadcast type of network, obviously that time the DRBDR will come into the picture. Then we have the network summary LSA, that is type 3. What it is doing, that generated by ABR, and this can be used for inter-area communication. We'll see that all the places you have this inter-area link. So you have area 0 connected by different areas, and all these AB are shown in the diagram. They are going to generate type 3 LSA to do this inter-area communication. Then we have ASVR summary. Now the next question here is, suppose from OSPF inter-area, you have to reach to non-OSPF domain. So for that reason, we have Autonomous System Border Router Summary LSA, means somehow you need to reach, or somehow we have a route to reach to the non-OSPF protocol. Then we have external LSA type 5. Now this is generated by the ASBR, and this information will be flooded inside all the areas. So all the areas, if obviously you have the redistribution, all the areas should know how to reach to the autonomous system border router or the network behind the ASPR. We have type 6 as well, that is the multicast OSPF, type 7 as well, that is not so stubby area. And this type 7 is actually very important, and we'll discuss this later on. Now here in the diagram you can see that you have area 1, area 0, area 2. So belonging to area 1, area 2 and area 0, you have this router and network LSA, means type 1 and type 2 LSA will be generated in that. Then you can see that router C and D, they are ABR, so they are going to generate the type 3 and type 4, and the router G is belonging to ASBR, he is going to generate type 5 LSA. Okay, great. Then how this OSPF is going to form the OSPF neighbor relationship. So if you go and connect two OSPF or two routers in between, so suppose for sake of simplicity, I have only two routers connected in a network. So in that case, what will happen? Suppose I have router 1 and router 2, and these two routers are connected, or they are inside area 0. So obviously these routers, because they are within the area, and suppose if it is a point-to-point network, then they will send and receive the router LSA, correct? So what will happen, that they are going to send their hello packet in the point-to-point network or in the broadcast network. This hello timer is 10 seconds and dead timer is 40 seconds, so it's 1 into 4. And in the broadcast network, actually in the NBMA network, that will be 30 second, and then the dead timer will be 30 into 4, that is 120 second. So they will send and receive, they will exchange their hello packets, and if they are matching certain criteria while sending and receiving the hello packets, then they are going to form the neighbor relationship. So here you can see that what will be what are the things inside the hello packet, or what are the fields inside the hello packet. They contains area ID, area type, prefix, subnet mask, hello interval, dead interval, network type, and authentication. Basically it is termed as that they have 8 field inside hello packet, and you should match at least the area ID, the subnet mask, hello and dead interval, authentication, etc. So some fields are mandatory that should match in between two routers to form the neighbor relationship. Okay, so here you can see that a neighbor table is constructed from OSPF hello packet, which includes the following: the router ID, the current state, directly connected interfaces, and the IP address of the remote interface of each neighbor. We'll see that in the lab section, and we'll go and we'll run the command show IP OSPF neighbor, and then we can see the specific about the neighbors. Now the next topic here is that OSPF designated router and backup designated router. So what is happening and how they are going to form the DR BDR, or how they are doing the selection for the DR BDR. Let's discuss about that. So here you can see in the diagram, first of all, these devices, they should have their priorities. So let me show you what I try to tell here. I should have slide for that. Yeah. So here you can see that these devices, they have their unique identification. That's the router ID. All the routers in a network, they have the router ID. We can configure it manually, or suppose if device has the loopback interface or they have the physical interfaces, first of all they will check the loopback interface if you are not doing it manually. So that loopback interface will become the router ID, or the highest physical interface will become the router ID. So they should have the router ID. That will be by default if you're not doing it manually. Once they have router ID, then they are going to do the DR-BDR selection, and this selection will happen only in the broadcast network. So here you can see in the diagram that if we have router ABCD connected with a shared network or the broadcast network, so at that time they will go and select the DR and BDR. Okay, now what will be the selection criteria here? The DR BDR selection are determined by the router's priority, which is configured per interface basis. The router with the highest priority becomes the DR, and the second highest will become the BDR, and the rest are DR brother, something like DR, BDR, others. Okay. Now, if there is a tie in the priority, whichever router has highest router ID, that will become the DR. Now we can go and set this priority like this also, like we can go to the interface and we can set IP OSPF priority, and then we can force to make certain device as a DR or BDR. Now, by default, the priority will be 1. So obviously the selection will happen with respect to router ID. So whoever having the highest router ID in the network, that will become DR, BDR, etc. like that, in that manner. Suppose if you don't want that certain routers or device will take part inside the DR, BDR selection, so you can go to the interface and you can set the priority as a 0. So if you set the priority as a 0, that device will not take part inside the DR-BDR. Okay, so what are the important things we have studied in this video? That type of LSA, then how they are going to form the OSPF neighbor relationship, what are the important fields you have inside the hello packet. All the devices, they are sending the hello packets to the peer devices or the neighbor devices to form the neighbor relationship. Then how they are going to form the DR-BDR selection. Again, the router ID will be important factor here, and as per the router ID, they are going to form the DR-BDR, because by default we are not setting the priority. By default the priority will be 1, and according to the router ID they will select who is the DR, who is the BDR. Let us learn more about OSPF neighbor state, and then I'm going to perform one small lab task where we'll understand more about the OSPF process, OSPF actually neighbor process, and even the baseline commands of OSPF as well. So now when the OSPF, the first stage is that they have to form the neighbor relationship. When they are forming the neighbor relationship, at that time they are exchanging, or they are going through process, or they are going through multiple steps. So what are those states we have? Here you can see that they will start with a down, init, two-way, etc. So in down state indicates that no hellos has been exchanged, but the actual process will start from the init state. Init state, the devices, they will start sending their hello packets. We know that inside hello packet we have some important fields. Few of them are mandatory, like the area, like the authentication, uh, the network subnet, etc. So few of the fields are mandatory, that two sides or the neighbors, they should match those mandatory things. Then they will go to the two-way state. By the end of two-way state, uh, the devices, if they are in the broadcast network, they have to select the DR and the BDR. And by the end of two-way state, the devices, they are forming the neighbor relationship. Okay. Then we have the external start and external exchange. Now external start and exchange is a state where the devices, they have to select that who is the master and who is the slave, so they can exchange their databases. So obviously the devices, they are sending their link state or LS information to each other to build the database. Once they have the database as per the uh, master and slave entry, as per the master and slave role, they have to exchange their LS type, correct? So someone may sending, say, link state advertisement, someone may asking link state request, so LSA, LSR, those things are going in depth when we are talking about the exchange state. Then we have loading, where all the devices, they have to sync their database, and by the end of this loading state, the OSPF process, they are forming the topology table. Remember, we have three important table. We have neighbor table, so by the end of two-way state, they will form the neighbor table. We have topology table. By the end of loading, the devices will form the topology table. And finally, once they have the topology table, on top of that, the devices will run the SPF algorithm, shortest path first algorithm, and then they have to form the routing table. We'll see that if we have the broadcast network, then they will have the rules like DR, BDR, and DRR other. All right, so here you can see that suppose in broadcast network, if we have these rules, this DR other, they will go and stop at the level of two-way, because what is happening in that situation, in that case, is that you are giving the authority to DR and BDR to exchange all the LSs with all the other, rather than all the other DR others, they are exchanging their database packets. So that means they will stuck at the two-way state, means all the DR others, they will stuck at the two-way state. They will not have the full authority to exchange the databases. Correct? All right. So we have a small lab topology. In this first lab, just to start with, what we are going to do, that we will go and initiate the OSPF process. So let me show you this. Although we have this master lab topology, what we can do as per our requirement, will go and use it. So what does it mean? That we'll go and make these devices, so for example R1, R2, and switch 101 within area 0 at the moment. So they will be the part of area 0. And this switch that you are seeing here, switch 105, that I will make as a switch only. Later on we will make this as a L3, but at this point of time, I assume that I have R1, R2, and switch 101, and the IP that I am going to use, the IP will be, say, let me write here the IPs, and according to that I am going to configure the lab. So the IPs that I want to use is, say for example, 10.1.11 and 10.1.1.2 as per the name of the devices, and here, so for example, 10.1.1.101. They are inside the same broadcast network, so you can see that they will go and form the DR and BDR. Loopback addresses I will give like 111, and then this I can give 2222 as the name of the device, and this I will give as 101, 101, 101, 101. Okay, we are going to initiate the OSPF process inside area 0, and then we'll see that how they're going to exchange all those hello packets and the important ls type. All right, so let me go and log into the lab devices. All right, I logged in, and we know that we have other interfaces and links also connected that I don't want. So this is the topology that we have. What I can do here, that I will start with 101 E1/2. So let's do that. I can go to, first of all, let's see this neighbor, and I want to shut down few of the interfaces that I don't want to use. So for example, I want to use only interface 1/2, so 0001 and 1/2. So 0001, so I can do one thing, interface range E0/2 to 3, shut down, interface E1/0, shut down, because I want to use 1/2 only. So rest of the interfaces I'm making shut down. Like that, 1 also I want to make shut down. If I go and check show CDP neighbor, so I have 0001 and 12 that I want to use. Now next I will go to switch number 2. So switch 2 is not required in this particular lab, so leave it. Then I'll go to switch number 5, and we should check this E1/2 configuration as well. So I will go here and check E1/2, and what is configured here? Nothing is configured. If nothing is configured at this point of time, at least what we can do is we can make this interface as a switch port. Okay, so here you can see this capabilities R, S, and I, and that I don't want. I'll make this as a switch port. Then we'll go back to the switch number 5. Here you can see, and the interfaces we have is 0, 0, 1, 2, 3, and 10/0. So apart from that, what I want, that I want to make other interfaces as a shutdown, and we have so many interfaces here. You can see, even we can leave it as well, just to check the configuration for any of the interfaces. Say so run interface E0/0 that is connected with router number 1, and then router 2. So these are the interfaces connected. I don't want to do anything. Rather, I will do one thing, that interface range E0/0 up to, for example, 4 maybe, and 3. I'll make this as a switch port and no shutdown. And then interface E10/0 that is connected with switch number 1, that if you see here, switch number 1, what interface we have here, let me scroll up, 10/0, yeah. So I can go here, interface E10/0. I'll make this also as a switch port, no shutdown. Alright, so we are very much good with switch number 1 and switch number 2. Here again I can go to interface E1/2 and make this as a switch port no shut. Alright, so let me quickly see here that what I exactly required. So E1/2 should not be switch port. It should be a routed port. So I'll do no switch port and then I'll assign the IP address. So for example 10.1.1.101, and then I'll create one loopback, say loopback 0, IP address 101 and 101.101. So what I have done here, we can check show IP interface brief. So I have interface E1/2 and one of the loopback interface where I have assigned the IP addresses. Okay. All right. Great. So now we can go to R1 and R2 and the interfaces you can see here. So I'll go to R1 first and I can go to interface E0/0. I'll assign IP 10.1.1.1 and then I can do ping just to check that the far end switch is reachable or not. So it is reachable, then I'll go and create one loopback, say 0, and IP address I'll give 111 to that loopback. We'll go and check the show IP interface brief so you can see that we have the IP configured here. Now let's go to R2 and inside R2 we have interface E0/0. I can go and give the IP like this and then I'll create one loopback 0 where I can give IP related to as per the diagram or as per our schema 22222, and then let me try to ping first of all within the same network. Obviously everything is inside the same network for this example. So what I'm doing that I'm pinging to all the devices from R2. So now we have the baseline IP at this connectivity connected. The thing here is that we are going to enable the OSPF to all these devices and we are assuming that all these devices are inside area 0, correct? So let's do this and let me go back to the lab. Yep. So before doing that, at least one of the device I want to enable the debug. So I want to enable the debug OSPF packets and events, debug IP OSPF packets, and then I want to enable the events as well. Okay, let's do this OSPF configuration. So we can go to router OSPF and then you have to define the process ID, say 1 I'm giving at this point of time. Then I should go and advertise the network. So network is, I have two network, one is 10.1.1.0. I can go and give the wildcard bit inside area 0. So this is the format that we can go and enable the OSPF. And at the moment I enable that, you can see that we have event because we have enabled the debug as well. We can see that this router using this multicast address and the router ID is get selected as 11111. We have discussed this earlier. If I go and check show IP OSPF, you can see the read router ID is 11111 and we have the other information as well. Okay, so we have the OSPF configuration and periodically he is sending the hello packet. We can go and check the configuration for that, what we have done. So we have enabled the OSPF process, and then we have advertised the network, correct? So likewise, I can go here and initiate the OSPF process here as well. Then I can go and I can assign the router ID via the CLI command as well, means manually as well. But if you do not do this, automatically they will take this loopback, highest loopback address as a router ID. So then I have network 10.110.0.0.0.255 area 0, and then I have network 2222, say 0.0.0 area 0. Alright, and let me see that what configuration I have done here. Now they try to exchange this neighbor relationship. From there they will go and form the topology table, and finally they will go and form the routing table as well. Okay, so let me quickly see that what command I have given here for the network. Because we have used /32, that's why I have given 0.0.0.0.0. Now somewhere you will find that you are moving to loading to full state, and here if we can see that information in the log message. So we have enabled the debug and OSPF authentication is 0. We haven't put any authentication, so it is telling that OSPF authentication is 0. And here you can see that we have this loading to full message. If you go and check show IP OSPF neighbor, then you can see that you have DR BDR selection already happened. For router 1, he is telling that router 2 is BDR. Now if you go to router 2 and if you check show IP OSPF neighbor, you can see that he will tell who is the DR. So for router 2, this 11111 is the DR, what is the interface, what is the IP address that we have discussed earlier. Now I'll go to switch number 1, and here also I'll go and do this router OSPF say 1, and then I will put the network, for example the loopback address that we have 101.101.101.0.0.0.0 area 0, and then I'll put the network that we want to form the OSPF relationship. So we have network and with the wildcard bit 0.0.0.0 to 55. Alright, and within area 0. At the moment I'll do this, I can go and check show IP OSPF neighbor. Now you can see that he is seeing that who is the DR and who is the BDR, correct? The third device. Now if you go here and check the OSPF neighbor, you can see clearly that DR other. So now this IP is DR other. We haven't assigned the router ID manually, but here you can see that they can detect it. Means the router process can go and assign what will be the router IP or router ID for these devices. We can go and check like this, show IP OSPF, and you can see the ID. Now if you want to filter and use that, I try to do with this command, simply you can go and check the ID. That will tell you who is the router ID. Alright, so this is the way that they are going to form the DR and BDR. And if I have one more device in the DR other, then you could find that the process will stuck as two-way state. Okay, so what I'm telling here is that if I am here and if I have one more device connected to this guy here, and that is also working as a DR other, then these two devices, they will stuck as a two-way state. They will not exchange the entire topology and database tables, etc. All right, so let's stop here. In this session, I'm going to cover OSPF network type, metric, and passive interface. And next section, we'll do the lab related to this. Now, if you go and check the syllabus, so let me quickly show you the syllabus. In this syllabus, you'll find that in 3.2, you have to learn about OSPF and you have to compare with EIGRP. So for that, what I'm going to do, that I'm going to cover EIGRP in different series of videos. So once we know OSPF, once we know EIGRP, it's easy to compare. Then in 3.2b, you can see that we have to learn, understand more about OSPF. And that's the thing we are doing at this point of time. So let's quickly understand the network type, OSPF metric, and the usefulness of passive interface. Now, OSPF is supporting a wide variety of network type. Here you can see that in OSPF, you have these many network type support. Now, how to memorize this, because you can see it's a big number, this network type. So you can think like this, that you have point to point and you have, see here, so point to point, and then you have point to point, point to multi-point, broadcast and non-broadcast, like you can think. So you have network type broadcast, and then you have network type non-broadcast, and then again if we add with point to point and point to multi-point. So now point to point, obviously we know that point to point is just point to point network, two devices are connecting with each other, it's a point to point network. Then what about point to multi-point? So here you can see that point to multi-point non-broadcast. So you can think that you have point to multi-point broadcast and non-broadcast. Okay, so that means you have 1, then 2 and 3. Apart from that, you have network type broadcast. So you have network type broadcast and you have network type non-broadcast. That means you have total 5 different type of network support. Now again, if you go and check the nature of the broadcast and non-broadcast. So if it is a broadcast, that means the DR-VDR selection will happen and the neighbor will form automatically. Means you don't have to write the manual command to form the neighbor relationship. Correct? But if it is a non-broadcast, and suppose if DR-BDR is forming, you can see that the hello is unicast multicast. When you're seeing unicast means you have to go and use the neighbor command. So you have to manually form the neighbor. Correct? So once we know about the broadcast and non-broadcast, and again you can see the timer as well. For broadcast network is 10 and 40, and for non-broadcast is 30 and 120 seconds. Correct? Now same concept we can use here. So here you can see that point to multi-point. You can think this is a point to multi-point broadcast. So that's why it's a multicast. Hello. They will not form the DR-VDR because again it's point to point and you have so many points to point to multi-point. You can think like this. So whenever you have point to point network, you are not going to form the DR-VDR because just two devices, why you will form DR-VDR. Then I get point to multi-point non-broadcast. Now this is non-broadcast, so that's why you have to go and use the neighbor command to form the OSPF neighbor relationship. That's the whole summary we have for the OSPF network type. So let me go back to the theory. Now here you can see that it's a broadcast. So it will do DR-VDR selection, then it is using these multicast addresses. Because this is a broadcast, they will not form the neighborship manually, automatically they will form. Point to point, no need to define the neighbors because you have only two ends. They will form the neighbor relationship. Their timers will be 10 and 40 seconds. They are going to use the multicast address. But again, point to multi-point as well. Everything that is valid here for point to point, it will be valid for point to multi-point as well. Okay. Now Then we have non-broadcast. Whenever we are talking about non-broadcast, then you have to go and form the neighbor relationship manually. Now OSPF will elect DR and BDR, but neighbor relationship will be manual. And that's why we have this summary. This summary, it's easy to memorize, even no need to recall, but just will make a point that okay, you have point to point, point to multi-point, non-broadcast, point to multi-point broadcast, and then you have broadcast and non-broadcast network. How we are going to do the configuration? Configuration part is actually very easy. Only one command is there to define the network. You have to go to the interface. Suppose you are over this serial interface, you go to the interface and use this command IP OSPF network. Suppose if you go and type question mark, then you'll get all the options. So is it a broadcast? Is it a non-broadcast? It's a point to a multi-point, etc. Each and all these options you will get. And if it is using unicast method, means if it is a non-broadcast, then you have to go and define the neighbor. Otherwise, rest of the configurations are standard OSPF configuration. So for example, NBMA, non-broadcast multi-access. So here we are going and defining the network type is a point to multi-point, and if it is a non-broadcast, then you have to go and define the neighbor, right? So just refer this summary and things will become easier. Now OSPF is using cost as a metric. Here you can see the speed and the cost. So for example, for fast Ethernet and above, your cost will be 1, and then you can see for token ring for Ethernet, for token ring 4 Mbps, you can see the cost. Now the lower is better. So if lowest cost is there, that will be the preferred path in the route selection. How we are going to do the basic OSPF configuration, although we have done one lab, so there you have seen that you can go and initiate the OSPF process. You can define the router ID, otherwise it will take the highest loopback or highest physical interface if it is not configured. Then you can define the area, and that's it. So this is the baseline configuration. Now here interesting thing is that we are defining the wildcard bit. And now it is recommended that if you know the exact subnet, so according to that you can use the exact wildcard as well. So suppose if I am using point-to-point network, so I can use, say for example, 172.168.1.0. So here it's 17. So 172.171.0, and then I can use wildcard 0.0.0.3. So like that we can go and use the wildcard wisely. What will happen if we go and initiate the OSPF process, and once we start advertising the network, or once we put this network command, then they will send the hello packet, the neighbor relationship will start working. We know that as steps down, init, two-way, X start, exchange, loading to full. First they will form the neighbor table, then topology table, and finally they will run the SPF algorithm and will get the final OSPF routing table. Correct? Now the final thing here in this recording, as per the theory, the passive interface, the concept of passive interface. Now suppose if you don't want to form OSPF relationship, then you can go and make any of these interface as a passive interface. So suppose if I make this interface as a passive, then you can see that the passive means the command prevents update from being sent out or received from this interface. So if I go here in this example, it is showing this interface. So if you go and make this particular interface as a passive, or any interface as a passive, they will not participate in OSPF neighbor relationship, means they will not send or receive the updates. And that's the usefulness of passive interface. But generally how we are using this command is we will do this thing, no passive interface E0. Here you can see, first of all, we'll make all the interface as a passive. So the command one is passive interface default. Suppose if you have 10 interface, that means all the 10 interface, you're not sending and receiving the updates. And then you will go and add the interfaces one by one where you want to send or receive the updates. Okay. We have one important note here that the passive interface command will prevent OSPF and EIGRP from forming neighbor relationship out of that interface. No routing updates are passed in either direction. So this passive interface is true not only for OSPF, but this is true for EIGRP as well. So we are going to stop here, and in next section, I will show you a few of the things that we have a study here, like network type, how you can go and change the network type and you can enable the passive interface. Let us do the lab. Here you can see the topology. We have router 1, router 3 and switch 101. I'm using in between switch 105 as a L2 switch. So that means I have area 0. So this big blue circle is area 0 and the network is 10.1.1.0/24. Then I have switch 101 and 102 connected. That is inside area 2020, and the network is 10.1.102.0. So 101 is dot 1 and 102 is dot 2. I have already assigned the IP address. So what we'll do, we'll go and enable the OSPF process. Then we'll go and check the default network type, and then I will make any of the interface as passive interface inside area 0, and then again we'll verify the OSPF neighbor relationship. So let's do this. I can go to router OSPF 1, and even if we are here, we have option that we can run the script as well. So if you are doing the configuration over empty putty, you have this option for a script, say conft router OSPF 1, and then you can advertise the network as well. I can select the devices and then I can send the script. Now once OSPF is configured, then I should go and assign the, or I should advertise the network, or should I can use the network command. So what you can do here, you can go and check the IP route, your connected interface, and in the network command, actually, you can go and use it with wildcard bit, and we should check this 10.1.1.0 is part of area 0. So we know as per our topology this is correct. Then we have one loopback here that will be depend that in which area you want to put. This also I'll put inside area 0. And then I have one more network that is this guy here connected with area 20, area 20. So these are my network command. Likewise, I can go to switch number 2 and I can go and check the connected routes. I can use my network command. First of all, I'll advertise my loopback inside area 20. And then I have my network that is connected, that is inside area 20, because the bottom switch is actually everything is inside area 20. So that's why area 20, area 20. All right. So at the moment we run this command, you'll find that both the switches, they are now interfaces are part of area 20, and they will run the OSPF, and here you can see that the OSPF loading to full means all the states are completed. So I can go and check show IP OSPF neighbor. You can see full BDR and the interface as well. Then we can go and check show IP OSPF. Actually show IP route OSPF. So here you can see that you have the metric value and you have the AD value. AD is 110 and the metric is 10 plus 1. So that's why it is 11. We know that for Ethernet interface that is 10 and then 1 is for loopback. So that's why it is showing like this. Alright, here you can see the Ethernet. So for that we have 10 and then generally 1 it is using for loopback. Alright, next thing that I want to check here is that is show IP OSPF interface, and that is E0/0. Now here you can see that interface where the network type is broadcast. So what I can do that the switch is connected over E00. I can go to the interface E00 and I can make that IP OSPF network as point to point. Now here you can see that you have broadcast, non-broadcast, point to, multi-point, point to point. And if you go to point to multi-point and type question mark, you have point to multi-point. By default it will be broadcast, and then you have the non-broadcast like that. So I'm interested to make this as point to point, and both side I should do like this. So other side also I should go, and I should go here to E0/0 network point to point. Now you can see that again OSPF process is running. It is going from full to down, and the SPF algorithm is running one more time. And then we have the new tree, SPF tree, and from there we have new routing update or routing table. Show IP OSPF and the interface is E0/0. Here you can see this network is now point to point. You can see this cost as well. There is other information as well related to timers, non-stop forwarding, etc. Alright, so we have done this task with these two switches here. Likewise, I will go and initiate the OSPF process, and I will advertise the network for R1, R2, and only R1 and R2. We don't have any R3. Alright, so let me quickly check here in switch 101 what is the complete OSPF configuration that we have done. So these three network, one network is belonging to the network that we have connected with R1 and R2, that is nothing but the area 0. And then these guys have one loopback address 111 inside area 0. And likewise I'll go here and then I will use 222 area 0 and then this. Now if I go ahead and check show IP OSPF network, here we have three devices who is forming the OSPF relation. If I go and check show IP OSPF interface, I want to check the interface E0/0. So here I can see that again the network type is broadcast. Now in our topology, either I can use network type as a point to point or broadcast, but we have seen that chart that as per the topology, suppose if you are working or dealing with frame relay, then you can use NBMA and then you have the mode for NBMA, correct? I don't want to make this as a non-broadcast. If you make this non-broadcast, so suppose if I go to R1 and R2, and I should know what is my neighbor, show IP OSPF neighbor, and if I go to interface E0/0 and if I make this IP OSPF network is non-broadcast, then I need to add the neighbor command manually. So now if you check your neighbor, you can say it's a down. Because in this case, you have to use this neighbor command. So you have to go to router OSPF1 and use the neighbor command. Who is your neighbor? So this guy is your neighbor. Then use the neighbor command. This guy is your neighbor. So manually we are adding the neighbor now. And here also it is detached. So these are my neighbors. I'll go to interface E0/0. IP OSPF network is non-broadcast. Then router OSPF1. We'll go and add the neighbor, this, and again I'll go and add one other neighbor. Then we can go and check show IP OSPF neighbor. Still this is down. Show IP OSPF interface and then E0/0. So now it become non-broadcast, but we are seeing here that the network is down because we are using the wrong network type here. If we have the NBMA type of, or if we have a non-broadcast type of network, then we should go and use here. Again, you can see this hello and dead timer is changing. Okay, so what I'll do here that I'll go and make this interfaces again backup. Interface is 0/0 and IP OSPF network is, say for example, broadcast. So one side is broadcast and other side is non-broadcast at this point of time. And now you can see it is forming the relationship with the switch 101. So if I go and check do show IP OSPF neighbor, you can see it is forming this. Likewise, I'll go here and again interface is 0/0. IP OSPF network is broadcast. And then we can go and check show IP OSPF neighbor. Alright, so now we have to test the final piece, that is the passive interface. So suppose if I go and make one of the interface over R1 as a passive, so let's do that. I can go to router OSPF1. You can see that we have this command passive interface default, and then you can go and make no passive interface. So once you do this command, all the interfaces become passive, means your neighbor is down. So here you have to use no passive interface, and that is the E0/0. E0/0 is the interface. I want to make no passive interface. And again, if I go and check the neighbor, so here you can see this is up. So that was the lab related to whatever we have studied in the previous recording. You can refer this particular lab.